Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we're going to work through right triangles in trigonometry. Now, this is the first lesson in our trigonometry unit, and what I'm going to do is work through my lesson, show you how I'm working through each of these problems, so therefore you can see how my instruction went within my classroom. So let's go ahead and get started with right triangles. First thing I always like to tell people is, what basically is going to be in this lesson. We're going to find the missing sides of the triangle. We're going to evaluate the 6 trigonometric functions, given a triangle, given an equation, and then we're also going to talk about evaluating trigonometric functions with special right triangles. So really the purpose of this is kind of a good review for students from coming back from geometry or a trigonometry course. So the first thing we kind of remind them of is the Pythagorean Theorem, because up to this point, at least in pre-calculus, we haven't really talked too much about Pythagorean Theorem. So again, just making sure that when we have a right triangle, we have leg and 2 legs, and then we have the hypotenuse. Remember that the hypotenuse is always directly across from the 90-degree angle. The hypotenuse is always larger than the 2 legs. And the Pythagorean Theorem basically just states you're going to square your 2 legs, and that's going to equal to your hypotenuse squared. A lot of commonly referred to as the a squared plus b squared equals c squared, which is a little bit easier to remember than leg squared plus leg squared equals hypotenuse squared. Make sure again that the 2 legs are what make up the 90-degree angle. So most students, don't have a problem with the Pythagorean Theorem, but this is something that we want to be able to do rather quickly in the class. So I do kind of work through just a standard example, and then I gave the students some examples to kind of work through. So in this first one, you can see that we have the 2 legs, and we're trying to find the hypotenuse. So I basically have 2 squared of 2 squared plus 3 squared equals c squared. So again, I kind of work through 2 squared of 2 squared because that's, typically not something that we, it's been a while since maybe students have done that. And from either geometry or algebra 2. So I just kind of work through that so you can see where we get 8. And then really the important thing here is in this context of this problem, you can see that this is a triangle in space. There is no up and down, left or right, right? This is just in space. So even though in our previous chapters, we always did plus or minus, for today's lesson, we don't really need to worry about the plus or minus because C has to be positive, right? The hypotenuse in this case has to be positive. The legs of the triangle are going to be positive. And again, that's because there is no orientation of these triangles. They're just in space. So now let's just go and work through a couple more examples so you can kind of see what's, how to kind of, work through Pythagorean Theorem a little bit quicker. So again, I'll just, treat these 2 side lengths as A and B, and that's C. So therefore we have 3 squared plus 4 squared equals C squared. Well, this becomes 9 plus 16 equals C squared. 25 equals c squared, and that's kind of nice. You can see that c is equal to 5. So here, I don't actually have any radicals. That's kind of interesting and very helpful. Let's do another one here with some 3 radical 3. So we'll have 3 radical 3 squared plus 3 squared equals c squared. So again, basically what we're doing is we're squaring both terms. So we're taking 3 squared, which is 9, and then square root of 3 squared, which is just 3. So 9 times 3 is going to be 27. 27 plus 3 squared, which is going to be 9, equals c squared. And again, in this case, we have 36 equals c squared. So c is equal to 6. So again, in this case, we have a nice little number right there. In the next example here, we have 7 and 1. So again, now this would be 1 squared plus, let's call this b, plus b squared equals 7 squared. So we have 1 plus b squared equals 49. Subtract 1, subtract 1. And now in this case, we have b squared equals 48. Well, when we take the square root of 48, we can do that, but again, we need to make sure that we can simplify the square root of 48, right? We know it's the positive version, but for this unit, we're always going to want to simplify our radicals, but there wasn't anything, yeah. So this radical, square root of 17, we couldn't simplify it, right? But in this one, square root of 48, that's going to be the important thing that we're going to want to do for all of ours here is simplify all these radicals. So we recognize that 16 divides into there 3 times. So therefore, b is equal to 4 times 3. So b equals 4 radical 3. So that is the simplified version of your square root of 48. And then last but not least here, we have square root of 5 and 2. So let's go ahead and do Let's call this one a. So we'll have a squared plus 2 squared equals the square root of 5 squared. So a squared plus 4 equals 5. Subtract 4. And you can see a squared is equal to 1. So therefore a is equal to 1. So not too bad. As far as the problems. And again, eventually we're going to get to the point where we can do most of this just kind of like in our head. And that's kind of the goal that I want to do. So that's why we kind of work through these 4 problems, even though we're not really going to be often tested just on using the Pythagorean theorem. All right. But then we kind of looked into the sides of the triangle. So, when we look at the triangle, we have leg, leg, and hypotenuse. But how can we differentiate between these 2 legs, right? Because the legs are the same, but not always, we don't know if they're the same length, right? So they could be different lengths. So if we want to talk about triangles, like actually talk about triangles, we recognize that those legs are not always the same length. So how can we have a conversation about them as far as their lengths? Well, what we can do is we can do this referring to an angle. So we have this new angle here, which is theta. And hopefully in geometry or another class that you've seen theta. Theta is is part of the Greek alphabet, and it's commonly used for angles, for unknown angles. So the important thing is, if we have theta here, we can actually, instead of calling these legs and legs, we could say, well, this is a leg, that's correct, but it's the leg that's adjacent to my angle theta and the 90-degree angle. So this is what we call their adjacent side. And basically the way that I remember adjacent is it's always in between the angle and the 90-degree. Whereas the opposite is kind of on the opposite end of the triangle. So when we have a triangle and we're referring to theta here, you can see that here's the adjacent side, here's the opposite side. But again, this is really, really important because if I was talking about the triangle where theta was up here, now the adjacent and the opposite side are changed. The hypotenuse doesn't change, right? It's always directly across from the 90-degree angle, and it's always the longest side. So the hypotenuse is not changing. Yet, depending on which angle we're talking about, we're going to refer to these side lengths, these legs, as either the opposite side or the adjacent side. So that is kind of like one of the key distinctions as far as what we're doing. Like previously, we just kind of looked at the side lengths, comparing them, with Pythagorean theorem. But if we can actually get a little bit more detailed in our comparisons, we understand that they are going to depend on which angle we are talking about. Now, how can we actually compare them, or what are the comparisons? Well, those are our 6 trigonometric functions. And I bring this up because, I tell my students, for the longest time, didn't understand the 6 trigonometric functions. I knew what they were. When I was taught this, I was just saying, basically remember SOHCAHTOA. And if you can remember SOHCAHTOA, then you'll be good for your test. And it's like, okay. And that's what you did. You just said opposite over hypotenuse. Like, didn't really make any sense. You just did opposite over hypotenuse. But in reality, this is a ratio. And remember, a ratio is a comparison. And so the way I like to look at this is when I'm looking at sine, that the sine of theta, that's a comparison of the opposite side of the triangle based on the hypotenuse of the triangle. Another way of thinking about it is how big is the opposite side compared to the hypotenuse? Now, when you think about it that way, there's some interesting things that happen. We know that the opposite side is never going to be equal to the hypotenuse, right? So you're never going to have a ratio equal to 1 because the hypotenuse is always larger than any other side. We also know that the ratio is never going to be 0, or at least in this case, right? Because at least for the case of this triangle, so for today's lesson. But that brings up an interesting point as far as when it can be 0, and which we'll learn later. But at least as far as when we look from 0 to 1, you can see that the sign is going to be some decimal, right? If you were to take these fractions and put them in decimal form, you're going to get some decimal between 0 and 1. It's not going to equal 1. And for today's lesson, it doesn't make sense for it to be 0, but we will learn later how it can be 0. But yeah, so that's kind of like interesting as far as understanding these, because these are all they are is comparisons. Sine is opposite of hypotenuse. Cosine is how big is the adjacent side compared to the hypotenuse. Tangent is just the comparison of the opposite over the adjacent. Cosecant, and you guys can notice that that's just the flipped version, right? So when we flip something, if we have these are what we call our reciprocals. Okay, so cosecant is the reciprocal of sine. Secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. Now, the other thing I wanted to mention is, remember, these are functions, right? So there's a couple important things. One, they have an input, and they have an output, right? You plug something in and you get something out. Also, when you plug something in, you're only going to get one thing out, right? One unique item out. So first of all, let's look at what are we plugging in, because it's really important as far as how we say this. This isn't sine equals opposite over hypotenuse. This is the sine of theta equals opposite over hypotenuse. And another really, another way to think about this is the sine, like this is based on this theta. This is exactly what I talked about over here. The opposite over hypotenuse is based on the theta. Like if this is theta, then this is opposite over hypotenuse. If this is theta, then that's opposite over hypotenuse. So it's all dependent on your input variable. And again, we say the sine of, and that's very similar to what we also talked about with the square roots. I bring this up because a lot of students will just they'll write the sine function without an angle, or the cosine function, any of these without the angles. And I say, that makes no sense, because that does not make any sense. Because think about it, if I say the square root of 4 equals 2, you're like, yes, okay, I understand that. But if I say square root equals 2, you're like, that doesn't make any sense, because it's the square root of something, right? You have your argument, your radicand is under the radical. That is what you're taking the square root of. You have to take the trigonometric function of an angle, right? And it's always going to be an angle. Okay, because again, you're comparing the sides based on the angle. So we're always taking our trigonometric functions of our angle. Now, are there other angles that we are going to use? And the question is, yeah, we're going to use theta, beta, alpha, phi, gamma. Like take out the Greek alphabet and we can basically use it. In my class, I like to stick with the theta, beta, and alpha. And also I'll be using those the most often. You'll see in this lesson, those are the angles we're going to use. Sometimes we'll use x and y's as well. Sometimes it gets a little confusing using x and y, so that's why we like to use the theta, beta, and alpha. But these are variables as well, and they can represent your angles. So the main thing I want students to understand is these are functions, and then also that they are comparisons of a triangle, of a triangle based on the angle. Right? So they're functions and they're comparisons. So understanding, those I think is going to give us a good foundation as we kind of move through the lesson. All right. So, one of the questions that we're definitely going to be addressing in the class is evaluating these 6 trigonometric functions. So in this example, did I forget? Oh, yeah. So in this example, we were given 2 side lengths, 3 square root of 2 and square root of 2. And what I asked the students to do was to evaluate the 6 trig functions. Well, we cannot evaluate the 6 trig functions unless we have all of the sides. So the first thing we did was set up the Pythagorean Theorem. So you can see here we have the hypotenuse, and then we have this one leg, and then I say this is A. So I go ahead and solve. I get square root of 16. A is equal to 4. Remember, it's always going to be the positive version of 4. And then what we're going to look at is the trigonometric functions. So again, sine of theta, right? And here's my theta, is going to be the opposite over the hypotenuse. Well, I now have my opposite side, and I now have my hypotenuse. So I'm going to take 4 divided by 3 square root of 2. But now this brings up the point as far as how I want my answers to be provided for my students. So in later chapters, simplifying is going to be very helpful and very important. So for this chapter, even though the basics I want my students to understand is just the ratios, we are going to expect them to be able to put things in simplified form to practice for later chapters. So for simplified form, I just assume everything is going to be in simplified form. That means fractions are reduced, radicals are simplified, and there's no radicals in the denominator. So that is my expectation for this chapter. So to get rid of a radical in the denominator, the students are going to rationalize the denominator, multiply by the square root of 2 on the top and the bottom. Therefore, that produces 4 square root of 2 over 6. I can reduce that fraction to 2 square root of 2 over 3. For cosine, that's going to be adjacent over hypotenuse. You can see how I wrote that up there. And then obviously, applying the division property, those divide out. But again, remember the 3 doesn't go away from the denominator. It still remains there, so it's 1 over 3. And then the tangent, we have opposite over adjacent, rationalize the denominator, 4 divided by 2 simplifies over to 2 square root of 2. So those are your main trigonometric functions. And now let's look into the reciprocal functions. So remember, the reciprocal functions are just the reciprocal, right? They're the flipped version of it. Now, you could always flip the final answer. But again, then you're going to have a radical in the denominator. I'm going to have to rationalize the denominator again. So my advice is to sometimes it's easier to do the final answer. Like here, it's easier to flip 1/3 than it would be to flip this. But for sine, it's going to be easiest just to flip my original ratio. Or again, just use the, hypotenuse over opposite. Done. But here for secant, I don't want to do hypotenuse over adjacent. I already know the final answer is 1/3 for cosine, so secant's going to be 3/1, or just 3. So again, that's kind of comes into those little like looking ahead, seeing what's going to be the easiest way to simplify that. And then we're going to have cotangent, which is the flip version of 4 over square root of 2. So that's going to be square root of 2 over 4. All right, so now we have some angles, and you can see that I have beta over here and alpha over here. And let's go and evaluate the 6 trig functions. So first thing we should be doing is finding our hypotenuse. So let's do 1 squared plus 2 squared equals c squared. So 1 plus 4, that's going to be 5 equals c squared. So c equals the square root of 5. All right, so now I'm going to do the sine of beta. And again, remember, you have to include that sine of beta, right? It makes no sense just to say sine, right? It's the sine of beta is going to be opposite over hypotenuse, 2 over square root of 5. I've kind of forgot I showed you. So I worked through, rationalizing the denominator. I guess I'll probably do it for this lesson here. Because for later lessons, I don't show the rationalizing the denominator. So that's 2 square root of 5 over 5. Let's bring that down because I have more room. All right, so cosine of beta is going to be 1 over the square root of 5. And again, going back to using the rationalizing denominator, and I apologize for those of you that already know about rationalizing the denominator, but I just like to make sure students understand this because, yeah, once I stop writing rationalize the denominator, I start moving a lot quicker. And so I just want to make sure that all students understand why I'm multiplying by the square root of 5 to simplify the answer, and as well as how my answer is being represented. Let's kind of put that up. I just want to make sure that 5 is under the radical. All right, and tangent of b is equal to 2 over 1. It's also important to note that when I'm doing these, I told my students that I always want to see the original ratio as well as the simplified answer, because this is an introductory unit. So therefore, I want them to show me the original ratio and then that they simplified, or how they simplified. Because later, I'm not going to expect that. So cosecant of beta, I'm just going to take the reciprocal here. That's going to be square root of 5 over 2. Secant of beta, that's going to be square root of 5 over 1, so that's square root of 5. And then we have the cotangent of beta, which is just going to be adjacent over hypotenuse, which is 1/2. And there you go. All right, looking at the next example, now we're going to have 2 square root of 5 is the hypotenuse. So that's going to be, let's just call this a. So we'll do a squared plus 4 squared. So 2 square root of 5, so 2 squared is 4, 5 squared is, or square root of 5 squared is 5, so 4 times 5 is 20, equals a squared plus 16 minus 16, and we get 4 equals a squared, so therefore we can say a is equal to 2. All right, and then so our alpha is up here, so again, make sure that now everything's different, right? This side length is no longer the adjacent side, right? If there was an angle down here, we'd call it a different angle, and we would go through the trigonometric functions there. So again, we're dealing with alpha, so we're going to use a sine of alpha. So sine of alpha is opposite over hypotenuse. So that's going to be 2 over 2 radical 5. Again, the 2's are going to divide out, so that's going to be 1 over the square root of 5, right? And then you rationalize the denominator. I'm going to keep the same color this time, to get square root of 5 over 5. Let's move that over. All right, for the cosine of alpha, that's going to be adjacent over hypotenuse. So that's going to be 4 over 2 square root of 5. Again, the 4 divided by 2, that's going to simplify to a 2 over square root of 5. And then you can rationalize the denominator there. So therefore, you're going to get 2 square root of 5 over 5. And then the tangent of alpha is just going to be 2 over 4, which is just equal to 1/2. Okay. So now, again, if we're looking at the reciprocal functions, let's do the cosecant of alpha. That's just a reciprocal here. So that's going to be 2 square root of 5 over 2, which just equals the square root of 5. The secant of alpha is going to be 2 radical 5 over 4. That just gets reduced to square root of 5 over 2. And then the cotangent of alpha is going to be 4 over 2, which is equal to 2. All right, so that's basically it for on that one. Let's go ahead and need to. There we go. All right, now let's go and take a look at this one. I'm going to get rid of the pen style because I'm not going to show that anymore. No, come on. Fit to width. There we go. Okay, so let's go and take a look at these two. So again, now we have x in this upper right-hand triangle. We are given the hypotenuse, so let's go and figure this out. So we're going to have 5 squared equals 1 squared plus, I don't know, b squared. So therefore, in this case, we have 25 equals 1 plus b squared minus 1 minus 1. We have 24 equals b squared. So b is equal to the square root of 24, which we can divide by 4. And so their square root of 24 can be written as 4 times 6. Square root of 4 is 2. So that would be 2 radical 6. All right, so now we have our side lengths. So we're going to do the exact same thing here. So we're going to have the sine of alpha is going to be opposite over hypotenuse. So that's going to be 1/5. Oops, I'm sorry, we're dealing with x, not alpha. So again, make sure you're paying attention to your angle, right? So that's sine of x. Then we have cosine of x is going to be adjacent over hypotenuse. So 2 square root of 6 over 5. Tangent of x is opposite over adjacent. So 1 over 2 radical 6. Now when you're rationalizing the denominator, some students multiply by 2 radical 6 on the top and bottom, which you could do, but it's just multiplying by an extra number. Like you only need to get rid of the radical, so you only need to rationalize by the square root of 6 over the square root of 6. Okay, so therefore it's going to leave me with the square root of 6 over square root of 6 times square root of 6 is 6. 6 times 2 is 12. And again, don't try to simplify. We cannot simplify a number inside of a radical with a number outside of a radical, right? So we're just going to leave that just as it is. And then we can have cosecant of x is just the reciprocal. Secant of x is going to be reciprocal here, which is going to be 5 divided by 2 square root of 6. So again, we're going to rationalize the denominator here. So multiply by the square root of 6 on the top and bottom. That's going to be 5 times the square root of 6. Square root of 6 times square root of 6, that's going to be over 12. And then we'll have the cotangent of x is just the reciprocal here, which is going to be adjacent over opposite. So that's going to be 2 radical 6 over 1, which is 2 radical 6. Okay, last but not least here, we have this one. We have our 2 side lengths and our hypotenuse. So let's go and get this. So we have square root of 3 squared plus 2 squared equals c squared. So 3 plus 4 equals c squared. So that's going to be 7. C equals the square root of 7. All right, so let's do this one last time here. So we have sine of y is equal to, so that's going to be opposite over hypotenuse, so that's square root of 7. So that's going to be square root of 3 over the square root of 7. So a lot of people get confused here, but again, you're just going to rationalize, you're just getting rid of the radical in the denominator. So multiply by the square root of 7 on the top and bottom. And now we can multiply radicals. Like we couldn't divide out when a number is inside of radical and outside of radical, but here we can get this to be square root of 21 over 7. Can't simplify it any further. You can only simplify when they're both under a radical. Let's do cosine of y. That's going to be 2 over the square root of 7. Again, multiply by the square root of 7. multiplied by the square root of 7, 2 radical 7 over 7. Then we have the tangent of y, which is going to be opposite over hypotenuse, or opposite over adjacent, square root of 3 over 2. Let's do the reciprocal functions. Cosecant of y is going to be the square root of 7 over the square root of 3. Rationalize the denominator. Now we're going to have the square root of 21 over 3. Secant of theta, secant of y is just going to be square root of 7 over 2. Yep, square root of 7 over 2. And then last but not least is we are going to have the cotangent of y, which is going to be the reciprocal of this. So that's going to be 2 over radical 3. Rationalize the denominator. 2 radical 3 over 3. Okay, so that's basically when we have a triangle, what we're going to work on. The next thing here is looking at the evaluating a triangle evaluate the 6 trigonometric functions given an equation. So in this case, we're given the 6 trigonometric functions, we're given an equation. So we're saying the sine of theta is equal to square root of 2 over 2. How can we write the rest of the trigonometric functions? So the important thing is when you're given a triangle or when you're given an equation, we need to create a triangle, right? Right now, up to this point, we've only known how to evaluate the 6 trig functions when we are given a triangle or when we have a triangle. So remember, sine represents the opposite over the hypotenuse. So in this case, we're given 2 sides of the triangle, the opposite and the hypotenuse. We just use Pythagorean Theorem here to find the other side length, which in this case ends up being the square root of 2. Now we just evaluate the rest of the 6 trig functions. So we already have sine, that's given to us. We notice the cosine is exactly the same. The tangent, opposite over adjacent, is 1. And then the cosine, cosecant, secant, and cotangent, we just use the reciprocal. So the main thing is when you're given an equation, create a triangle. All right, so in this case, now let's just work through these examples. So again, we have opposite over hypotenuse. So let's just draw the triangle. We have 2 over 3, and therefore let's just call this A. So let's actually do this kind of in our, I did show my work, but let's see. I'll set up the Pythagorean Theorem, and then I'll just kind of work through it. So we have 9. Let's do 3 squared equals A squared plus 2 squared. So 9 equals A squared plus 4. So subtract 4 and then take the square root. So that's going to be the square root of 5. Okay, I'll just do that. 5 equals A squared. So A equals the square root of 5. I'm not going to show my work in there because you can see how it takes up, so much of the space. But let's go and figure out. We can do a couple of these. So, and again, the main important thing is, where was my angle, right? Like you created the triangle, good for you. And did I show it over here? I did. So here I use theta. And obviously, whatever your angle is, that's the angle you're going to use. But where do you put it? Like, do you always put it here? Do you sometimes put it here? Well, again, it depends on how you label your triangle. Like, I drew the triangle like this, but you could have drawn the triangle any way you wanted to, right? And actually, in class, I drew the triangles in different versions. It was a little bit more difficult for me using this software, so I didn't do it like that. But, you could have right triangles that are in all different types of orientations. So wherever your side lengths are, that's fine. Just remember, 2 represents the opposite side. So my angle can't be up here. It has to be down here, all right? For at least in this example, the way that I drew this triangle. And typically, I always like to draw this triangle. You can draw different ones however you want to, but, I like to be consistent. But I will show you, if I want to get crazy and have a little fun, we can rewrite it around. Just make sure that 2 is always the opposite side, right? And 3 is always the hypotenuse. So, all right, so now we already have sine of x, so that one's easy. Let's just write it out there, though. Cosine of x is basically the adjacent over hypotenuse, so that's going to be square root of 5 over 3. And the tangent of x is going to be 2 over the square root of 5. So again, I think I've shown the rationalizing the denominator enough, so I'm just going to start rationalizing the denominator and giving you the answer. So I'm giving you the original, and then I'm giving you the finalized answer once simplifying has occurred. Now let's go and do the reciprocal. So cosecant of x is 3 over 2. Secant of x is going to be 3 over the square root of 5, which can be simplified to 3 radical 5 over 5. And then we have the cotangent of x, which is going to be the square root of 5 over 2. All right, next example. We have tangent of theta equals the square root of 3. Now this one gets confusing because you're like, well, there's only a number. Like, what are the sides of the triangle? Like, what are we going to do if we only have one side of a triangle? But again, remember, all the trigonometric functions are a comparison of one side of a triangle to another. Tangent is the opposite compared to the adjacent. So how can we rewrite the square root of 3 as a ratio, as a fraction? Well, we can always just put it over 1. Therefore, this is the opposite side, and this is the adjacent. Okay, so I don't know. Let's have a little fun. Let's do a right triangle like this. Oops, that's not a right angle. Right, and let's pretend you want to do this. And let's say that's my right angle, and then I'm going to make this, let's put this as my theta. Like, I don't think this is very helpful to do it that way, but maybe you like it this way. I don't know. So therefore, if my opposite side here is going to be the square root of 3, and this is going to be 1. So definitely my triangle is not drawn to scale. But hopefully you at least see how, your side lengths can be anywhere. You go ahead and find them. Or however you want to write them based on the information. So now we just need to figure out what c is. So we'll do c squared equals the square root of 3 squared plus 1 squared. So 3 squared is going to be 9 plus 1. So c squared is equal to 10. C equals the square root of 10. I don't remember that answer. Was that the right one? I hope so. Looks like it. I'm not seeing anything. Oh, I didn't do that right. You're right. Square root of 3 squared is not 9. I was wondering, I was like, why is that different? The common mistake, square root of 3 squared, guys, is square root of 3 times square root of 3, which is 3. Right? So I was like, I don't remember seeing that answer. So that's 3. So that's 4. That means that answer is 2. All right, I can work with 2. That's nice. So let's do sine of theta. Sine is going to be opposite over hypotenuse. So square root of 3 over 2. Cosine of theta is adjacent over hypotenuse, 1/2. Tangent of theta is going to be opposite over adjacent, square root of 3 over 1, which is just square root of 3. Oh, we already knew that. Cosecant of theta is going to be 2 over radical 3. Simplify your answer here. You get 2 radical 3 over 3. Secant of theta is going to be 2 over 1, so that's just 2. And then we can look at the cotangent of theta. That's going to be 1 over the square root of 3, which equals the square root of 3 over 3. Okay? A couple more examples. 2 radical 3 over 3, so it looks pretty confusing, right? It looks like, I don't want to do that one. But again, just like notice this is, this is the hypotenuse, and that is going to be the opposite side. So again, let's just draw a triangle. Let's just draw the basic one here. We have alpha, so I'm going to put alpha there. And therefore the hypotenuse, 2 radical 3, and this is the opposite side. So let's go and figure out what a is. So say a squared plus 3 squared equals 2 radical 3, quantity squared. So a squared plus 9 equals 2 radical 3. So 2 squared is 4. Radical square root of 3 squared is 3. So 4 times 3 is 12. And then subtract 9. I'm not going to show my work. Subtract 9. Therefore, you're going to get a squared is equal to 3. Therefore, a equals the square root of 3. Okay, so now let's just go ahead and simplify them. So the sine of alpha is opposite over hypotenuse. So that's 3 over 2 radical 3. Rationalize the denominator. Let's see here. That's going to give me a 3 radical 3 all over 3 times square root of 3 times square root of 3 is 3. 3 times 2 is 6. So my answer, it's running out of space here. I'll just put this down here. Is going to be, that reduces to 1/2. So therefore, that's going to be square root of 3 over 2. And then we have the cosine of alpha. And that is going to be, cosine of alpha is square root of 3 over hypotenuse. So this is the square root of 3 over 2 radical 3, which is just equal to 1/2. And then we have the tangent of alpha, which is going to be 3 over square root of 3. Rationalize the denominator. You get 3 radical 3 over 3, which is just equal to the square root of 3. Let's see here. We already have cosecant, so I'm just going to rewrite that answer, kind of cheat there. The secant of alpha is going to be hypotenuse over adjacent. So, 2 radical 3 over square root of 3, which equals 2. And then we have the cotangent of alpha, which is just going to be the reciprocal there, which is square root of 3 over 3. Now, hopefully you recognize, and this is one thing I wanted to point out to the students, that these are exactly the same. These answers should be exactly the same, which they are. Obviously, they're not on the same slide, so it might not be as easy for you, but when we looked at them on the board, you can see. So it's important that, I can give you different pieces of information and we could still be talking about the same triangle, right? Now, obviously, I'm not sure these are different triangles, right? Because we have different angles, theta there. But it's just important that, something can look really confusing. But in reality, a lot of the math here, the only difference with this one compared to this example was we had a little bit more simplifying to do. But that was it. But again, the sine, cosine, and tangent were all the same. And that's interesting. That's important for what we're going to be learning here coming up. All right, last but not least here is the cotangent of beta, which is the adjacent over the opposite. So I'll go and draw my triangle here. So we have 4 over 3. So 4 squared plus 3 squared equals c squared. And hopefully you remember we did this at the beginning. 25 equals c squared. So therefore, my hypotenuse is 5. Now the nice thing about this is I don't need to rationalize any more denominators, right? So my beta, here's adjacent, so put that right there. So the sine of beta is 3/5. The cosine of beta equals 4/5. The tangent of beta is 3/4. And then the reciprocals are just, flipped. Cosecant of beta is 5/3. The secant of beta is 5/4. And then we already know the cotangent of beta is 4/3, which was given to us. So when we have a Pythagorean triple, and that's, or when we have triangles with no radicals, you can see how quick and easy and nice it was to do a problem like that. But let's go and investigate why these were the same when we had completely different ratios. And to do that, we had to look at the isosceles right triangle. So when you look at the isosceles right triangle, one thing we notice that the side lengths are the same. So therefore, the two angles have to be the same, right? Because if you have all the angles add up to 90 degrees, and these two, and you have a 90 degree here, and these two angles are the same, then they both have to be 45. When you do the Pythagorean theorem, if you don't know the side lengths here, you have x and you have x, and then let's say you're going to solve for c as the hypotenuse. Well, when you go ahead and solve for c, you recognize that that's going to be x times the square root of 2. So the relationship between an isosceles right triangle is the legs are the same, and the hypotenuse is just multiplied by the square root of 2. And that is what we call our special right triangle, the 45, 45, 90 triangle. So we have x, x, x squared of 2. So this is something that we talked in geometry just to kind of introduce students to it. And, I just want to make sure students, they understand, if I give you the leg, just multiply by the square root of 2 to get to the hypotenuse, right? If I give you the hypotenuse, divide by the square root of 2 to get to the legs. If I give you one leg, you obviously know the other leg is exactly the same. Moving on, so therefore what I did is I said, well, I can find all the missing sides of the triangle if I just give you an angle. If I give you 3 square root of 2, then I know the other leg is 3 square root of 2, and then you just multiply by square root of 2 again to get this hypotenuse. So this is something that could show up, in the class. So I wanted students to make sure they understood that relationship. When you have a 45, 45, 90 degree triangle, life is easy, right? I mean, to find all the side lengths, we don't need to do Pythagorean theorem. We can just use that, understand that relationship. In the same respect, the square root of 7, as the hypotenuse, we're going to divide by the square root of 2, right? So to go from here to here, we multiply by the square root of 2. So to go from, here to here, we're going to divide by the square root of 2. And therefore, you get these two side lengths. So that was kind of the important thing, was just reviewing that just in case, when you have a problem and you see a 45, 45, 90 degree triangle, those relationships exist. But we wanted to bring these up for another part, which was our discussion, which was, what if we found the sine for both of those triangles? And what do we notice? What do we notice about, the sine? So let's look at this triangle. If I take the sine, 3 square root of 2 over 6, that gives me square root of 2 over 2. If I take the sine of 45 degrees here, again, I have this weird, crazy fraction, right? But as I simplify it, you see I get square root of 2 over 2. So I get the same angle, the same triangle. Now, why does that work? Why do I have the sine of 45 degrees equals the sine of 45 degrees? But again, if you kind of step back, I brought this up to my students. I'm like, guys, these are functions. Of course, the sine of 45 degrees is only going to be one number, right? It's like the square root of, not the square root, it's probably not a good answer. Well, I mean, yeah, like when you're just doing the square root of 4, you're only going to get the number 2, right? Because square root, when you're just doing the square root, we're only using the positive version of it. But again, it's a function. There's only one, for your input, there's only going to be one unique output. So of course, the square root of 45 degrees is square root of 2 over 2. Always. I don't care what triangle you use. It's always the square root of 2 over 2. So then we say, well, why is that? And the answer is basically because those triangles are what we call proportional. They are similar triangles. When they have the same angles, and this is something that we talk about in geometry. Let me do this. So when you have like a triangle, all right, come on. Right? So here's a triangle. We have all the side lengths. Well, if I create like another triangle here, these triangles are what we call, they're not congruent, but they are similar. They have the same measures of the angles. And therefore they are similar, and therefore they are proportional. And again, remember, if they are proportional, that means their ratios are equal to each other. And again, what are trigonometric functions? Trigonometric functions are ratios. So of course, these triangles are going to have the sine, when we have 45 degrees, of course, that's going to be the same for the small triangle and the big triangle. So then we bring up to the question is like, well, could we use better numbers? Because, for these side lengths, these numbers don't really look that nice, especially that one. And then we kind of came up to the idea, well, why don't we just use 1, right? And 1's not too bad. Like if you use 1 for the legs, 1, and square root of 2, then you can easily find the square root of 45. You could do the cosine, tangents, everything's usually easier with 1. So we just kind of used that triangle. And I asked this triangle for students to now say, well, why don't we evaluate the 45, 45, 90 triangle using that triangle, right? And I already did the work. Sine of 45 degrees is square root of 2 over 2. So square root of 2 over 2. Well, the cosine, here's put the triangle here so you guys can see it. 1, 1, square root of 2. The cosine is obviously going to be the same as the sine. The tangent is going to equal 1. Cosecant is the reciprocal of that. So we're going to have to rationalize the denominator here. But the secant is going to be the same as that. And then the cotangent also will equal to 1. But I did this because I wanted students to recognize that the sine and cosine are the same for this triangle. The cosecant and secant are the same for this triangle, as well as the tangent and the cotangent are exactly the same. And again, that is because on your 45, 45, 90 triangle, your legs are exactly the same. So it's really just bringing in this relationship of the sine and the cosine being the same. And again, this is something we're going to explore in more depth later in the unit. This is just the first day. Then let's say, well, what about another triangle we could investigate? What about the equilateral triangle? That is when all the side lengths are the same. Now, the problem with the equilateral triangle is we don't have a right angle. So therefore, we create this angle and line bisector right here. So that's going to create our 90-degree angle. So if an equilateral triangle, you have 60, 60, 60. But if I bisect that, that's now going to be a 60, 90, 30. And therefore, if I say, well, I don't know the side length of this triangle, so let's use x. Well, then if I bisect this side, that's going to be x divided by 2. And then let's go and figure out for h. So what I did is I did the Pythagorean Theorem. It's a little bit messy. But hopefully you can kind of see my work here, what I did. X squared over 4, put that to the other side. To subtract x squared minus x squared over 4, I got this to be the same denominator by multiplying by 4 over 4. And then I took the square root. Now, this one kind of gets a little confusing here. But when you take the square root, remember you can separate the square root to the top as well as to the bottom. And you can't take the square root of 3, so that's why that remains. The square root of x squared is x, and the square root of 4 is 2. But rather than leaving it like this, I rewrote it like that, because what that shows us is it's really x over 2 times the square root of 3. So x x divided by 2, and x squared of 3. Now, it's pretty confusing for most students, especially in geometry. So a lot of times in geometry, what we did was we just used this triangle. So instead of having the hypotenuse here as x and then dividing by 2, we did the short leg as x and then we multiplied by 2. And that's usually the easier way to understand it. It's really the same relationship going on. All I did was I multiplied everything by 2. So basically, you take this triangle here and multiply everything by 2. And again, if you multiply everything by 2, all you're doing is dilating the triangle, right? You're not changing the ratios. Like if I have a triangle, like here's my triangle, and then if I multiply it by 2, it's still going to, the sine, cosine, tangent, the ratios are still always going to be the same. So when you multiply everything by 2, you'd get this relationship. And again, obviously, this is kind of turned on its side from there. But again, the important thing is if you have the short leg, you multiply by 2 to get the hypotenuse, you multiply by the square root of 3 to get the long leg. And then again, let's say I give you the hypotenuse, or you want to find the short leg. Well, from the hypotenuse, you divide by 2, and from the long leg, you would divide by the square root of 3. So it's just using those inverse operations. So again, we did the same kind of thing. Said, all right, if I give you, this long leg, how do you find the short leg? Well, again, to go from long leg to short leg, long leg to short leg, you divide by the square root of 3. So we divided by the square root of 3, and we just got 2. To go from short leg to hypotenuse, you just multiply by 2. That's how I got 4. And then we did it over here. Now I'm giving you a hypotenuse. So to go from hypotenuse to short leg, so from here to here, we multiply by 2. To go from here to here, we would divide by 2. And then from here to here, we divided by square root of 3. So to go from here to here, we would multiply by square root of 3. So that's exactly what I did there. And then I asked students the same question. Well, what about the sine of 30 degrees? Is it the same for both triangles? And this time I couldn't trick them. They're like, yeah, it is the same for both triangles. They're both going to be 1/2. This one was a lot easier to simplify than that one was to simplify for 1/2. And then we say, well, is there maybe a better triangle that we could use to evaluate? And we kind of came up with, what about when the short leg is 1? And that looks pretty simple, right? So now let's go ahead and use that as our 30, 60, 90. And again, it doesn't matter which triangle. And that's the important thing that I wanted students to come away from this. It doesn't matter what the triangle is. You could use this triangle. You could use this triangle or this triangle. But the sine, the cosine, the tangent of all of those is always going to be the same. But if you needed to figure this out, just draw a 30, 60, 90 triangle and then let's go with it. So the sine of 30 degrees here is opposite over hypotenuse. So that's 1/2. The cosine of 60 degrees is adjacent over hypotenuse. Secant of 30 degrees is going to be hypotenuse over 30 degrees, so hypotenuse over adjacent. So it's going to be 2 over the square root of 3, which is 2 square root of 3 over 3. The cosecant of 60 degrees is going to be hypotenuse over opposite. The tangent of 30 degrees here is tangent 30 degrees is opposite over adjacent. So that's going to be square root of 3 over 3. And the cotangent of 60 degrees is opposite over adjacent. So in this one, this is something that's kind of interesting. Oops, I'm sorry. So again, in this case, what we have is we have a, in this case, we have a triangle that is, so again, if you remember the 45, 45, 9 triangles, like the sine of 30 was equal to the cosine of 30, right? Or the sine of 45 was equal to the cosine of 45, right? Well, in this case, they're still equal. Sine is still equal with cosine. It's just for different angles of different parts. So if I'm referring to 30 degrees or if I'm referring to 60 degrees. So you can see, again, they still have that relationship. And that's something that's very, very important that, again, we're going to be bringing up. But I just want you to see in this case for the 30, 60, 90, it's not because they have the same angles, because you can notice that that would not make them the same. However, when it's the opposite angle of that triangle, they are still going to provide the correct or similar ratio. And then last but not least, I just wanted to provide students with the Pythagorean triples. Obviously, you can keep on doubling these numbers. If you notice from here to here, I double them. And you could go one more time. You could double that to give you 15, 16, 20. and you could keep on doing that. So these are going to be the Pythagorean triples that we'll most commonly see in my class. And obviously there are infinite many Pythagorean triples, but we're not going to be using a calculator. So therefore we're going to keep things rather simple. But you can kind of continue doing this, and there are plenty more Pythagorean triples. I would just recognize, I told my students basically, these are the ones you're going to see most often. Basically, I will be using all 5 of those at least once in this class. And that was basically it, guys, for our first unit in trigonometry. And then we just basically wanted to see what you understood and what you had a hard time understanding. So if you I made it this far, I would love to hear your feedback, and I look forward to seeing you on the next video. Cheers. Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we're going to work through the angles in trigonometry, which is the second lesson in our trigonometry unit. So again, I'm going to kind of work through my notes that I gave to my students, so therefore we can see the step-by-step solutions to help you with angles in trigonometry. So let's go ahead and get started. What you're going to learn, basically what we're going to cover in this lesson is we're going to learn how to label and graph angles in trigonometry. We're going to make sure we can find different types of angles, as well as how to convert between angles in trigonometry. So, first of all, I just wanted to kind of remind students, some basic operations that we apply in with our angles. And this is something that, might pop up, throughout the lesson or next couple chapters. But in geometry, we talked about finding the complement and the supplement. And the complement are angles that are complementary, remember, add up to 90 degrees. So if I wanted to find the complement of an angle, I'm just going to subtract that angle from 90 degrees, and therefore I get 53. Therefore, 53 and 37 are complementary angles. Supplementary angles are angles that add to give you 180 degrees. So again, you just take 180, subtract 37, and you can see that 143 is going to be the supplement of 37 degrees. Now, so far, up to this point, mostly, in geometry and what we've covered so far, negative angles don't make any sense. So therefore, 90 minus 111, you see is going to be a negative 21 degrees. But we're not going to include negative angles as complementary angles. So that's kind of, taken away back from previous definitions we used, as well as the context of angles that we've previously used. However, I can subtract 111 degrees from 180 to go ahead and get the supplement, which would be 69 degrees. All right, so that kind of brings us up to our first definition, which is really just kind of like the measurement of degrees, and really like an angle. And I kind of talked about this as like the vocabulary word really of an angle. The angle is really going to be the measure of rotation between two rays set at a vertex. We've also talked about angles that basically, being between two sides of a triangle or any kind of really polygon that we have. But the important thing, what I asked the students to do is I said, go ahead and graph 30 degrees. And most students graph 30 degrees like this, or they graph 30 degrees like that. But in reality, these 30 degrees are in space. There is no orientation. There is no expectation of how we should graph 30 degrees. Some people could do 30 degrees like this, or, you could do 30 degrees really any different way. You could even created another polygon, some regular polygon and represented that with 30 degrees. So we didn't have any really standardized process. The one thing I wanted to bring to students is, one, why do we use 360 degrees to represent the rotation of a circle? And then really, what is that unit measurement of a degree? And really, just a degree is going to be, 1/360th of a revolution around a circle. That's basically our measurement of a degree. So I kind of went a little bit into the, the backstory, or at least the understanding of using 360 rather than using any other random number we could have. But the short form is basically 360 is a really nice number. It can be divided very nicely, evenly into that case. And again, I am not a history thing, but as far as I remember looking up, it very much circles that the, 365 days in the year, 360 is very close to that. And we know that that is going to be, the same thing kind of orbiting in the sun. Think of it as a circular day. But 360 is a lot better is a lot more divisible than 365. So therefore, that was just kind of the accepted use for the rotation of a circle. All right, but the problem is, again, we don't really have a way to differentiate between how we want 30 degrees. If I say 30 degrees, everybody's going to draw 30 degrees differently. So therefore, that's when we came up to standard form. Now, standard form is very important, not only because we're all going to be graphing our angles the exact same way for this chapter, but also it brings in direction of rotation. Because up to this point, 30 degrees was 30 degrees. It was just a measurement of rotation. There was no arrows there, right? Didn't matter if you went from here to here or from here to here. You know, we didn't care what the direction of rotation was within a triangle. However, in standard form, you can see we have an initial side and we have a terminal side, and we always rotate from initial to terminal. When we are rotating in the counterclockwise direction, that is considered positive, and when we are rotating in the clockwise direction, that is considered negative. So the initial side is always going to be on the positive version of the x-axis, and then the terminal side is just going to be the final side that we have. And so just kind of notice here that I always start here, and then I have an arrow which represents my rotation. So now that we're including orientation, we have this positive and negative, but there's some things we should also take away from 360 degrees. So obviously, if all the way around, if we're just going to accept degrees as 360, well, then we know half of that is 180, which also produces the straight angle, which hopefully we're familiar with. And then half of that would be 90 degrees, right? Which is the right angle. So then we just kind of count, well, if that's 90, that's 180, that's 270. So just kind of understanding those angles is important. Again, under the assumption that we're going to accept 360. But I really kind of press the students as far as like, is there maybe something better than degrees, right? I mean, again, it is just this arbitrary number that is very easily divisible. It kind of makes sense to like the orbit of the Earth around the sun, and it's close, but it's really not exact. It doesn't really make sense. It just kind of seems like a made-up number that works really well. So that's when I press them. Well, what about a radian? And so the way that I kind of teach radians is I basically label them. I basically label the radius of any circle, and I kind of treat that as like a hard spaghetti noodle. And basically, obviously, we cannot move that or it's going to break, right? We can't bend it or shape it. However, if we take that spaghetti noodle, put it in like some hot boiling water for a couple minutes, then we can start to, it's malleable. We can start wrapping around the circle. And what happens is if we wrap it around the circle here, well, if we were to rotate a ray, that rotation with the radius around that, like the circumference there, that would measure 1 radian. And that's what we call a angle degree of 1 radian. If we do it, go ahead and twice, that would be 2 radians. And if we did it 3 times, that would be 3 radians. Now, the interesting thing is, if we, it looks like it's really, really close to being 3 radians halfway around a circle. And I said, wouldn't it be perfectly great, amazing, if it was exactly 3 radiuses that could wrap around halfway of a circle? And it would be great if that worked out. And you can see, unfortunately, though, it's close, but it's just not there. And that little decimal extra ends up being 0.14159, ... repeating on and on and on forever. And therefore better known as pi. So I prefer, pi. I like the understanding of pi is basically the number of radiuses it takes to wrap around the circle. I mean, yes, circumference over diameter or any other definition that you've used for pi, works, but I just like it. It's basically taking the radius and wrap around the circle. There's 159 radiuses that you can wrap around the circle. This also brings up another important point as far as the radian. This just seems nice and easy, like 1 radian, 2 radians, 3 radians, and pi. So we can have an angle measure in just standard numbers, or we can also refer to radians, which is going to be more common in terms of pi. So therefore, if we know halfway around a circle is pi, all the way around the circle is 2 pi. Now we can do a quick little conversion. I kind of, prepare students that yes, pi is equal to 180 and 2 pi is equal to 360. So therefore we can convert between radians and degrees and between degrees and radians. But we have to be careful. I told students, a lot of students do not like radians, like, this is something new I have to learn. So maybe I'll just convert every single time I have radians into degrees. And I said, if you do that, you're never going to finish a test in my class because it's just going to take too long. 9 out of 10 problems that we'll probably be doing, on tests and quizzes are going to be in radian form. So you're going to want to make sure that you are comfortable with radians as much as you are with degrees, which up to this point, you're definitely more comfortable with degrees than radians. So to convert, we have this conversion ratio. Because basically we know that pi is to 180 and 180 degrees is to pi. Now, a lot of students have trouble with this. So I just remind them, well, look at your other classes when you guys have done conversion ratios. If I wanted to convert 7 inches to feet, what I would do is I'd multiply it by the conversion ratio of 1 foot is to 12 inches. And, right, because we know that 1 foot, at least for the standard American system, 1 foot is equal to 12 inches. They are the same measurement, just different units. But when I multiply 7 inches by 1 foot over 12 inches, again, since this is the same measurement divided by itself, I'm not changing the fraction. But the reason why I'm using this conversion ratio is because I'm going to be changing the units. The inches now divide out, and I'm left with 7 times 1 times, foot. Oh, I'm sorry. 7 times 1 divided by 12, which gives me 7/12 inches. So therefore, you could say that 7 inches is equal to 7/12 of a foot, which I wrote down here incorrectly. It's not inches. The inches divide out, so that's feet. However, if I wanted to figure out how many inches makes up 7 feet, well, now I'm going to multiply by the conversion ratio of 12 inches over 1 foot. And here you can see that the feet divide out, and therefore divide out to 1. And therefore I'm just left with 7 times 12 inches, which ends up being 84 inches. So we've used the conversion ratios for different units of measure. And again, it works, for the metric and everything else. But so that's what we're going to be doing here, because pi is equal to 180. They are the same measurement. They're just in different units. So let's go ahead and, how are we going to convert radians and degrees? And basically what we can do, well, all we're simply going to be doing is multiplying by the conversion ratio. So if you have degrees and you want to convert that to radians, then just multiply by pi over 180. And there's a couple different ways you could do it. You could multiply all the way across and then simplify. Or since everything is separated by multiplication, you can just simplify from there and you're going to get the same answer. The one thing I tell students is, typically if you remember from our unit in rational expressions, it was easier to simplify, apply operations, and then simplify again. So while sometimes students just like to multiply and then simplify, and that works, sometimes they'll get caught up though. So I'd always advise them to look to simplify first. For instance, same thing. Whenever I have radians over here, and I want to, real quick. When I convert this, I get negative 5/6 pi. And again, negative 5/6 pi is really the same thing as negative 5 pi divided by 6. But this is going to be the more common term that we're going to use when we're representing our angles in terms of pi. Over here, so now I have 2 pi over 3. Well, again, if I want to convert from radians to degrees, I want the pi's to divide out, right? So that's why I'm going to use the conversion ratio, 180 degrees over pi. And really, the trick is here I wanted degrees divide out, so I had the degree in the denominator. Like whatever you wanted to have divide out, whatever unit you want it to be, go away with, just make sure that, unit in your conversion ratio is in the denominator of your conversion ratio. And then, you can see how the pi's divide out and the degrees divide out. So again, you could multiply everything across and simplify, or you could just simplify before. 3 goes into 180 60 times, the pi's divide out, and then 2 times 60 degrees is 120. So that's basically the general concept. I think it's important sometimes students, when we want to be able to convert, just to make sure we understand that, they are the same measurement, but we can convert them between the two. So it's not always the best use of our time to be able to do that, but I wanted to make sure students feel comfortable. So let's just go ahead and work through a couple examples here. So if I wanted to convert 240 degrees, again, I want to get rid of the degrees, so I'm just going to multiply by pi over 180. Now here I have 240 degrees divided by 180. The zeros can divide out. That's like dividing 10 on the top and bottom. And then basically I have the fraction 24 over 18. Well, I know that, 6 divides into 24 4 times. And 6 divides into 18 3 times. So therefore this gives me a fraction of 4 pi over 3. Okay, so you can just kind of see how you're reducing your fraction. And that's really like the main issue that students are going to have here is one, choosing the right conversion ratio, but I think with a little practice, you'll get to it. And then really the second issue comes up from students that are just the simplifying fractions. So the next one with the negative. Negative is really not going to impact anything. We're just going to, again, still multiply by 180. So my degrees multiplier, now in this case, I don't really have anything. This one's kind of a little confusing, right? This one was nice to simplify. This one's like not as easy. So what I'm going to do is I'm just going to write this as one fraction and kind of think about this. Degrees pi, oops, degrees divide out. So negative 140 degrees pi over 180. Now you could divide by 5 on the top and bottom, right? But again, like I already think like 45 is half of 90, right? So therefore, I could divide 45 in the top and I could divide 45 in the bottom. Well, 45 goes into the numerator one time and 45 goes into 180, like 45 plus 45 is 90, right? And then times that by 2. So therefore you can see this is going to be a negative pi over 4. And again, like later in this lesson, you'll be able to, a lot of these we're going to be converting them very, very kind of quickly anyways. For the next one, 400 degrees. So in this case, again, we're going to be multiplying by the same conversion ratio. Okay, again, we can have zeros divide out, and now we're left with 40 over 18. I don't know a number off the top of my head, but it looks like I can divide the top and bottom by 2. So that would be 20 pi over 9, and that can no longer be simplified. Okay, so some of them are definitely going to simplify. Some of them, is not going to be as easy as other ones, and then you could have ones that would just simplify once, but, that's going to be it from there. The next one is -3. Now this one's kind of confusing for a lot of students because they immediately think they see a number not in terms of radians, so they think, oh, it has to be a degree. But again, if you don't have that degree symbol, it's not in degrees, it's in radians. So therefore, we need to multiply this by our other conversion ratio, 180 degrees over pi. Now, there's really nothing I can simplify here, right? I'm going to be multiplying -3 times 180 times pi. So negative 180 times 2 would be 360 times, plus 180 one more would be 540. So this is a really weird answer. 540 degrees. Pi still remains in the denominator. And that's just going to be in degrees. Now, again, when would you really ever need to do something like this? Probably not very often. But it's just used to make sure you understand that this is a radian, right? Not a degree. And therefore you can have an angle in terms of pi. It's kind of weird, but in this case, it works. All right, so for the next two examples, you can see they're definitely radians because they're in terms of pi. So I'm going to multiply them by the same conversion ratio, 180 degrees over pi. And again, rather than multiplying everything across, I can see that the pi's divide out. 6 divides into 6 one times. 6 divides into, 18 3 times, so it's going to divide into 180 30 times. So therefore, that is going to be 30 degrees. Actually, let's keep that. We already have the degree there, so you can see that would be 30 degrees. All right, and again, we have another negative angle, but again, hopefully you'll recognize that the negative angle really doesn't matter. It's just going to make the negative angle negative at the end. So again, let's multiply by 180 degrees divided by 5. And again, you can see like this 5 is not really as nice. You could multiply this by 3. And again, my students are not going to have a calculator. So it really kind of comes into, them being able to kind of check your work. And that's what I'd kind of also just, make sure with students is like, divide this in there. Like you can just do the work to the side if you need to. What am I doing by pi? Okay, so the pi's divide out. Here I'm going to divide 180 into 5 into 180. And, so again, you could do like 5. How many times does it divide into 180? Well, 5 goes into 18. Again, if you get like stuck on this, 3 times 5 is 15. Subtract the rows, right? If you remember, we did this long division in the last chapter. 5 goes into 30 6 times. Oh, okay, so that goes in there 36 times. So that's a -3 times 36 degrees. Well, 36 times 2 is 72, so therefore that gives you a -108 degrees. Okay, so if you don't have the answer up at the end, don't be afraid of doing just some basic little math here on the side. Until we're given a calculator, then obviously we can take advantage of technology. All right, so now that we have the basic conversions, we're not going to want to convert these to radians, but let's go ahead and just practice sketching in standard form. So what I did with the students is I said if we're going to sketch 400 degrees, remember that all the way around the circle here is 360, right? So if all the way around the circle is, here's 0, here's 360, right? We know all the way around the circle is 360. So then to get to 400, how much farther do I need to go? Well, that's just 40 more degrees, right? So, obviously we know like 90 here, half of 90 is 45. So it's going to be somewhere in between. And I told students, I'm not the graphing police. This should be somewhere. It's definitely need to have the quadrant right when you're graphing. You need to make sure that you're showing the whole rotation, not just showing, that angle. And it should be relatively in the middle. It should not be very close to an x, to the x or the y axis, and therefore you're going to be perfectly fine there. But again, just making sure that show the rotation in the positive form, as well as showing the arrow, which is showing the direction of rotation. Negative 9 degrees, we know that's going to be a right angle, but again, negative just tells us we're going to go in the opposite direction, right? Because we know 90 degrees is right there, so negative 9 degrees is going in the opposite direction. Again, noticing that arrow and the use of rotation. Again, noticing my initial side is always going to be starting there. From here, we can just kind of work through some other examples. So let's just kind of work through these now. So 30 degrees is just going to be a nice one, positive. That's not going to be very big. So start on our initial side. Let's go from there. We'll say there's 30 degrees. 157 is not an angle that probably many of us graph very often. So again, I think it's just kind of important to know that, from standard form, that's 180, and that's 90 degrees. So 157 is just going to be somewhere in this second quadrant, right? A little bit closer to 180 than to 90. So we'll just kind of do something like that. And again, you can see that for all these angles, I'm not just graphing the angle, but I'm also graphing the terminal side. The same kind of idea can be applied for 225 degrees. So 225 degrees, so if this is 180, and if you remember, I originally just added 90 again, right? So here's 90, here's 180, this would be 270 degrees. So 225 degrees is going to be somewhere in between, probably a little bit closer over here, or maybe it looks like actually pretty much right in the middle, right? But again, it's roughly in there. You can see now how that represents the angle. And then we have a nice little negative one, and we know all the way around the circle is 360. So in the negative direction, it's just going to be all the way around the circle. And you can see there is negative 360. All right, so now let's get into the fun ones, graphing a good old radian. So what I showed students when we're graphing radians, there's really this main concept that I want all students to be able to understand. And that is that halfway around a circle represents pi radians. Okay, so if we can understand that halfway around a circle represents pi radians, then we are going to have the fundamental understanding, because we can basically work from there. So if we have, here's pi, right? So that means if I wanted to graph pi halves, that's really half of pi, right? So 1/2 pi. And you can see that's the same thing as 90 degrees. I don't like to convert or talk about 90 degrees. I want to keep everything in radians. But you can see, here's pi, so half of it is going to be right up there. And again, we don't really write it as 1/2 pi, we write it as pi halves. But you can see how that kind of makes sense. And the other thing is, if we're taking pi, if I wanted to break pi into halves, then, you can see it's already broken down in pi. So you can see how this is pi halves. Now again, kind of following this understanding here, if this is pi halves, right? If that's pi halves, that means this is going to be 2 pi halves. Here is going to be 3 pi halves, and all the way around the circle is going to be 4 pi halves. So you can see how, if we have, pi halves is what we call our unit of measurement, our counting unit. Pi halves, 2 pi halves, 3 pi halves, 4 pi halves. And again, remember, this is equal to pi. This is equal to 2 pi. Okay, so the measurements are the same. We're just counting them now in terms of halves. And that's why I should actually break that down into halves. Okay. So now let's go ahead and just practice sketching on the axes, or sketching within halves. Oh, I was going to move that one around. Okay. So on the first one, again, as we kind of talked about, if this is pi halves, if that's pi halves, this would be 2 pi halves, and that'd be 3 pi halves. So you're really just counting your way around, pi halves, 2 pi halves, 3 pi halves. As far as negative 2 pi, again, that's kind of the same one that we already discussed here. So that's going to be all the way around in the negative direction. Here we have negative pi halves, so that's just going to be down there. Like again, this is positive pi halves, so negative pi halves is going to be down in that direction. And then we have one that's a little bit larger than pi, so we know all the way around circle is 3 pi, and then we just need to go one more pi, which is again half that revolution there. All right, so again, that's basically all we want to do. Notice how my angles, again, all start on the positive x-axis, and they all have a terminal side where they're ending. In this case, it's all on an x or a y-axis. And they also have arrows showing your rotation or direction of rotation. So now let's get into a little bit more of the fun ones, which would be sketching the fourths. Oh, I guess did I do this? Yeah. I guess actually that's what I meant to do. Yeah, well. So there's my angle, pi halves right there. Okay. Actually, you know what? I'm going to fix that. Let's do this as 2 pi halves, 3 pi halves, and then this one, which would be 4 pi halves. 2 pi, and then this is equal to pi. Therefore, my angle, I'm just going to like redraw this because I already had that up there. But I want to draw the angle just nice and pretty. So now, just the angle pi halves is right there. Okay, so now let's go and look into the fourths. So basically, on the fourths, we're again going through the same basic understanding. Here is pi. Well, now I can break pi into 4 equal parts, right? So I break in pi, and you can break it into 4 equal parts. So this is pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. And that's really important because in the same respect, all the way around the circle is 8 pi over 4. Now, we only need to get to 3 pi over 4, which thankfully is already drawn for us. So, you can see 3 pi over 4, so that's just going to be pi over 4 short here. Oops, so let's just go. So you can see 3 pi over 4 is this angle right here. So I'm just going to redraw it down there, 3 pi over 4. But it's basically this understanding, again, of taking pi and then breaking it up into 4 equal sections, right? It's like taking that candy bar and cutting it to however many sections that you want. So understanding that, now let's just go ahead and work in through a couple more examples, which, wow, I have 3 of them that are negative. So maybe I changed one of those. I don't know why I did that. All right, so let's do negative pi over 4. So again, that is going to be, you can count it. Like if you want to break it down if you like to and break it down into fours. But again, you can just see that negative pi over 4 is just going to be that angle right there. Negative 7 pi over 4. Now this one is, again, a lot of students like to count these up. So you can break a fourths here, break a fourths there. So 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4. So you can say it's almost, no. So you can see it was almost all the way around, right? And again, like all the way around circle we know is 8 pi. So if you're at 7 pi over 4, that means you're just going to be pi over 4 short of a revolution of a circle. And again, notice this is negative, so therefore that's why we're going around in the negative direction. As far as negative 9 pi over 4, I think let's just make that a positive. That's what I'll do here. I'm just going to raise. I'm not sure if I missed that or what. So I'm just going to make that a negative and pretend we never saw that. Okay, so 9 pi over 4. Again, kind of going through this understanding. If we know that all the way around the circle, that was... Maybe I'll make that, because that was the one I did in class, was the negative 9 pi over 4. That's all right. Dang it. Okay. I'm going to change this one. Sorry. I thought I recognized this, but I guess I didn't. So I'm going to change this one to a positive. I only really need 2 negatives, so I'm not sure why I did 3 negatives. Kind of weird. Okay, same idea, but now we're just going to go down in this direction again, pi over 4 short. Right, so force, 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 and then you can see that my angle here is just going to be pi over 4 short. Now, negative 9 pi over 4, again, is going to be going in the negative direction. We know all the way around circle is negative 8 pi over 4, so I just need to go one more pi over 4. And you can see, therefore, that is going to be my angle negative pi over 4. So it's going to be larger than a revolution, down an extra pi over 4. For the next one, we have 5 pi over 4. So again, breaking this down, like if we know that halfway around a circle is 4 pi over 4, we just need to go an extra pi over 4. So again, you can see that like obviously breaking it down into fourths is helpful, especially when you want to count and like make sure you're doing it right. But again, once you kind of understand that like half of a circle is 4 pi over 4 and all the way around the circle is 8 pi over 4, then you can just basically kind of use those as your kind of like, foundation and just kind of work from there. All right, so now let's go and get into thirds. Now, when dealing with thirds, I don't really like having this axis here, but again, it's like the same thing, right? You're just taking this and breaking it down into 3 equal parts, right? So if here's pi, you can break pi into 3 equal sections. So negative 4 pi over 3. Sometimes when I like to do negative 4 pi over 3, I like students to understand, 3 pi over 3. So if here's 3 pi over 3, that means 4 pi over 3 is going to be down here, right? If here's 3 pi over 3, and then 4 pi over 3, 5 pi over 3, 6 pi over 3, right? Did I change that to 4 pi? Let's change that to 4 pi over 4. Okay, so that's 3 pi over 3, 6 pi over 3. So therefore, if I was going to do 4 pi over 3, again, that's just going to be this angle here. And again, like sometimes if you get confused with the negatives, I just like students to think of like, just imagine what would be the negative version. Like it's the exact same angle, it's just in the negative rotation, right? So negative 4 pi over 3 is the exact same angle, just in the opposite direction. Okay, so you can see the difference. Like they have the same measure, they're just in opposite directions of each other. All right, so let's go ahead and do sketch 5 pi over 3. Again, if we, like here, you could break this up into thirds. Again, having the x-axis there, it gets confusing. But again, so let's actually delete it. So you could just count, 1/3, 2/3, 3/3, 4/3, 5/3. And you can see that is going to be your angle. Here, we're going to do negative direction. We know halfway around circle would be 3 pi over 3 in the negative direction. So negative 2 pi over 3 is just going to be 2/3, right? So 1/3, 2/3. Now, here's where we get to a little bit of fun with 10 pi over 3, because I think when students start to like count, they recognize, wow, counting works, but it's just not very fun. Like, I'm going to count it just so you guys can see what happens here. So 1/3, 2/3, 3/3, 4/3, 5/3, 6/3, 7/3, 8/3, 9/3, 10/3. All right, so we found the angle, and that's the angle. It has like an extra revolution and going and then down in the third quadrant. But the reason why I represent that is when we did this rotation, it was like an extra rotation. We didn't really need to graph around a rotation just to find the terminal side. So what I show students is, we know in terms of thirds, 2 pi is equal to 6 pi over 3, right? That is what we learned up here. 2 pi is equal to 6 pi over 3. So I could also rewrite this as 6 pi over 3 plus 4 pi over 3. Now, we can't discredit that the 6 pi over 3 exists, but it's a little bit easier to understand that when I want to graph this, 6 pi over 3 is a revolution. I can graph that very easily. Wrap it around the circle, right? Then now I'm just graphing 4 pi over 3. So I know 3 pi over 3 is halfway around a circle, and then it's just an extra third. So now I can just graph from there. So it's with this understanding that, using these extra revolutions, which we call using period as an aid, you can quickly and easily graph these if you can break them down like that. Here's another example where it's going to be larger than 2 pi. But again, this one isn't too bad. Like it's only a pi greater, right? Because we know that like 6 pi over 3, right? So we have here is going to be, now this one is a little bit different though. You can write this as negative 6 pi over 3 plus a negative pi over 3. Because again, like direction matters, right? So here's negative 6 pi over 3. Same thing, a revolution just in the negative direction. And then you're adding one more negative pi over 3. So therefore, that would be our angle down there. Okay? All right, and then it brings us to lovely 6. So let's do this as 6 pi over 6. And therefore, all the way around the circle is 12 pi over 6. So the nice thing about at least doing with 6 is you're basically taking the thirds and you're breaking them up one more time. So there's pi, here is thirds. And again, you don't really need to be perfect here, but you can see how we can break this up into 6 equal parts. So again, understanding 6 pi over 3, I'm going to want to use the period of an aid. Again, we notice that halfway around the circle here is 12 pi over 6. So therefore, I know that this is larger than a revolution. And it's only going to be larger than a revolution of pi over 6. So I'm just going to do a nice little revolution, and then I'm going to add, come on. I'm going to do a nice little revolution, and then just go extra pi over 6. And there you go. All right, so let's go ahead and work through these last examples. Pi over 6 is fairly basic enough. You're just going to really estimate there, pi over 6. Here we have negative 5 pi over 6. Again, halfway around circle is 6 pi over 6 in the negative direction. So we're just going to be pi over 6 away, like short. There you go. Next one, we have negative 11 pi over 6. Again, all the way around the circle is 12 pi over 6. So all the way around the circle is 12 pi over 6. So therefore, again, we're going to be pi over 6 short. But again, just remember this is a negative angle. And then last but not least, guys, we have 17 pi over 6. Again, if I use period as an aid, that's going to be 12 pi over 6 plus 5 pi over 6. So again, let's go ahead and sketch this real quick. So 12 pi over 6, got that done real quick. And then 5 pi over 6, halfway around the circle is 6 pi over 6, so we're pi over 6 short. That angle is going to look just like that. Okay, so now let's get into one of the more important definitions that I want students to understand for this chapter, which is the reference angle. So this is going to be something that we're going to be using every single day from now on. And really the reference angle is fairly basic, but students get it confused all the time. The reference angle, which we concern as theta prime, is just the acute angle between the terminal side of an angle and the x-axis. Main thing is reference angles are always positive and they're always acute. So if you're writing the reference angle and it's not positive and it's not acute, then it's wrong. So the important thing is, notice how my angles are in red, right? We could call our angles theta, for whatever case. But again, like angles have directions in standard form. Reference angles do not have direction. Notice how there's no arrows in the reference angle. They just measure the distance from the terminal side to the x-axis. So it doesn't matter if I'm going this way or if I'm going that way. Like it's just the measure of from the terminal side to the x-axis. Also notice that they are always acute. Remember, acute means they have to be larger than 0 and less than 90. They can't be equal to 0 and they can't be equal to 90. So, again, if you have an angle that lies on an axis, then there's going to be no reference angle. Now, there are a lot of formulas, and I used to teach the formulas, but then I was like, just use common sense. So that's what I'm going to do when I go through these. Is basically you ask yourself, how far is the angle away from the x-axis? Sometimes, and basically you're just going to be using subtraction and finding the difference of two angles. And how, depending on which quadrant you're in, you're going to do that differently. So I will go ahead and explain. So in the first example, we have 2 pi over 3. Now again, we know halfway around a circle is 3 pi over 3, right? So if I just traveled 2 pi over 3, how much farther do I need to go to get to 3 pi over 3? And the answer is just pi over 3, right? Because 2 pi over 3 plus pi over 3 is 3 pi over 3. Or as far as the subtraction goes, 3 pi over 3 minus 2 pi over 3 gives you that reference angle, which is pi over 3. Now again, easily get tricked up here is once we see these negative angles. Once we see these negative angles, students automatically want to go ahead and graph negative 9 pi or see a negative angle, and they say, oh, the reference angle must be negative. But no, it's not. Like when you graph negative 9 pi over 4, Again, like all the way around the circle is 8 pi over 4, and then you're just going pi over 4 more, right? So therefore, how far did you travel? From the x-axis, how far did you travel to this terminal side? Well, the answer is just pi over 4, right? That is that absolute distance that you traveled. It doesn't matter if the angle is negative, doesn't matter if you're traveling back to the x-axis or in the negative direction, you still just traveled pi over 4. That is the reference angle. So, therefore, let's just go ahead and work through a couple of examples here. I should have done 3, 5 over 3. Well, yeah, that's all right. Okay, so the first example is 5 pi over 4. And when we go ahead and do 5 pi over 4, so we can graph 5, come on. So a lot of times when I'm finding the reference angle, I just like to go ahead and just draw the angle just to kind of get used to it again. And therefore, that's the reference angle. So halfway around the circle is 4 pi over 4. I went an extra pi over 4, so therefore theta prime is pi over 4. For B, I'm doing a degrees, 360. Well, I know all the way around the circle is 360, but my angle is 361 degrees, which is just one little unit over, right? So in this case, how far am I away from the x-axis? I am just 1 degree. So the reference angle is, again, it's cute and it's positive. Here I have negative 2 pi over 7. And it's like, whoa, we never dealt with sevenths. And again, one thing actually I forgot to mention here is, a lot of times what I do with students is I said, hey, like we did sixths. Like, should we do 12ths? Like eighths? 24ths? 36? Like, what is the next number? And again, you could really do any number. It doesn't, like, these are the numbers that we use for a specific reason, and you'll see why coming up in the later units. But yeah, we can break up a triangle any way, like we can break up a candy bar any way that you want to. Hey, if you take take that circle and you break it up into 180 parts, then you'd have a degree. Like pi over 180, you would have, obviously you can see that's the conversion ratio, that creates your degrees. But anyways, let's go back to where we're at. So my point to bringing up that is we have negative 2 pi over 7. So let's actually graph that. So we know that halfway around circle here is negative 7 pi over 7. Now you could go ahead and sketch this as well. You haven't tried to identify like 7 equal parts, which is kind of weird. But again, we know that half of that, like half of 7 is 3.5 sevenths. Right? Now again, you don't need to graph this at all. But I think it's just important to kind of know where this angle is. Negative 2 pi over 7 is still going to be in this fourth quadrant. Okay? It's going to be down here, and you can see that how far is it away. If I just traveled 2 pi over 7 away, then my reference angle, theta prime, is going to be 2 pi over 7. So it's going to be the exact same angle. It's going to be the exact same angle that than my original angle. And also, notice this one. I also could have written this as 360 degrees plus 1 degree. Right? So we have this extra revolution. But again, when you have an angle that lies in the first quadrant, or the terminal side, it's just going to be that same angle. Like that's an extra revolution. You can see that those are going to be the same. All right, and then last but not least here, we have 5 pi over 6. So again, if all the way around the circle is 6 pi over 6, and I only traveled 5 pi over 6, that means my reference angle is going to be pi over 6. Okay, so we'll talk about how to use these later. It's really just the idea for students to be able to identify the reference angle in each part. But now it's going to bring us up into our last definition, which is coterminal angles. And the definition of coterminal angles is actually even easier than reference angles, but it's more difficult for students to comprehend. And you'll see once we kind of start talking about this. But coterminal angles are basically just angles that have the same initial and terminal side. So you can see all of these angles here all start on the positive x-axis, and they all end on that terminal side, which hopefully is supposed to be the same, right? Or you can see is the same. Now again, it doesn't matter the direction, right? You can go in the positive direction, you can go in the negative direction. You can go around the circle, you can go around a circle. And like, that's the important thing that you understand. Like, if I could keep on going around the circle, then there's infinite many coterminal angles. And the answer is yes. So the reason why this gets confusing is because since there's infinite coterminal angles, you're going to have the way that the questions are asked are going to be directed, certain ways. Like one, thing I might say, find the smallest positive and negative coterminal angles. So therefore, I'm looking for specific, two angles. Or, you could have a multiple choice question and it says, which of these angles is not coterminal? So that's why the graphical approach is nice, but it's really like understanding, well, how do I, understand this? And the way that I kind of explained to my students was like running around a track. All right. It's kind of weird, but let's pretend you wanted to come with me and run around the track, like at a gym, outside around the football field, we have, the tracks. So my point was like, what if, well, it's kind of weird actually in this example. It made sense in all these examples, the way I was teaching my students, but let's pretend that you wanted to go ahead and run with me, right? And like here I start and then I stop here before I meet you. Now, if we want to run again, but we want to stop, like come back to the same direction, like how far are we going to run? Let's use a green. So here I'm running by myself, right? And then you meet with me and you say, hey, let's run a lap around the circle, right? So if we run a lap around the circle again, you can see that we're back to where we started. So really that question is, how far did we run together, right? Now, obviously I ran a little bit before you showed up and then we ran together. But from when you showed up to when we stopped running, we're back at where we started, right? We went around the whole track together. So how big is that green? So that's why you can see I'm going to do the green as 2 pi or 360. So we could say plus or minus 2 pi or plus or minus 360 degrees. And I would say, well, why are you subtracting 360, right? And again, like it kind of gets a little different. Like you could basically go in the opposite direction. And then if you, so you could say that by subtracting 360, you're going to get to the same angle as well. So we could start and then you could add 2 pi, or from here, from this point, you could actually subtract 360 and that would take you back to the same point. It gets a little confusing looking at it that way. But really the way to find, and I'm actually going to delete that. But the way to understand coterminal angles is you're just adding and subtracting 2 pi or 360. You're just adding a revolution. Because again, what is 2 pi? What is 360? It's just a revolution, right? It's just a loop around the circle. So when you add 2, like if here's your like angle and your point, and if you would just add to 360, you're just going to keep on going back to where you started, right? Or if you went in the negative direction, which is subtracting 2 pi or subtracting 360, you're going to get the exact same thing. Now, it doesn't really make as much sense in the context of the problem I explained, so that's why I wanted to kind of stop it. I did spend a lot more time with my students kind of going over some scenarios of like being on the track, which at this point, I don't want to even kind of go through because in reality, you really need to understand adding and subtracting 2 pi or 360 is like the easiest thing to do. So what I did though is I did kind of go through these different scenarios here with this angle. Like for negative 3 pi over 2, that is the red angle, right? And actually what I'm going to do is I'm going to go back with the blues. I'm going to go through like each color. So there's my red angle, negative 3 pi. That's my original angle. Now, what if I took and I subtracted, so let's do negative 3 pi over 2, and let's subtract 2 pi. Now, obviously, guys, subtracting 2 pi with a fraction, that's like, oh, God, what am I going to do here? But again, remember, in terms of halves, we can just rewrite this as negative 3 pi over 2 minus 4 pi over 2, right? Which gives us a negative 7 pi over 2. Now, if we were to graph negative 7 pi over 2, that would be that blue angle. And think about it. If you go all the way around the circle, that's negative 4 pi halves. 4 pi halves, 5 pi halves, 6 pi halves, 7 pi halves. So you can see how that is verified algebraically. Now let's go and do a green one. Because again, I said you could, subtract, you could also add. Now, instead of using 2 pi again, let's just add 2 pi. Oops, I'm sorry. I'm going to change that into 4 pi halves. So I'm just going to write this as 4 pi halves. So if I add 4 pi, you can see that I get pi halves. And again, look at that green angle. You can see the green angle is at pi halves. Now, you could add 2 pi again, right? You can add 2 pi as many times as possible. So for the pink one up there, I'm basically just taking my last angle, pi halves, and I'm going to add 2 pi again to that. 4 pi halves, and you get 5 pi halves. And again, let's check it. all the way around circle is 4 pi halves, plus another pi halves is 5 pi halves. But the main thing I want you to see is the angles all start on the positive x-axis and they all line on the y-axis. So when getting to this one, 17 pi over 6, again, it's important to note that this is greater than 360. So when I graph this, I go, or 2 pi, sorry. So I broke this up into 12 pi over 6 and 5 pi over 6. So I'll go all the way around, that's 12 pi, and then add 5 pi over 6. Now, it gets a little confusing, this one, because if I take 12 pi over 6 and I add, so again, here's my coterminal angles. Oh, now, first of all, it says determine the smallest and positive negative coterminal angles. So by subtracting 2 pi, I got negative 2 pi over 6. By adding 2 pi, I got pi over 6, right? So those are going to be my two smallest coterminal angles, because if I added 2 pi again, I got 5 pi over 6, which is a coterminal angle. It's just not the smallest coterminal angle. That's why these are going to be my two answers. Now, what I did here is I graphed these, but then I actually didn't give the answers. I just graphed them. So I got to go ahead and do them now for you. So the important thing is if you take 7 pi over 6, right, a lot of people just memorize, oh, just add and subtract 2 pi. And like, yeah, that is correct. But why do if I add, again, if your goal in this problem is to find the smallest positive, if I add 2 pi, remember 2 pi in terms of 6 here is 12 pi over 6. So by adding 2 pi, I'm going to get a really, really big angle. So I don't want to do that, right? That's going to give me 29 pi over 6. I'm trying to find the smallest positive. So what I'm going to do is 17 pi over 6, I'm going to subtract 12 pi over 6. And when doing that, I get 5 pi over 6. Now again, that's still positive. And again, I need to get a negative angle. So all I'm going to do is I'm going to take 5 pi over 6, and now I'm going to subtract 2 pi one more time. And by subtracting 2 pi over 6, you get negative 7 pi over 6. Now again, do we see 5 pi over 6 as well as negative 7 pi over 6? Yes, and you can see how they are represented graphically as my two solutions. I just didn't do the algebraic portion. But now let's go and do the algebraic portion here for the rest of these angles. And again, we're just trying to find the smallest positive and the smallest negative coterminal angles. So in terms of fourths, it's important to know that 2 pi, I think for these is equal to, 8 pi over 4. So this is between one revolution. So therefore, I'm just going to add 8 pi over 4, and I'm going to subtract 8 pi over 4. So that gives me 15 pi over 4. And this gives me negative pi over 4. Here we have a negative angle, which again, it's fine, but notice that this is larger than one revolution, right? So again, because 2 pi is equal to 6 pi over 3. So you can see that this is larger than revolution. So if I add 2 pi to this, I'm still going to have a negative angle. So therefore, what I'm going to do here is I'm going to add 2 pi twice rather than subtracting. So when I add 2 pi once, that gives me a negative pi over 6. I need to add 2 pi again. Now, could you add 12 pi over 3? Yes, you could. Or you could just take the last answer that you had and then just add 2 pi again to that. And that gives you now 5 pi over 3. So again, just recognize when you have an angle that's larger than 2 pi, larger revolution in the positive or in the negative direction, make sure you're either going to be adding twice or subtracting twice. In this case, for fifths, this one's kind of weird, right? But 2 pi is going to equal to 10 pi over 10 pi over 5. So again, this is less than one revolution, so I'm going to add 10 pi over 5 equals 11 pi over 5, and pi over 5 minus 10 pi over 5, negative 9 pi over 5. And now we have now we have an angle that's in degrees. Again, guys, kind of like the same idea here. Again, that's within one revolution, right? It's not larger than 360. You're subtracting 360. So I'm just going to add 360 to this number. Obviously, that's going to be one revolution. And you can see that is going to be 225 degrees. And then you can take negative 356 minus 360. And that is going to equal negative 495 degrees. So again, this is just a process of finding these coterminal angles. And yes, the obvious idea is really just to add and subtract 2 pi or 360. But again, you can notice that when you have angles that are larger than a revolution, you got to be careful from there. And, I think it's just also important to understand the graphical approach from there. But that is it, ladies and gentlemen. That is basically all the angles in trigonometry. Hopefully you have a better understanding of how to graph them, the different types of angles, how we represent them, how we label them, as well as how to convert between them. Because you can see that we did a lot of radians. Like we introduced radians, a lot, but you can see how they are just really a different unit, therefore degrees. So hope you learned a lot. And if you have any other questions or reflections from this lesson, I look forward to hearing your comments, and I'll see you guys on the next video. Cheers. Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we're going to work through angles and constraints in trigonometry. So this is actually the third lesson that I teach in my trigonometry unit. So I'm going to go ahead and work through my notes, so therefore you can see me working through multiple problems and get the solutions that I covered in my class. So what we're going to talk about in this lesson is basically just how to identify the quadrants that an angle lies in, how to evaluate the 6 trigonometric functions given a triangle and constraint, as well as to evaluate the 6 trigonometric functions when given a point. And you might notice this is very similar to kind of what we've already covered in day 1 of our first lesson. And that is true, because actually this is like a little overflow of problems that I decided I wanted to separate from the first 2 lessons to kind of create it as its own lesson. However, in a typical textbook, you would see these combined with either in day 1 or in day 2's lesson, either in right triangles or in the angles in trigonometry unit. But I wanted to give them a little of their due because students have trouble with identifying the quadrants. It's not so much labeling the quadrants, but it's just understanding that process of the constraints for the functions. So either way, let's go ahead and get started on how I started this lesson, which is basically just asking students to plot a point. Now, I know it kind of sounds like a little elementary task to give some students, but there's a couple of key points that I wanted to make sure students understood. The first thing is that, again, these are coordinate points. These are x and y, right? So x from the origin, x tells us the horizontal distance away from the origin, and y is going to give us this vertical distance away from the origin. So you can go over 1, up 2, right? You're not doing, I remember when I taught Algebra 1, sometimes we'd have students do this. Well, that's like 2 points, right? So you're not plotting 2 points, you're just plotting 1 point. So it has a x and a y coordinate, right? So that was kind of like that important idea here. It's just understanding those distances, because that's going to come up in this lesson. The other thing was like estimating. I'm not big on students being able to, how correct they are on their graphing, but I wanted them to understand, 2/3, that's larger than 1/2. Forget about the negative. It's larger than 1/2, but less than 1. It's actually 0.666 repeating, right? But so just as long as you can estimate, and like you can even see my graph is not that great, but at least just understanding where that should lie if I was going to graph it. And then also the square root gets a lot of students as well, because they're like, I don't know the square root of 2. You're right. Probably most of you do not know the square root of 2. And if you don't have a calculator, what do you do? Well, in my case, I just like for them to understand, the square root of 1 and the square root of 4. So, the square root of 2 is going to be somewhere in between 1 and 2, right? And it's going to be closer to 1 than it is to 2 because we have the square root of 3 in there as well. And then the last thing I just wanted students to recognize when they're plotting these points is notice that each point is in a different quadrant. And the reason why they're in a different quadrant is either the x or the y, or both are going to be negative, right? In the first quadrant, my point is positive. Whereas this second quadrant, my x coordinate is negative. Third quadrant, they're both negative. And in this fourth quadrant, the y coordinate is negative. And I kind of gave away my quadrants, but that was something I wanted students to, I tried to remind them of, which was that the coordinate points, or the quadrants that we have previously studied, quadrant 1, quadrant 2, quadrant 3, quadrant 4. And this is something that we do refer to throughout this lesson and in later lessons. So it's just important for students to remember those quadrants. Now I already kind of talked about this, but as in that warm-up, but this is what one thing I wanted students to basically go ahead and see is, this little summary here. So in quadrant 1, the coordinate point xy is always positive. And that's what's awesome about quadrant 1. X and y are positive. Like when I know something is in the first quadrant, this is going to be really helpful. We know that x and y are going to be positive. In the second quadrant, you can see that the x is negative. The y is positive. And you can just kind of see this little summary of information. So again, I kind of like wrote them out here, but I think just understanding this figure here is going to be really just kind of helpful to remember. So now is where we start to make this kind of jump now into a triangle in the quadrants, because previously when we were doing triangles, like in day one, we just had a triangle in space, right? It was just some random right triangle in space. There was no up, there was no down, there was no left, there was no right. It was just a triangle in space. So the point was, even though we always just did positive numbers, but negative numbers really made no sense. Well, now we're putting triangles in a XY axis in the, in the quadrant system here, or in this coordinate grid. So therefore, now we need to take into consideration the directions that we need to take into consideration the orientation of the triangle. So I kind of worked through this, but I just want to kind of step my way back and kind of do how I started this. So I first started this with the XY. We knew that X represented the, here's the point. X represents this distance over, and Y represents the distance up. Now, we can create a triangle by obviously drawing a direct angle towards the origin. And if you were to think about that, you could say, well, what should we call that? That's the hypotenuse. And some people like to call it C or H or, whatever case. We're going to go ahead and use R, and you'll see why. We'll call it R in a later lesson. But for my point is, let's just understand what is R representing in this case. R is representing the direct distance from the origin to the point, right? We have the horizontal distance, we have the vertical distance. R is like the direct distance, right? If you could instead of walking that street, if you could run directly to that point, that would represent R. Now, obviously in the triangle here, you can see that it is the hypotenuse. Now, there's also a couple of key points here. Notice how my right angle is going to be perpendicular with the x-axis, and that my angle here is at the origin, has a vertex at the origin, and it's also between the terminal side and the x-axis. So this is what we call our central angle. But this is really important to make sure you understand this how this triangle is drawn, because sometimes students will draw the triangle like this, and sometimes students will draw the triangle like this. Now, obviously, this is going to be taken into consideration like X and Y, which is not going to work, and this one is not going to work. And the reason why it's not going to work is because notice these angles that I have here, and this is really important to understand. When I reflect this, when I take this point and reflect it over here, you notice that the X just changed the same, right? The Y coordinate remains the same, the R coordinate remains the same. The only thing that changes is the X. And then I say, look at the angle theta. The angle theta, again, if we're just reflecting this triangle, that is the same, right? So this angle is the same. Then I say, well, what does this angle really look like? How can we kind of maybe conceptualize, understand based on last chapter or last lesson what that angle is? And you can say that that is the reference angle, right? If blue represents my angle, this point here would represent the reference angle. And that is true for this angle, for that angle, and for that angle. They all represent the reference angle. And that is extremely important, because once we get into our next lesson, we are going to be talking more and more about the reference angle. So last class period, we just really introduced the reference angle and kind of showed students how to find it. Next lesson, we're going to actually be utilizing the reference angle to help us solve problems. So if you drew your triangle like this or this, you notice that these are not reference angles, right? The reference angle is between the terminal side and the x-axis. So basically, I kind of just ended up with my students. When you're drawing a triangle, because we are going to be drawing our own triangles in today's lesson, if it doesn't look like one of these triangles, then it's going to be wrong. So make sure you're drawing your triangle here. We're representing these as reference angles or as central angles, where basically the vertex is going to be at the origin, and your angle is going to be the terminal side between the side as well as the x-axis. So just make sure it's always with the x-axis. You can always make your triangle perpendicular to the x-axis, not the y-axis. All right. And then the only other thing that I also talked about is, the difference here with all these triangles is they're just reflections. This is reflected about the y-axis, then this is reflected about the x-axis, and then you reflect it over. So you can see how the side lengths now change based on which quadrant they're in, right? But the one thing that does not change is R. R remains the same. R is always positive. And again, if you just think about what R represents that direct distance from the origin to that coordinate point. So of course R is always going to be positive. Like it doesn't matter which quadrant it's in, like the orientation, R is that direct distance, right? So it doesn't have any direction to it. And that's going to come, that's going to be very helpful for us in this lesson to understand that it's that direct distance. But last but not least is when we were looking at this, and we did spend a lot of time like I'm doing now. Since we have these new triangles with X and Y's and R's, that means our previous trigonometric definitions, we can actually update those from day one. So let's go ahead and take a look at some new trigonometric functions. And they're not really new trigonometric functions. They're the same trigonometric functions. They're just a new way of basically describing them. So, here's the triangle in the first quadrant again. We can see if here's our angle theta, right? We remember sine, right? Sine of theta was opposite over hypotenuse. And that's still the case, opposite over hypotenuse. But now when we're talking about this in a coordinate grid and not some random triangle in space, we can use y over r, where again, r represents the hypotenuse, right? Or it's also that direct distance here from the origin to the point. So sine of theta is y over r, so therefore cosecant of theta you can see again as the reciprocal, it's just r over y. Cosine and secant, again, are reciprocals of each other, and tangent and cotangent are reciprocals of each other. Now, there's something else that really plays into this that's important to understand because, positive and negatives, as I mentioned, like now make sense, right? They are important. So if sine is negative, right, r is always positive. So if sine is negative, that means y is negative. So if sine is negative, cosecant has to be negative, right? If y is negative, then y is going to be negative over there. If the cosine is negative, then the secant is going to be negative. The tangent is negative, the cotangent is going to be negative. So that's one thing I'm looking at when I'm grading. If I know that we're in a certain quadrant, I know that both sine and cosecant are going to be negative, right? Because basically they're the same reciprocal, they're the same sides of the triangle, just, different comparisons, either opposite or hypotenuse over opposite. So they're both definitely going to have the same sign, either as positive or negative. Now, it does get a little tricky here with tangent and cotangent, just in the fact of if I know it's negative, I don't know if it's the y or the x that's negative, right? Because typically we write that x in front or the negative in front, but it could be one or the other. So that's what we're going to be basically discussing today is how to determine which is going to be negative, because you could have a negative in the numerator, you could have a negative in the denominator, you just can't have it in both. The other thing is also if it's positive, that could be a positive y over a positive x, or it could be a negative y over a negative x. So dealing with tangent and cotangent sometimes can get a little tricky, and that's obviously what we're going to cover here in this lesson. So before we get started though, there's one last topic that we want to cover, which is basically just understanding the trig functions and the constraints. So if you remember, here's just me redrawing all the triangles now in each quadrant. And if you remember the trigonometric functions, right? Sine is y over r, cosine is x over r, tangent is y over x. You can notice that in the first quadrant, since x and y are always positive, that the sine, cosine, and tangent are always going to be positive. In addition, if sine, cosine, and tangent are positive, therefore cosecant, secant, and cotangent are positive. So I didn't even write them in there because we now already know that the reciprocals are also going to be positive. And we're going to get faster at this, but I'll just kind of go through the first summary out here. If we're in the second quadrant, we know that the x is negative. So any trigonometric function which is when x is included, then is going to be negative. For instance, cosine and secant will be negative for any angle that's in the second quadrant, as well as tangent and cotangent, because those are, tangents y over x, y over negative x, and cotangents negative x over positive y. So of course, those are going to be negative in the second quadrant. When we look at the third quadrant, you notice that a negative x and a negative y. So obviously, cosine's negative, secant's negative, sine's negative, cosecant's negative. However, the tangent, though, is going to be positive because negative y over negative x is positive, or cotangent, negative x over negative y is positive as well. So you can see here, basically the x, both of them negative. And then last but not least, the fourth quadrant, the y coordinate's negative. So now my sine and cosecant are negative, but also my tangent and my cotangent are going to be negative. So that is just kind of like this little summary of ideas. And again, you don't need to memorize these or write these down. I just told my students, but it is a good idea to just kind of see how we can identify, without actually evaluating the trigonometric functions, we can just see if they're going to be positive or negative just based on knowing which quadrant they lie in. All right, so now let's go ahead and determine the quadrant. So fairly basic, right? We have our 4-quadrant system, and we're just going to practice drawing the triangle in the correct quadrant system. So there's a couple different ways that I'll present students with them. The best way is just tell them which quadrant the angle lies in. But a lot of times we're going to be given some trigonometric inequalities. So for instance, this one says cosecant of x, remember x in this case is the angle, cosecant of x is less than 0. Well, again, that's really just a fancy way of saying something is negative. So if cosecant is negative, what does that mean? So remember, cosecant of an angle is your hypotenuse r over y. Well, r is always positive. That means y is negative. So then which quadrant is y going to be negative? Well, y is going to be negative in the 3rd and the 4th quadrant, right? Because if the y coordinate is negative, it's going to be down here. So it has to be in one of these two options. And then cotangent of x is greater than 0. Again, that's just a nice fancy way of saying something is positive. So cotangent, it represents the x over the y. Now again, as I mentioned, that is important because x over y could be positive x over positive y, or it could be negative x over negative y. Basically giving me the option for the 1st as well as the 3rd quadrant. And therefore, what you can see is, I'm not really doing this plus or minus, but you can see that in the 3rd quadrant, that is the only quadrant where both of these restrictions are true. So therefore, I can just draw my triangle. I'm going to use the same angle x, and again, I'll kind of further explain this later, but because even though it represents the reference angle here, but I'm go ahead and graph that same triangle in the 3rd quadrant and just make sure I graph it the way that we kind of, discussed from the beginning. In the next example here, I have 270 degrees is less than some symbol that we have not discussed yet in my class is less than 360 degrees. And I joked to my students, I said, hey, you don't know what that symbol is, so, hey, we should just not do a problem, right? And they're like, yeah, sure, why not? What is that? But again, that is phi. It's another Greek alphabet, or another letter in the Greek alphabet. But again, the important thing is it's something we don't know. It's an unknown. But again, it doesn't make sense. It's, it's representing some angle between 270 degrees and 360 degrees. So could we do a rough sketch of that angle? And yeah, if I know here to here is 270 and all the way around is 360, then I can assume that phi is going to be some angle, some angle right around in there, right? So therefore, I can draw my triangle in the 4th quadrant. I know it's going to be 4th quadrant. I'm not going to use phi. You could use phi. But again, representing that this represents the reference angle, you could use phi prime. Just really depend on, I'm not going to get into that because what we'll do is next class period, we'll kind of further understand the relationship between this angle and that angle and how to apply them. But for right now, we're just going to use another angle. In this case, I'll just use theta to represent that angle. But either way, we just really want to understand the quadrant and how we can arrive at the quadrant, either by some trigonometric inequalities or just by using another inequality based on angles instead of trigonometric expressions. All right, so then let's go ahead and work again through another set. So in this example, we have secant of alpha is less than 0. So again, really what I like to do is just kind of identify what is secant. Again, secant is going to be r over x. So again, if that is less than 0, then I have the 2nd quadrant, or it's going to be in the 3rd quadrant, right? It has to be in one of those two. If tangent is less than 0, well, remember tangent is going to be a y over x. So therefore, that's either tangent is less than 0, that's going to be negative y over x, or that's going to be a positive, or that's going to be a positive y over a negative x. It's going to be one of the two. We don't know which one it's going to be, but it's going to be one of those two. So again, that's either going to be in the 2nd quadrant, or that's going to be the case in the 4th quadrant. So you can see that in quadrant 2 is the only quadrant where that is going to be true for both of them. And therefore, I will just go ahead and draw the triangle there in that 2nd quadrant, right? Because really the question was just what quadrant does the angle lie in? The next one here, we have sine is less than 0. So again, sine is going to be y over r. So again, if sine is less than 0, that's a horrible line, but that's kind of cool, is less than 0. So that's going to be down here or down there. If cosine is greater than 0, then it's going to be over here or over here. So you can see that the only are true in this 4th quadrant. So let's go ahead and draw our triangle. And that one's going to be theta right there. So I'll just go ahead and use theta in that angle. There you go. Oh, yeah, and cosine is just going to be, let's just write that in there, x over r. All right, the next one is now just giving some angles here. So we're going to have pi is less than beta, which is less than 3 pi halves. So again, now we're having an angle that's in radian form. So it's the same kind of idea. We know that halfway around the circle here is pi, right? So if we start here in standard form, here's pi, and then here's 3 pi halves. So it's going to be some angle right in there. And again, if I wanted to draw my triangle in this third quadrant, then I'm just going to draw it just like that. And I'll just go ahead and use alpha to fit in. But you can see basically that triangle is going to be represented in the third quadrant. And then last but not least here, we have 0 is less than y, which is less than 90 degrees, which is going to give me a triangle here in this first quadrant. Here's 0, there's 90 degrees, and there's your y. Okay, so again, fairly basic, but you're going to see here in the next set of examples why understanding the quadrant is going to be helpful for our problems. But we can just understand that this is going to be important because based on each of these problems are in different quadrants, and based on that information, we know that the trigonometric functions are going to be positive and negative, are going to be different for each one of these 4 problems because they're going to be positive and negative based on the quadrant that they lie in. And that's really the fundamental understanding that we need to take away from this lesson, is understanding how these constraints are going to impact our answers. So let's go and take a look at how our answers, or what type of questions we'll be go ahead and solving. So the first one was cotangent of x equals negative 2/3, and then we have a restriction cosine of x is going to be greater than 0. So we know that cotangent is negative 2/3, right? We write the negative in front. Again, remember that can be negative 2/3, negative 2 over 3, or a 2 over negative 3. It just cannot equal negative 2/3, right? So what I told my students is like, we have 2 options, right? It could be this triangle or it could be that triangle, right? It could be, remember cotangent is x over y. So it could be negative 2, negative 2x, 3y, or positive x and a negative 3y, right? So it could be one of the 2. You don't know which one is which. Let's use x. I forgot to put in these angles. Then we got to look at the restriction. Well, the restriction says cosine of x is greater than 0. Well, what is the only one where, remember, cosine of x represents the x coordinate, right? So what is the only triangle where the x coordinate is positive? Well, obviously, you can see here the x coordinate is positive. So therefore, we're going to use that bottom angle. So I'm just actually going to put a big X there to remind you that when we're doing these 6 trigonometric functions, we are not referring to this triangle. And actually, let's just do. I'll just maybe do a line. There you go. So we're not referring to that triangle. Bad triangle. All right. Let's go back. Oops, wrong one. Okay, so then I just evaluated the 6 trigonometric functions. Remember in the 4th quadrant here, the y coordinate's negative, so therefore I automatically can check my answers. I know sine and cosecant are going to be negative, as well as tangent and cotangent. And you can see sometimes I threw the negative in the numerator, or in the denominator in the numerator, and sometimes you can just put it in front. And it really doesn't matter. Typically, we always like to write it in front, but if you leave it in the numerator and denominator, that's perfectly fine. And what I asked my students to do is just kind of write the original function, and then they could rationalize the denominator. And if they needed to show their work, they could. But I am not going to be showing my work in this case for as far as rationalizing the denominator, because that's something we already covered. And I don't want to keep on spending so much time doing that because we do it a lot. However, I did want to bring up one other problem that we have. And that is with the sine of theta equals 1 over x, where cosine is less than 0. So this is a problem that we're actually going to be doing a lot of in this chapter. It's actually going to be something that we're going to tackle at the end of the unit, but I wanted to present it to the students for 2 reasons. One, so they understand that if I give them sine of an angle equals 1 over x, that is still a triangle. That's still opposite over hypotenuse, right? And we could still evaluate, we could still find the third side by using the Pythagorean theorem. Then the next part about this is that when you are evaluating, though the Pythagorean theorem, remember When you introduce the square root, the inverse operation of the square root is plus or minus, or the inverse operation of squaring is plus or minus the square root. So you have to include plus or minus again. We only stopped talking about that when a triangle was in space and negatives didn't make sense. But now, negatives make sense. Like, we know this orientation here. This is in the second quadrant. Not all the sides are negative. So, and you can see A represents this distance to the left. So of course this distance has to be negative. Like, if you write that distance, and I'll have this all the time when students take a quiz, is they'll draw the graph correctly, they have the side lengths correctly, but then they show this distance as being positive. And it's like, no, you're going to the left. This has to be negative. And that's why when you introduce, when we take the plus or minus here, that's why you can see we use the negative version. And again, I kind of finished the rest of the problem, so therefore those of you could kind of see how this works, but it's not really something that you're going to need to be concerned about, at least for the rest of this lesson, as far as how to evaluate those. But I really wanted to make sure students understood the plus or minus and how that comes up. All right, so now let's go ahead and work through some 4 different examples that you can kind of see are all different, are all the same. You can see that they, in each one of these we have our trigonometric expression, kind of like what we did in day 1, but then we also have a constraint. And again, the constraint is going to tell us which quadrant we are going to be in. So I'm just going to kind of work through these individually, and we'll kind of see how their answers compare. So in this first example, we have sine of theta equals the square root of 3 divided by 2. So again, let's just remember, like, the sine, represents the y over r, right? So I could plot this, but again, let's just kind of identify which quadrant we're dealing with. Cosine is going to be less than 0. So cosine is negative. So again, if cosine is negative, that means our triangle has to either be in the second quadrant or it has to be in the third quadrant. But it has to be in one of those two, right? If the x-coordinate is negative, less than 0, then it has to be in these two quadrants. So and then obviously, I can look at this. I'm not going to do like which quadrant it is and do where they intersect again, which you could do. But hopefully you can just recognize the sign is positive. So out of these two triangles, this triangle in the second quadrant, obviously the sign is positive. Here's where the sign would be negative. So drawing my triangle correctly here, I'm going to go here to here. So then this is going to be square root of 3, and this is going to be 2. Now again, I do not know my x value in this case, so therefore I'm going to use Pythagorean Theorem. So I'm going to say 2 squared equals square root of 3 squared plus, I don't know, let's call this a again. A squared. So this is 4 equals 3 square root of 3 squared is just 3 plus a squared. And therefore, a squared is equal to 1. Subtract the 3, right? And then you're going to square root both sides. So therefore, a equals plus or minus 1, which again, we know that since we're going to the left here, we can see that a is going to equal negative 1. So again, that's very important because a lot of students will get 1 and they'll write a 1 there. But again, notice that we're going to the left. So that's why the my a is, in that case, negative. All right, so now we're just going to evaluate the 6 trig functions. So we have sine of theta is obviously already given to us. So that's awesome. The cosine of theta is going to be negative 1 over 2. And the tangent of theta is going to be square root of 3 over negative 1. And again, if you look at this summary here, if you look at that summary, and I'm just going to simplify these from there. But if you look at the summary here, that again, it makes sense. Like cosine and tangent should be negative in this second quadrant. Now let's go ahead and do the reciprocals, whereas sine is positive. So the cosecant of theta is going to be the reciprocal. So that's going to be 1 over the square root of 3 over 2. You could do it that way, or we talked about, it's just the flipped version, right? It's just 2 over the square root of 3. So now I could rationalize the denominator, and I get 2 radical 3 over 3. The secant is just the reciprocal of negative 1/2, which is just giving me a negative 2. And the cotangent of theta is going to be the reciprocal of negative square root of 3. So that's going to be 1 over negative square root of 3. Again, you could rationalize the denominator, put the negative in the top or the bottom. Just don't put it in both, or put it in front. In this case, you get square root of 3 over 3. All right. So that's basically our going to be case. We're going to, utilize which quadrant we could be in. And sometimes you might just want to like put in your options. Like for instance, I have tangent of alpha is negative. So if I think about that summary, I have two options here. Tangent of alpha is going to be negative either in the second quadrant, like we just explained, or in the fourth quadrant. Whereas sine is less than 0, that is only going to be true in the third quadrant and the fourth quadrant. So just kind of by using visualizing this, and again, you could go through like drawing the triangle like I did in this first example and like doing your options, or you could do like the first problem that I did and actually, draw like two hypothetical, identify the quadrants and see where they, intersect. But in this case, you can see that the only triangle that makes sense is in the fourth quadrant. Now, I do recommend though that you still draw this triangle to make sense of it, right? So if this is going to be in the fourth quadrant, then let's make sure we understand where it's going to be. Now, again, we don't know where the negative goes, is it in the top or the bottom, but since it's in, since we're doing it in the fourth quadrant, we recognize that, this is y over x, right? So we know that the x is positive and the y is going to be negative. So this would be a negative square root of 3, and this would be a positive 3. And here's your angle alpha. So again, by looking at this triangle, does this make sense for the tangent? Yes, negative square root of 3 over 3 would be negative, and the sine, the y-coordinate, is negative. So it's, this is going to work. No other quadrant that you could play around with is going to satisfy that. So now we have our triangle. Now we just evaluate the 6 trig functions. Just make sure now we're taking into consideration that is a negative square root of 3. So the sine of alpha, we can't do the 6 trig functions until we know what our hypotenuse is. So, also at this point, we start doing the Pythagorean theorem in our head. But, let's just kind of work it out here, and let's just call this r squared. So 3 squared is 9. Negative square root of 3 is just going to be, again, a positive 3 equals r squared. And then in this case, we're going to have 12 equals r squared. So in this case, we don't have a nice little number, right? We're going to have r is going to equal the positive square root of 12, right? So you square root both sides. Now, it's very important that, remember, r is always positive, right? So we don't need to worry about the plus or minus because r in this case is always positive. However, we do have to simplify our r. So by simplifying the r, remember that the square root of 12 can be broken down into 2 radical 3. All right, so now we have our r, which is 2 radical 3. And now let's do our 6 trigonometric functions. So sine of alpha is going to be opposite over hypotenuse. So it's going to be negative square root of 3 over 2 radical 3. Well, the square root of 3's are going to divide out, so that's just going to leave us with a negative 1/2. The cosine of alpha is going to be adjacent over hypotenuse. So that's going to be 3 over 2 radical 3. Rationalize the denominator here. So that's going to be 3 radical 3 over 6, which can be reduced to square root of 3 over 2. Let's see here. The tangent of alpha, we already have that answer, right? So that one's easy. Then let's do work on the reciprocal functions. Now, again, we want to do as least amount of work as possible, right? So rather than flipping, our original ratio, let's just flip our final answer, which would just give us a negative 2. Rather than flipping this ratio, let's flip our ratio over here. So this is secant of alpha. It's just going to be 2 radical 3 over 3. And then tangent here, cotangent. I'm actually going to go back to the triangle. Cotangent of alpha. Because I don't really want to reciprocate that, but the cotangent, remember, is x over y, which again, you're not going to really get away from it then. So it's a negative 3 over the square root of 3. Rationalize the denominator is a negative 3 square root of 3 over 3, which equals a negative square root of 3. Just trying to fit that in all the way at the end. So you can see here, really kind of the same numbers, it just involved a little bit more simplifying. But again, and also they're different because this was in quadrant 2 and this is in quadrant 4. So the trigonometric functions are different, right? And I know that the sine and cosecant as well as the tangent cotangent are going to be negative. All right, so now let's get into some fun ones. So here we have secant of theta equals negative 4. Now again, remember secant is r over x. Well, we don't have an r over x. We just have a number. But remember, trigonometric functions are a ratio. They are a comparison. How big is the hypotenuse compared to the adjacent side? So that means we need to write this as a fraction. So to do that, we can just write this as -4/1. But remember, secant, secant of theta is equal to r/x. So when we have -4/1 is incorrect because r is never negative, right? So it's not going to be the fact that, oh, this triangle doesn't exist. But again, we can rewrite this as 4/-1, which makes a lot more sense. R is positive and my x is negative. So if my x is negative, I know I'm dealing with here the second or the third quadrant. My tangent is positive, right? So again, remember tangent is y/x. So if it's positive, that's going to be in the first quadrant. Obviously, everything's positive in the first quadrant. Or in the third quadrant, because -y/-x also gives me a positive. So therefore, you can see that the only quadrant that they both are true in is going to be the third quadrant. So I'm going to draw a triangle in the third quadrant. So that's going to be 4. That's going to be -1. I'm going to use Pythagorean Theorem here. So we have 4 squared equals -1 squared plus, b squared. That becomes 16 equals 1 plus b squared. So let's see. So b squared equals 15, and then square root. You can see b is going to equal the square root of 15. Sorry. That's going to be plus or minus the square root of 15. And again, we notice that we're dealing with something that's in the third quadrant. So therefore, this is going to be a negative square root of 15. Again, very important to understand that distinction, that why it has to be negative. So now let's go ahead and evaluate my 6 trigonometric functions. So we have sine of, what are we doing? Theta. Okay, so sine of theta in this case is going to be opposite over hypotenuse, so that's going to be a negative. I'll just put the negative in front, -15/4. The cosine of theta is going to be a -1/4. And the tangent of theta is going to be opposite over adjacent. So again, remember tangent is positive, right? A negative over negative is positive. So that's going to be a negative square root of 15 over -1, which is just a positive square root of 15. So now let's go to the reciprocal functions. So cosecant of theta is going to be hypotenuse over opposite. So that's a reciprocal. So it's going to be 4 over the square root of 15. Rationalize the denominator here. You're going to have a negative 4 square root of 15 over 15. For the secant of theta, that's just going to be a -4. And then for the cotangent of theta, that's going to be a positive 1 over the square root of 15, which equals the square root of 15 over 15. Bang. All right. Last example. Last example here, I have cosine of alpha is positive, right? And it's 5 over 13. If it's positive, then I'm dealing with the first or the fourth quadrant. And then I recognize the cosecant of alpha is also positive. Well, again, I can just actually stop here. If I know both things are positive, it has to be in the first quadrant, right? Cosecant obviously is only going to be positive in the first and the second. But again, the main thing that if you have something that's positive, then it's going to always be in the first quadrant. Or I'm sorry, when both terms are quadrant, it's going to be in the first quadrant. The other nice thing to notice about this is that you could use the Pythagorean theorem, right? X over R, or you could recognize that this is a Pythagorean triple. So, I'll write out the, x squared, or I'm sorry, let's do this as 5 squared plus, a squared equals, c squared, or I'm sorry, 13 squared. But hopefully you recognize here that we have done these problems, or we've introduced you before, that's actually going to be 12. And again, if you do the math, 13 squared is 169, minus 25 is going to be 144. The square root of 144 is 12. Since it's in the first quadrant, it's going to be positive. And the nice thing about this is now our trigonometric relationships are pretty easy, right? So we have the sine of alpha is going to be, 12 over 13. The cosine of alpha is going to be 5 over 13. The tangent of alpha is going to be 12 over 5. And now our reciprocals, we don't need to worry about our radicals at all. So therefore, our cosecant of alpha is 13 over 12. our secant of alpha is 13 over 5, and our cotangent of alpha is 5 over 12. So there you go, ladies and gentlemen. That is basically how our 6 trigonometric functions are going to change, or at least our problems are going to change if we are given a constraint. Because in the first lesson, we didn't have constraints. So we were just doing the exact same process for a triangle in space. But now you can see that orientation matters, right? It gives us now these negatives for side lengths that make sense based on the quadrant that the triangle lies in. However, we've been so focused on, finding the trigonometric functions given a triangle or given an expression. What if we were just given a point? So again, we can always create a triangle, right? If we have a coordinate point, this is x, y, and this brings up into like why we started just plotting points. You can always just plot the point, square root of 3, comma 1, like plot that point. We know square root of 3, again, is going to be some decimal between 1 and 2. So, I just kind of drew a graph there and I said, all right, that's going to be square root of 3, and that's going to be, the height is 1. So those are the side lengths of my triangle. I draw my right triangle correctly. And then I did the Pythagorean theorem here to figure out 2. So we're finding the hypotenuse, which is r. So therefore we know that it's going to be a positive 2. And now, based on this point, I know it's in the first quadrant. So that's nice. Everything's going to be positive. And from this point, I can create a triangle. So therefore, I can evaluate the 6 trigonometric functions. Now, you really don't need the 6 trigonometric functions or the triangle, because remember, the only 3 points that you need is x, y, and r, right? From our new definition today, all we needed was x, y, and r. Now, again, remember r, x squared plus y squared, and this is really kind of important. I didn't actually tell my students about this. X squared plus y squared equals r squared, right? Because r represents that hypotenuse. So without actually drawing a triangle, if you know the quadrant that the point is in, and you can figure out x, y, and r, based on our new trigonometric definitions, you could actually evaluate all 6 trig functions. Now, what typically happens? Most students just are comfortable evaluating the 6 trig functions from a triangle, and that's why I am going to teach it with drawing the triangle every single time. It's not that much extra time, and it also is just a good way for you to verify your work and check your answer. But the more comfortable you get with these problems, you can for sure just figure out x, y, and r and go about your way. Now, again, in this case, let's just say it was a multiple choice problem. Even just with the x, y here, we could solve for x, y, right? You could just say, you could solve the x, y. You could solve for tangent and cotangent though, because for tangent, cotangent, you don't need to know r. So you could just solve those without actually doing anything rather easily. All right, but let's go and look at some 4 different examples to kind of see how they differ and how this is going to help us with our understanding of these types of problems. All right, so here we have a couple points here, and you can see that they don't really look that pretty, right? Maybe B and D are not too right, but these do not look like that fun. So let's go ahead and give them a shot. Now, as far as graphing, 2 square root of 2, comma 2, I'm not even gonna, we could figure that out. We could, estimate, but in this case, let's just forget about it. Like, we just know it's gonna be positive, right? And we know that's gonna be larger than 2. So what I'm gonna do is I'm just gonna put this point over here. I'm not even gonna put any scales, because I don't want to overcomplicate the problem. We know that this side is 2 square root of 2 and this side is 2, right? I mean, that's it. You don't really need to know anything more except that it's in the first quadrant and that those are the side lengths of the x and the y, the adjacents, right? That's your x and that's your y. That's your adjacent as well as your opposite side. We could go ahead and use the Pythagorean theorem, though, to figure out our hypotenuse, which we know, again, is going to be positive. Let's call it r squared. So again, 2 square root of 2 is going to be 4 times 2, which is going to be 8. Plus 4 here is r squared, so that's going to be 12 equals r squared. So again, we have r equals, we already did this one, so that's going to be a 2 radical 3. Is that what I wanted from this? Huh. 2 radical 2. Let me just double check. That's going to be 4. I guess I wanted this one. Doesn't look as fun, but all right. I just want to make sure I had that one correct. That's 8. That's 4. Now my brain is like hurting. So 2 square root of 2, that's going to be 4 times 2. It's just 8, 12. Okay, yeah, it works. So let's go ahead and evaluate. So the sine, now again, like what angle should we do here? We can do anything, right? So I'm just going to use theta to make things easy. So sine of theta is going to be, this is 2 radical 3. So therefore, sine of theta is going to be 2 over 2 radical 3. I can rationalize the denominator here. The 2's are going to divide out, and that's going to give me square root of 3 over 3. For the cosine of theta, that's going to be adjacent over hypotenuse. So that's going to be 2 radical 2 over 2 radical 3. And therefore, again, you're going to have radical 6 over, the 2's divide out again. So in this case, you're going to have a, radical 6 over 3. And then we have tangent of theta. Again, I'm just doing the rationalizing in my head because that's something I've already covered. Tangent is going to be opposite over adjacent. So that's going to be 2 over 2 radical 2. The 2's divide out, so then you're going to have radical 2 over 2. All right, so now let's go ahead and get into the reciprocal function. So we have cosecant of theta, which is going to be just this reciprocal here. So just flip that over. That's going to be the square root of 3. Here we're going to have secant of theta, which is just going to be, let's see here, that's going to be, really the 2's divide out. So we can just, I'll just leave it up there. Square root of 3 over 2, square root of 2. Rationalize the denominator here. That's going to be a square root of 6 over 2. And then we have the cotangent of theta is going to equal 2 square root of 2 over 2, which is just the square root of 2. And there you go. So again, knowing that simplifying, so I wrote the original ratio and then I just simplified it. And I didn't show my simplifying work because that's something we already covered. The next one here, I have a coordinate point here in the fourth quadrant. Again, you could draw it out if you want to, but we know it's in the fourth quadrant, right? The x and the y are both negative. So therefore, that's a -6 and that's a -8. All right. Well, hopefully you guys also recognize that this is a Pythagorean triple. So you could do the Pythagorean theorem if you need to. But hopefully you guys recognize that that hypotenuse is going to be 10. Because 6 squared, 8 squared is 64, plus 6 squared, 36. 64 plus 36 is 100. Square root of 100 is 10. And of course, it has to be positive because r is always positive. So the sine, let's call this one different. Let's do this one as alpha. So the sine of alpha is going to be a -8 over 10. And again, we want to reduce these fractions, right? We can simplify these fractions. So dividing the top and bottom by 2, that's going to be a -4/5. The cosine of alpha is going to be adjacent over hypotenuse. So that's going to be -6 over 10, which can be reduced to a -3/5. And then the tangent of alpha is going to be the opposite over adjacent. So that's going to be a -8 over -6, which again can be reduced to a +4/3. Okay, so again, just making sure that you simplify and then also make sure that in the fourth quadrant that you can check sine and cosine should be negative and tangent should be positive. So now when doing the reciprocal functions, I'm not going to do the original. I'm just going to do the simplified version here. All right, I'm just going to do a -5. Oops, forgot the equals. So -5/4. For the secant, it's going to be a -5/3. And for the cotangent of x, or cotangent of theta, alpha, it's going to be a +3/4. So you can see once you've already kind of done the work once, you can really evaluate. All right, my favorite two problems. Two problems that students struggle with, which of course, who wants to go ahead and do this? Nobody, right? But there's something that's really important about this problem that kind of comes up that I used as an instructional piece when I was instructing. And then also this -1, 0, which is something we're going to talk more about in our next lesson. But let's go ahead and find the quadrants and then at least kind of go through these two problems to understand what they mean. So hopefully you recognize that this point is going to be, that's the x and that's the y. So it's going to be some triangle in the third quadrant, right? So we have -3/2, +3/2. Okay, So let's do Pythagorean theorem just like we do any other problem and see what we're going to get. So we have negative 3/2 squared plus a positive 3/2 squared equals r squared. So here we're going to have 9/4 plus 9/4 equals r squared. So that's going to give you 18/4 equals r squared. Now you could introduce the square root, right? So r is going to equal the square root of 18/4 plus or minus. Don't forget that. But again, we actually don't really need to include the plus or minus, right? Because we know we're just dealing r, so it's just going to be the positive version. And therefore, r is going to be, now we can just simplify that as the square root of 18 over the square root of 4. Legal process, okay? And the square root of 18, remember that can be broken down into 3 square root of 2. So r equals 3 square root of 2 over 2. Now again, you can't divide out the 2's, right? One's on a radical, one's not. But I think it's really important for me to write this out. Three halves times the square root of 2. All right, so here's the important thing. Here's what I want students to see. Nobody wants to do the 6 trig functions with the triangle like this. Nobody wants to do the 6 trig functions with a triangle like that. That is going to be way too many simplifying, way too much work to do. One thing I noticed is that the 2 legs are the same and that the hypotenuse is multiplied by the square root of 2. The legs are the same and the hypotenuse is the exact same of the leg, just multiplied by the square root of 2. And hopefully what that does is that brings up, oh, that is a 45, 45, 90 triangle. And again, remember, the trig functions, guys, are the exact same. It doesn't matter what the size is of the triangle, right? If they are proportional, they're going to have the same. They're going to have the same trigonometric functions, right? Because trigonometric functions are ratios. So what I could do here is you could use that triangle if you wanted to. Or what if you multiply all the sides by 2, right? That's a dilation in geometry. It's going to enlarge it, but it's going to have a scale factor. So it's going to keep the proportions intact, or the ratios, the trigonometric ratios intact. But if you multiply by 2, right, times by 2, you now have 3, negative 3, and 3 square root of 2, which is a little bit better, right? I like that. But what about now, let's make it even easier. What if now you divided by 3? Well, if you divided by 3, now you would have 1, negative 1, square root of 2. That is a lot easier for me to be able to evaluate my 6 trig functions. And you might even be as well versed in the 6 trig functions to already know what the trigonometric functions are, because we've already talked about our 30, 60, 90 triangles. But we'll use that as triangle if that's something that you are not familiar with. And I'm going to write this as beta. So sine of beta. Now again, it's in the second quadrant, so I know sine is positive. I'm just going to go ahead and go through my answers. Actually, you know what? I already know the answers for a 45, 45, 90 triangle. So I'm just going to write that in there. It's a 45, 45, 90 triangle. So I don't expect students to know the answers, at least in this point, but I know those answers, so I'm going to work with it. The cosine of beta, though, is cosine's negative, right, in the second quadrant. So that's going to be negative square root of 2 over 2. And the tangent is going to be negative. And tangent doesn't matter if it's these two fractions, these two, or these two. We know it's just going to be a negative 1. The cosecant of beta is now just going to be negative square root of 2. So when you flip that and rationalize the denominator, not negative. What am I doing? The secant of beta is going to be that's going to be the negative square root of 2. And then the cotangent of beta is going to equal, again, also a negative 1. So again, you could have worked out the relationships here, but basically we've already kind of talked about this 45, 45, 90 triangle and those values. So therefore, I'm just working it with that. All right, on to the last point. Again, is a very, very important understanding here, because if you take the point negative 1, 0, we have an issue because that does not create a triangle. So how are we going to evaluate the 6 trig functions without a triangle? Like, is that even possible? Should we just write not possible? You could, but let's go and investigate this a little bit further. Because I was trying to be really careful when I was describing these values that we're finding, the x, y, and the r. Yes, we can create a triangle, draw a perpendicular line, create a triangle, and go from there. But in reality, remember, x represents this horizontal distance. y represents this vertical distance, and r represents this direct distance, right? So if we take this point and, we kind of rotate it like around here, right? We know that x in this case is -1, y is going to be 0, and then r, again, if you just think of r as what is the distance from the origin to that point, you can say that r is going to be a +1, right? R is always positive. So r represents a +1. Now, again, all we need for our 6 trig functions is x, y, and r, and we have exactly what we need. So we actually can evaluate the 6 trig functions when we are not given a point that creates a triangle. We can actually use this information to evaluate our 6 trig functions. So let's do sine of, let's just go back to theta. So sine of theta is, again, just going to be y over r. So that's going to be 0 over 1, which is just equal to 0. The cosine of theta is going to be x over r. So that's going to be -1 over 1, which is -1. The tangent of theta is going to be y over x. So that's going to be 0. Wait a minute, what did I do? Sine is, 0 over r. Okay, tangent is y over x. So that's 0 over -1, which is just equal to 0. So now the reciprocals, though, we have something that comes into play here, because cosecant of theta is 1 over 0. And if you remember, we can't divide by 0, right? So this actually is undefined. The secant of theta is just going to be 1 over -1, which is also -1. So secant and cosine are actually the exact same. Interesting. And therefore, cotangent of theta is now going to be -1 over 0, which is, again, also undefined. So we'll talk more about that from now. But I just want to make sure that you understand, really, when we're given a point, drawing the triangle is important, or at least knowing the quadrant that the triangle in is also important. But then also realizing that really we just need to figure out these x and y's, and remember that proportionality matters. Like if you need to simplify the problem, as long as you're multiplying or dividing all the sides of the triangle by the same number, you are keeping those triangles proportional with each other, and therefore the trig functions are going to remain the same. So always kind of think about that. I don't want students to be spending 20 minutes trying to do the 6 trig functions and then getting the exact same answers that I got here in a fraction of the time. But hopefully that this lesson kind of helps you out, at least understand those constraints a little bit more, because we're not just going to be dealing with triangles in space. We are going to be dealing with triangles where the orientation matters. So hopefully you can reflect on what made sense for you on this lesson and what things you're still struggling with. And I look forward to reading your answers and helping you out on the next video. Cheers. Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we're going to work through the unit circle. This is the 4th lesson in my unit for trigonometry. So again, I'm going to work through my notes, so therefore you can get an idea of what the unit circle is, as well as how we're going to use it. And this is a very, very important lesson, because from this lesson on, we are going to be referring to the trigonometric functions most often using the unit circle and no longer with triangles. So basically we're going to come through is where do the points on the unit circle come from? How do we find a point on the unit circle given an angle? And how can we evaluate the 6 trigonometric functions given an angle? So you can see here's the difference here. Previously we always had to evaluate the 6 trig functions with a triangle. Now we're going to be using a circle, which kind of seems weird, but hopefully through the end of this lesson it will make a little sense to you. So to kind of set this up, in our first lesson, we talked about special right triangles. So here's an example of 45, 90-degree triangles, all right? And these are all the side lengths, because again, remember they are all proportional to each other, right? So all I did was I took these triangles and I just multiplied them by different scalars to kind of get these triangles. So the sine of 45 degrees is the same. We know the sine of 45 degrees from day 1 is square root of 2 over 2. And you can see, do opposite over hypotenuse of any of these triangles, and you're going to simplify to square root of 2 over 2. Now, on day 1, we had some problems that we wanted to evaluate for the, sine of 45, cosine of 45, tangent of 45, and we want to do all those. So we said, which side lengths would make this the easiest? And on day 1, we decided that triangle C was going to be the easiest because it had the two legs were 1 and 1. And for that day, probably it was the easiest based on what we knew. However, what we're going to use today is the 45, 45, 90 triangle where the hypotenuse is 1. And that's the essential understanding that we need to take away from today, is that this hypotenuse is going to be 1. And this is actually going to make our life easier and make everything possible that we want to do. And the reason being is because if you took sine of 45 degrees, you're going to do opposite over hypotenuse, right? Well, if you have opposite over hypotenuse and your hypotenuse is 1, we don't really care about the hypotenuse. We can just look at the opposite side. In the same respect, adjacent over hypotenuse, if it's over hypotenuse with 1, just go ahead and look at the adjacent side. So this helps us a lot when understanding our trigonometric functions. We don't have to do this opposite or adjacent we don't have to look at that full ratio when we know the hypotenuse is 1. And we did the same thing for the 30, 60, 90 triangle. Again, same thing. Here's all 30, 60, 90 triangles. They're all proportional to each other because obviously we know the sine of 30 degrees is 1/2, right? And you could do opposite over hypotenuse, right? Or you could simplify these. But in this case, you notice that it's 1/2 over 1. You could say, oh, the sine of 35 degrees is just the opposite side, right? When the hypotenuse is 1. The cosine of 30 degrees is, oh, just square root of 3 over 2. I didn't even have to look at the hypotenuse because it was 1. And that is again, really going to be our focus today, is only working with triangles when the hypotenuse is 1. All right, so last class period, we talked about the constraints and how it mattered which quadrant a triangle was in, because previously, we just dealt with these triangles that were just in space. You could have a triangle, 45, 45 degree triangle like this. And we're like, all right, there's a triangle in space. But then we talked about, well, if we have these on an XY axis, then the side lengths can be positive or negative. So if you look at this first quadrant, right, if we take this triangle, you can see there's my triangle I talked about. The adjacent side is square root of 2 over 2, square root of 2 over 2, and 1. Now, obviously, if it's in the first quadrant, everything's going to be positive. But we could also think about this, well, it's on a coordinate grid, we could take this to be the coordinate point, square root of 2 over 2, comma, square root of 2 over 2, right? From the origin, you're going over square root of 2 over 2, and then up square root of 2 over 2. So again, this is that special triangle that we are referring to. But rather than that triangle just being randomly in space with no orientation, we're putting it on an XY axis. So a couple key measures that we want to make sure we understood here, is 45 degrees is the degree form, right? And we're familiar with. But since we've also talked about radians in day 2, we know that's equivalent to be pi over 4. And again, notice that we're using this central angle, right, with the origin, and it's going to be perpendicular to the x-axis. Now, if I take this triangle and I reflect it about the y-axis, notice that really the only thing that changes is the x-coordinate, right? Now we're in the second quadrant. So the x-coordinate is going to be negative. The y-coordinate is still positive. The hypotenuse is still going to be 1. The central angle, or what we call the reference angle, is still going to be 45 degrees. Now, this is where it kind of gets a little confusing. Where am I getting 135? Well, again, like here's this angle. What we're really kind of measuring is this angle. That's what I'm writing down right there. And you'll see how we write that out. Basically, what I'm drawing is the angle from the standard form from here to here. That's what I'm writing there. Because we know the reference angle is 45 degrees, 45 degrees, 45 degrees, right? But if I wanted to figure out what are the actual angles from standard form that are producing those angles, that's where I'm getting those measures. Okay, so that's what I'm calculating, the 215 degrees, 5 pi over 4, 315 degrees, 7 pi over 4. And again, basically all I'm doing is if I know this angle is 45 degrees, and I know halfway around a circle is 180, I subtract 45 to get 135. I add 45 to get 225. All the way around the circle is 360, subtract 45, that's going to be 315. That means the angle from here to there is going to be 315 degrees. Now it's important that you understand like that angle from 315 degrees, right, is really equivalent to like negative 45 degrees. They both produce this terminal side, which yes, obviously makes this triangle, but it produces also this point, square root of 2 over 2, negative square root of 2 over 2. Because if I take this triangle and reflect it about the x-axis, you can see that this is going to be a negative, that's going to be a negative y-coordinate. In the same respect, if I take this triangle and reflip it down to the third quadrant, you can see how both of these points are all going to be negative. Okay? And And that was basically it that I wanted to cover with the 45-degree triangles. Making sure that, again, the same thing, halfway around circle is 4 pi over 4, right, which is pi. So I'm subtracting pi over 4 to get 3 pi over 4, add pi over 4 to get 5 pi over 4. All the way around the circle is 8 pi over 4. But you can see that this angle right here, right, all the way around the circle is 8 pi over 4, but you're pi over 4 short. So that's why I came up with the angle 7 pi over 4. And I know it doesn't really, it kind of seems a little confusing. In my class, I gave the students actually the unit circle to fill out with me. And I guess I probably should have mentioned that before. So therefore, they knew what to write in these angles, because these angles, like these angles right here, do not represent those angles right there. Those angles are all the same, which is 45 degrees or pi over 4. But what these angles represent is these angles up in there. And I guess I probably should have made that more clear. So hopefully you didn't get confused, because when I just started looking at it, I could see where some of you might have been coming from on there. But the main important thing is that we have a 45-degree triangle. These are not made-up triangles, right? We have investigated these triangles before. You've seen them, right? And we could have picked any one of these triangles, right? Any one of these. We could have done this one if we wanted to. But for the sake of today's lesson, we are going to stick with the 45-degree triangle where 1 is the hypotenuse. All right, so that's why I'm using this triangle in these 4 quadrants. I could have used any 45, 90-degree triangle. But by using 1 here, we notice that now the hypotenuse is 1 for all of them, okay? And then these are our side lengths. And then, just like we learned last class period, when we have the side lengths, we could also write them as coordinate points at these little points right here, all right? So now we have more than a 45, 90-degree triangle. We can also do a 30, 60, 90. So let's go and take a look at a 30, 60, 90. All right, so on the 30, 60, 90, what we have is basically, again, these little triangles up here, right? And instead of picking any of these, I'm just picking this one because it has a hypotenuse of 1. I'm trying to go with that theme of the triangle is going to have a hypotenuse of 1. So again, I'm doing the same exact process here. I am just orientating. I'm not really sure. I'm just making the orientation of the triangle to lie on the first quadrant where the 30-degree angle is at the central angle. Now, again, for the understanding of degrees and radians, I'm going to convert 30 degrees into radian form. You can see this is pi over 6. And yet again, no matter what I do with these reflections, I don't know why I didn't negate those. Jeez. No matter what I do with these reflections, these angles all remain the same, right? But again, like these angles right here are not the angles, the little central angles. Those are the angles for in each quadrant. So that's that one, that angle, and that angle. Okay, so 150 degrees. So again, if we know this angle is 30 degrees and we know halfway around circle is 180, you subtract, 30 degrees, and that's how I get 150, right? Or you have pi over 6, 6 pi over 6, you subtract pi over 6, you're going to get 5 pi over 6. And that same process is what I did. I added 30 degrees to give me 210, or I added pi over 6 to give me 7 pi over 6. All the way around circle is 360, so I subtract 30 to get me 330 degrees. Or all the way around circle is 12 pi over 6, you subtract pi over 6 to give you 11 pi over 6. So that is the process from there. Obviously, the square root of 3 over 2 and the 1/2 comes from the triangle that I previously showed right up here. And then, again, like understanding, since this is on a coordinate grid, like an xy axis, I can write the distance from the origin here of square root of 3 over 2, 1/2. I can write this as a coordinate point, xy, right? And then as I'm following these reflections, we obviously know that in the second quadrant, x is going to be negative. In the third quadrant, x and y are both going to be negative. And in the fourth quadrant, the y coordinate is going to be negative. The hypotenuse is going to be 1 for all of them. And that's really the only thing that's changing, right, is that these coordinates are changing and that the angles are going to be different for each one of these. Yet, their reference angles are all the same. And that was kind of one of the connections I wanted to make with the students when we were creating these is they all have the same reference angles and they all have the same coordinate points. The only thing that really changes is the signs of the coordinate points based on the quadrant that the angle lies in, right? Because the angles are different, right? All of these angles are different. So all of their quadrants are also different. And since their angles and the quadrants are different, that means the signs are all going to be different. Yet, the things that remain the same is the reference angles are all the same, the values of the coordinate points are all the same, and the hypotenuse is all the same. So those are some of those kind of similarities we wanted to do. But we kind of get stuck here when we only have a 30, 60, 90 and a 45, 45, 90 triangle, right? So we basically just took two triangles, threw them on the, coordinate grid. Like, what else can we kind of do? Well, that kind of brings us up to our 60, 30, 90 triangle. We can also take a 30, 60, 90 triangle, right? Instead of doing this, 30 degrees, 60, we can just flip it. It's the same triangle. I'm just changing the orientation of that triangle. Right? So if you just take the triangle, flip around, like still the same there. And then again, so we now know these coordinate points. Again, the hypotenuse is always going to be 1. This distance here is what, 1/2? I'll just write that in there. And this is square root of 3 over 2. Right? Just like we did for all the other ones. Did I write that in there? Yeah, I did. So this is 1/2, that's square root of 3 over 2. Now, in this case, we have 60 degrees, right? So we convert that to radians, and that's going to be pi over 3. So these are all 60 degrees, or pi over 3. So again, if halfway is 180, subtract 60, you get 120. Add 60, you get 240. Halfway around a circle is 3 pi over 3. Subtract pi over 3, you get 2 pi over 3. Add 2 pi over 3, you get 4 pi over 3. All the way around the circle is 360. Subtract 60, you get 300 degrees. Subtract pi over 3, you get 5 pi over 3. And again, just for the sake of conversation, or when students are looking at this at another date, I just want to make sure students understand those angles. That again, the measure here that I'm giving them is not for the reference angle, because we already know the reference angle is the same, but it is for these angles here, which produce the same terminal side. All right, but we're going to make this connection between these reference angles and these angles that I'm providing you, and how they relate to each other. All right, so then the hypotenuse all 1, we do our reflections, just make sure I did the negatives in this one correct, which I did. And again, you can kind of see it's the exact same thing now. We're just putting a 30, 60, 90, we're just rotating. So it's the same triangle. So in reality, I haven't really done anything new yet. All I have done is taken two triangles that we've already investigated in this class. I have changed their orientation and I've put them on an XY axis. Right? Now I did selectively choose the right triangles when the special right triangles when the hypotenuse was 1. But that's about it. So what if I took this quadrant, put it on top of this quadrant, and then put it on top of that quadrant? Right? You would have 12 triangles on a quadrant. And that would look a lot. And you could probably look at this and say, wow, that looks really confusing, especially with all the writing I would have, right? But that's exactly what we want to do. And what happens is when you combine these, I'm just looking at the first triangle here, but when you combine these, yeah, you're going to have, these 12 quadrants here. But what's nice about this is you can see when you put them together, they create this nice little curve. And again, also going with that understanding of the hypotenuse or the distance away, the hypotenuse is 1, you could say, well, from here to here is going to be 1. And if there to there is 1. And then if you just connect them, you can see it makes that beautiful, nice little arc, right? And then if you kind of continue that arc, you can see it brings up a circle. And that's what we call the unit circle. And again, why do we call it the unit circle? Well, we call it a circle because obviously it creates a circle. And it's the unit circle because like our counting units is by ones, right? So it's the radius is 1 of this circle. And that is because we chose the triangles to have a hypotenuse of 1. Right? So we could use if we would have chose the hypotenuse to be something else, then we could call it a something else triangle. But 1 is going to be our preferred number because it's going to make our life a little bit easier once we get into our trig functions, which you will see in a second. You can see here by looking at these 12 functions, that's going to be a lot of triangles or points to remember. So do we really need to memorize all of this stuff? And the simple question is no. I just want students to basically memorize these coordinate points. Basically the first quadrant. If the students know all the points in the first quadrant, then they're good to go. And again, there's a lot of ways to, memorize the quadrant. Obviously, you can look at your hand, like a lot of people know the good old hand method. Like you have 5 fingers, and how many points are there? Right? There's 5 points. So that's an easy way to remember them. The first 2 points are easy to remember. And then these points are not as easy to remember, and they're easy to get mixed up. So, the basic way that, we have is if you can really remember what I tell students, if you can remember the square root of 1, then you're good. Because once you know the square root of 1, just continue the pattern. Square root of 1, square root of 2, square root of 3. Square root of 1, square root of 2, square root of 3. And then everything has a denominator of 2. And there you go. Now I just created it, right? Because obviously a lot of students, when they're doing these problems, we're doing them quickly and they'll get them mixed up. And I do it all the time too. I might even do it today, right? You just got to slow down and like think about what actually it is which angle and point you are using. Really the main confusion I would say what students have is mixing up the 30 degrees and pi over 6. But just remember, the larger the denominator, the smaller the fraction, right? So pi over 6 is smaller than pi over 3. But students just want to connect, the 6's together. Pi over 6 is 60 degrees and pi over 3 is 30 degrees, right? Just because there's 3's and there's 6's. But just remember, one is a measure and one is a fraction. So they are not equal to each other. So just make sure you're careful with that. And the other reason why I only rely on this first quadrant is because all the rest of these points over here, all of these points are just reflections. They're the exact same values. We're not like throwing a 4 in here or a 5 or a square root of 2 or a square root of 5 or a square root of 7. No, it's the exact same coordinate points. It's just reflections, right? It's just positives and negatives. That's all the only thing that's changing. So I have a step-by-step process to show us, how to use this circle and this right triangle. But the main thing is you need to know this first quadrant, because after we get into more advanced lessons in this course, we are going to rely on this, knowing the information on the first quadrant, because these are going to be coming up so often. We want to make sure that we know them and that we don't try to memorize something that looks like this. Now, I haven't actually done this in a long time, but I provided this actually to my students. So therefore, they could just see how everything is relayed. But I have been pushing for students to make sure they knew the first quadrant for so many years, because I see students that just get so dependent on using the unit circle and they can't think for themselves. They just anytime they have to evaluate a trig function, they just automatically look at their unit circle. And then when it comes time for like a test or quiz and they don't have access to it, that's where they stumble. But this is the unit circle with all the values. And you can see trying to memorize something like this is crazy, right? Nobody wants to go ahead and do that. Yet memorizing something like this is really not that bad, right? And really my goal is not really to memorize anything, but it's just to keep on doing enough problems. So therefore you get really good at it and you basically kind of have it memorized by doing the work. But the main important thing is, well, why are we learning this again today, right? We already know sine. We already know these trigonometric functions. And you're right, like the sine in day 1 was opposite over hypotenuse. Did I already do this? No, I didn't. That's day 1. In day 3, we drew the triangles in the coordinate system, in the coordinate system, and therefore the sine of theta was the y coordinate over r, right? Still opposite over hypotenuse, but in terms of coordinate points, y or r, where r represented the distance away from the origin, which was also, known as the hypotenuse. So the nice thing here is if r is 1, I don't need to write it. That's why we just have sine is y, right? Like why write y over 1 when we could just write y? So that's kind of the nice thing about this is we don't really need to refer to 1. But the problem comes in is a lot of times, I'll give students a coordinate point. I'll say, evaluate the 6 trig functions. And like, for instance, they'll like take this point over here and they say, oh, the sine is the y coordinate, which is square root of 2. And it's like, no, remember guys, 45 degrees, like these coordinate points, this point, this point, this point, all have the same angle, 45 degrees. That means the sine needs to be exactly the same. So when the hypotenuse is 1, we know the sine is square root of 2 over 2, which we already knew from basic 45-degree triangles from day 1. So square root of 2 is not the sine of 45 degrees, right? It's the y coordinate over the hypotenuse. Square root of 2 over 2 is square root of 2 over 2. Here, square the y coordinate over the hypotenuse. So again, these points only work when you have a point on a circle with the unit circle, which we call the unit circle. So they only work is when we have a point on the unit circle. All right, so make sure if you're just taking the x and the y, or you're evaluating these new definitions, that you're only using them when you have points on the unit circle. And you can see 45 degrees for each of those is all going to be the same, square root of 2 over 2. One last point I would like to mention here is that the sine, of theta equals opposite over hypotenuse. And the cosecant of theta was hypotenuse over opposite. Now, another way we could look at those reciprocals is just putting them over 1, right? Since y is over 1 here, we could just think of cosecant of theta as 1 over y. But that's important because, for instance, if I had the, square root of 2 over 2, I want you to understand that 1 over square root of 2 over 2, if you just put it under 1, that is the same thing as flipping it. Okay? So a lot of times in previous lessons, we just, flip the fraction. But this definition kind of looks like taking the sign, wherever sign is put in under 1, which is, yes, that is correct. But don't forget like what we learned before, like the sine and the cosecant are reciprocals of each other. So if you have a fraction, or you can write the sine as a fraction or any trig function, a lot of times it's just going to be easier to reciprocate it to go ahead and get the value rather than putting it under 1. Because if you put it under 1, then, if you put it under 1, then you have the square root of 2 over 2. Then you're going to multiply by the reciprocal, which gives you now 2 square root of 2. So all I did was multiply by the reciprocal, which gave me back my answer anyways. So, a lot of people see these new definitions, and then instead of reciprocating fractions, they put it under 1 and they do this extra work. So I just wanted to kind of point that out. Last but not least, I wanted to point out one other thing is what about just like a random point? Like, we only have these points here. Why don't we have like a point right here? Actually, maybe I should just make sense of this. Like, why don't we have this point? Right? Where's that point? Like, what is that XY coordinate? And the thing is, well, we have that point. Like, you can actually evaluate that, but that's going to be some angle between 60 and 90. And that's not on our special right triangles. And for right now, we only know the sides of a triangle of our special right triangles. Those are the only triangles that we are referring to right now because we know them and we can use them without using a calculator. So, this could be, 70 degrees, 75 degrees, 80, like whatever it may be the case. But we will be getting with that, but that's going to be when we deal with calculators. For right now, we have these are all triangles. So therefore we can figure out what these coordinate points are. So that is what we are going to be using. So that is going to be for some later lessons. All right, so now let's get into some examples. Now, to evaluate the examples, we're going to look at the process. So the process that I have is for evaluating the 6 trigonometric functions given not a point, given an angle. All right, so the first thing we're going to do is we're going to sketch the angle in standard form. Then we're going to identify the reference angle. And again, these are all from day 2 in our lesson. Then we're going to determine the point given by the reference angle. So that is going to be, so basically we're looking at the point, and here's like, I think this is the important one. We're going to find the point given by the reference angle. Now, again, you might think of like, where's that point going to be, right? There's points in all of 4 quadrants. But if it's the point given by the reference angle, what is it we know about the reference angle? The reference angle is positive and then it's acute. That means the point of the reference angle has to be in the first quadrant. These are all basically our reference angles, right? Because reference angles have to be acute and they positive. That means it's going to be one of these. That's why I say only memorize these, because if you can figure out, what your reference angle is, you can find your coordinate point that you need. Then we're going to apply the sign based on the quadrant of the terminal side of the original angle to the point. Now that's a lot of words for really just saying apply the sign based on the quadrant the angle lies in. So obviously if the angle lies in the second quadrant, you're not going to, remember reference angle points are always positive. So if your angle though is in the second quadrant, you're going to make the x negative. If your angle lies in the third quadrant, then your point is actually, your x and y coordinates are actually both negative. And if your angle is in the fourth quadrant, then the y coordinate is going to be negative. So let me show you what I mean. And what I did is I kind of broke down each one of these steps and labeled them. Oh, I didn't finish these, I guess. So I evaluated 6 trig functions, I guess didn't finish it. So let's go ahead and do that. Did I not do? Yeah, I guess I just stopped. All right. So question number 1 is graph the angle. So I have 5 pi over 4, standard form, right? Going in the positive direction. Remember, the reference angle is the distance away from the x-axis, so from here to here. And you can say that theta prime is going to equal, I wrote it up there, but theta prime is equal to pi over 4. Now, you don't need to re-graph it over here, but again, I'm just showing you theta prime pi over 4, it's right there. That coordinate point is square root of 2 over 2, comma square root of 2 over 2. That is the coordinate point for the reference angle. You don't need to graph this, but I wanted you to see where I'm getting square root of 2 over 2. Yet, we know that the angle is in the fourth quadrant. So instead of using this point, we need to use this point where the x and the y are both negative. Now, again, we have an x and a y coordinate. We can use our new trigonometric function, our definitions. Sine is the y coordinate. Cosine is the x coordinate. Tangent is the y over x, which is 1. Cosecant is, again going to be 1 over y, right? You could write it like this. But what I mentioned to you is why do that when all you need to do is just, again, reciprocate this. And then you'd rationalize the denominator in case you forgot. I'm going to not do this again. Because potentially I'm hoping that you just get used to these answers here, which is going to be a negative square root of 2. You can see that's like a lot of work. And thankfully, since I already did it once for cosecant, I don't need to do it again for secant because these are going to be the same answers, obviously. Same thing with tangent. Why flip this the other way? I know that the cotangent of theta is just going to also equal positive 1. So again, graph the point, find the reference angle, find the point of the reference angle, and then apply the signs based on the quadrant, and then you can evaluate your 6 trigonometric functions. So let's go ahead and do some more examples. So the first one here is 45 degrees. So what I'm going to do is I'm just going to kind of show you the angle. So 45 degrees is right there. The coordinate point here is square root of 2 over 2. Square root of 2 over 2. So here's the angle. Basically, I'm going to provide you with the point that I'm using. So that's square root of 2, comma square root of 2 over 2. Reference angle is obviously 45 degrees, so it's already in the first quadrant, so that makes life easy. And therefore, it's basically going to be the same answers that we just did. So sine of theta is going to be the y coordinate, square root of 2 over 2. Cosine of theta is going to be square root of 2 over 2. Tangent of theta is going to be 1, right? Because y over x is just 1. Cosecant of theta, you can reciprocate these, right? 2 over square root of 2. Hopefully you recognize that's just the square root of 2. Or you could do the secant of theta. You could say that's equal to 1 over 2 square root of 2. But again, when you do the math, you get square root of 2. And then the cotangent of theta is equal to 1. The next one, 5 pi over 3. So let's go ahead and graph that again. There we go. So 5 pi over 3, so that's going to be in positive form. So halfway from here to here is 3 pi over 3, right? So 4 pi over 3, 5 pi over 3. Again, if you're breaking things up into thirds visually. Let's just do this real quick, just because this one still gets students. 1/3, 2/3, 3/3, 4/3, 5/3. Okay, so you can see how that works there. So that's 5/3. Let's look at the coordinate points here. So in the first quadrant, the coordinate point for pi thirds is going to be 1/2 common square root of 3 over 2. But since we're in the fourth quadrant, the point that we're going to be working with is 1/2 common negative square root of 3 over 2. All right, so you see the difference? Like you can see the reference angle, and I guess I should probably write this. The reference angle is just going to be pi over 3. So therefore that coordinate point for pi over 3 is this, but then it's in the fourth quadrant, so therefore that's negative. So now we have the sine of theta. It's going to be negative square root of 3 over 2. The cosine of theta is equal to 1/2. And the tangent of theta is going to be negative square root of 3 over 2 divided by 1/2, which hopefully you should start getting used to. You could multiply. I'm going to show my work here so then I don't have to do this again. You can multiply by the reciprocal. That goes to 1. That divides out. Negative square root of 3. The cosecant of theta, let's just flip this. So that's going to be negative 2 over square root of 3. Rationalize the denominator. For the secant of theta, that's going to just give me 2 over 1, which is 2. And then we have the lovely cotangent of theta, which is, equal to a negative 1 over square root of 3, which equals a negative square root of 3 over 3. Now, again, the important thing is, one thing I told students is when I'm looking in this fourth quadrant, I'm looking for your signs, right? I know that the y-coordinate is negative. That means sine, cosecant should be negative, and cotangent and tangent should be negative. Negative, 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 negative. But cosine and secant are going to be positive because they only deal with the x-coordinate and r, right? So therefore, those should be positive, which is good. All right, next one is 5 pi over 6. So again, that's going to be this angle right. No, don't do that. That's going to be that angle right there. We can say that theta prime is equal to pi over 6, which in the first quadrant, that gives us square root of 3 over 2, comma 1/2. Yet we're dealing with this point right here, which is going to be negative square root of 3 over 2, comma 1/2. So therefore, now let's go ahead and evaluate our sixth trig function. So the sine of theta equals positive 1/2. Cosine of theta equals negative square root of 3 over 2. And the tangent of theta is going to be the last one, 1/2 divided by, is going to be 1/2 divided by square root of 3 over 2. Now, I'm going to do this one more time. Multiply by the reciprocal. That goes to 1. The 2's divide out. You're left with 1 over square root of 3. Then you can rationalize the denominator. And you're going to get square root of 3 over 3. All right, I have now done the hard problem, so now I'm just going to give you the original ratio and then just move on. The cosecant of theta is equal to 2. The secant of theta, guys, we already did this, right? I already did this work. You flip it, so therefore it's going to equal a negative 2 square root of 3 over 3. All right, the last one is pi equals, or theta equals pi halves. So pi halves is right there, right? So this coordinate point is 0, comma 1. So again, what's nice about this unit circle, which actually I forgot to mention when I was doing more of the instruction, is now this doesn't create a triangle. We no longer need to rely on having a triangle to evaluate the 6 trigonometric functions. We can now evaluate these just based on a coordinate point on the unit circle. As long as we know the point is on the unit circle, we can apply those trigonometric definitions. So in this case, we have the sine of theta is equal to 1. Cosine of theta is equal to 0. And the tangent of theta is 1 over 0. Well, you can't divide by 0, so that's going to be undefined. So the cosecant of theta is 1 over 1, which is 1. The secant of theta, which is 1 over 0, which is, again, undefined. And the cotangent of theta is the x over the y, so it's 0 over 1, which is 0. So just remember, when we're dividing by 0, that's obviously going to give us a undefined value. But hopefully you guys kind of recognize here at least this process that I followed. And now we're just going to work through some more angles. For instance, negative angles. So again, when we do the negative angles, just remember we're going to be going in now in the negative direction. Doesn't change anything with our points. You know, obviously we're going to have different points here, but it doesn't make anything else negative, just changes our direction of our angle. So we go in the negative direction here. I have 0, comma, negative 1. I do not have a reference angle, but again, I don't need a reference angle because I already know the point on the unit circle. So in this case, cosine is 0, sine is negative 1, tangent is going to be y over x, which again is undefined. Secant is y over x, which is undefined. Cosecant is 1 over negative 1, which is negative 1, and cotangent is 0 over negative 1, which is 0. So let's go ahead and work through these. Again, really kind of the same process. So let's go and graph the angle, negative pi over 6. That means this reference angle for pi over 6 is going to be pi over 6, which gives us, if you're going to find the coordinate point for pi over 6, that's going to be square root of 3. Come on, come on. No, don't do that. Eliminate that. So that's pi over 6, so that coordinate point is square root of 3 over 2, comma 1/2. So that means this coordinate point, the one we're actually working on, is going to be positive square root of 3 over 2, comma negative 1/2. Okay, so the sine of pi over 6 is going to be negative 1/2. the cosine of pi over 6 is equal to the square root of 3 over 2. And the tangent of pi over 6 is going to be negative 1/2 over negative 1/2 over square root of 3 over 2, which I already solved, right? Where did I do that? It's one of these. Okay, I think I've solved all of these, so therefore now I'm just going to start giving you the answers there. So again, you can look at my work for previous to be able to figure that out. And that's going to be a negative square root of 3 over 3. Now, I do want you to understand there's a difference here. Why am I using sine of pi over 6 instead of sine of theta like I did over here? Well, it doesn't matter. You can do anything you really need to. You can see that in each of these examples, my angle theta was defined, right? Or 45 degrees was defined as theta. So I just used theta, and I actually didn't mention that, and I kind of forgot about that, and I apologize, because you could say sine of 45 degrees, cosine of 45 degrees, tangent of 45 degrees, sine of 5 pi over 3, cosine of 5 pi over 3, tangent of 5 pi over 3. But even saying it is a lot. Writing it is a lot as well. The one thing you do not want to do is what one of my students asked me is, can we just like not write the thetas and just do sine, cosine, tangent? And I said, no, because remember, these are functions. They are functions of an angle. So if you don't have the function of the angle, then you are writing you're writing it completely wrong. So you have to make sure you have an angle. A lot of times students don't want to write the angle for every single time, so we just use theta. Sine, cosine, tangent. Therefore, the cosecant of pi over 6 is going to equal a negative 2. The secant of pi over 6 is equal to 2 square root of 3 over 3. And the cotangent of pi over 6 is going to be reciprocal of that, which is just negative square root of 3. And again, this is in the fourth quadrant. So I know my sine and cosecant should be negative. My cosine, my secant should be positive. My tangent, my cotangent should be negative. Now, I wrote this because it wasn't really too bad to write pi over 6, but I'm not going to use negative 4 pi over 3. I'm just going to use theta in this case. Because again, remember, theta is equal to negative 4 pi over 3. They're interchangeable, right? So let's go and graph negative 4 pi over 3. So that's a negative version. So here's 3 pi over 3, right? So negative 4 pi over 3 is right there. So again, we have a reference angle of pi over 3, which over here, pi over 3 gives us the coordinate point, positive 1/2, square root of 3 over 2. So over here, it's going to be a negative 1/2, comma square root of 3 over 2. And now we have our coordinate point in the correct quadrant. Let's evaluate the 6 trigonometric functions. So we have sine of theta, right? I don't want to use that. Sine of theta is, oh, I forgot to mention that though, didn't I? Did I mention that? Yeah, that was on there. Did I skip something? Hold on a second. I totally forgot to mention this. Oh my God. All right. I like skipped over this trigonometric functions. All right, let me go and do this, and I have one point that I need to mention. Sorry about that. So in this case, we have sine of theta. Sine of theta is equal to the y coordinate, which is square root of 3 over 2. The cosine of theta is equal to negative 1/2. The tangent of theta is going to be y over x, which is negative square root of 3. The cosecant of theta, which is going to be reciprocal here, which is 2 radical 3 over 3. You can see how I'm starting to do things a little bit quicker because it just is a lot to write. Secant of theta is negative 2, and it's the same thing over and over again, right? I don't need to show my work of simplifying the same problem 5 times. Like once you do it once, you have an example, and then we can just kind of repeat that. The cotangent of theta then is just going to be negative square root of 3 over 3. Now, let me go and take a quick, no, let's finish this one and then we'll go over. So then we have negative 3 pi over 4. Actually, I'll do that at the end. So let's do negative 3 pi over 4. So that's going to be right there, right? So the reference angle is going to be how far it is away from the x-axis, which is going to be pi over 4, right? Because if you travel negative 3 pi over 4, you need to go pi over 4 more to get to the x-axis. So that coordinate point is square root of 2 over 2, comma, square root of 2 over 2. Well, the point that we're working on is going to be negative square root of 2 over 2, comma, square root of 2 over 2. So let's go and evaluate these 6 trig functions. So the sine of theta, because I don't want to write negative 3 pi over 4 every time. The sine of theta is going to be square root of, that's both negatives. It's going to be negative square root of 2 over 2. Cosine of theta is going to be a negative square root of 2 over 2. And hopefully you remember this answer. The tangent of theta is going to be a positive 1. The cosecant of theta is going to be the reciprocal of that, which ends up being negative square root of 2. The secant of theta, which is the reciprocal of that, is negative square root of 2. And then last but not least, guys, the cotangent of theta is just going to be positive 1. So again, this is already some ratios that we've already simplified earlier. The only difference now is, you can see they're in the fourth quadrant, so we just want to make sure we have the correct signs. Last but not least here, we have a negative angle, negative 2 pi. So this one is going to be all the way around right there, which is going to produce this coordinate point 1, 0. It's not, doesn't have a reference angle, right? The angle is 0, but we still need to evaluate here for the x and the y coordinate. And again, that's one thing I kind of forgot to kind of mention here is, when you're doing these, the reason why I'm evaluating these is because based on the x and y coordinates, right? These are the x and y coordinates that I'm using for each of these ratios. And I should mention that, at least in my examples. Did I mention that over here for the example? Yeah, I mentioned that for the x and y there. So at least I show my work, so that's at least good. All right, so now we have this coordinate point. Let's go and evaluate our 6 trig functions. So the sine of theta, you could use 2 pi. Let's just use, I don't want to use that. You could write negative 2 pi, right? But it's a little more. So sine of 2 pi. Oh, this is negative pi over 6, isn't it? That's why I don't like writing the angles, because it's so much more work. Theta is much easier. So the sine of theta is negative 2 pi, which is going to be 0. The cosine of theta is going to be 1. The tangent of theta is 0 over 1, which is just 0. Let's see here. The cosecant of theta, which is 1 over 0, which is undefined. I don't really like how that's out of the way now. The secant of theta, which is 1 over 1, which is 1. And the cotangent of theta, which is 1 over 0, which is, again, undefined. Okay, so you can, again, see when you have these coordinate points on the axes, you're going to have some undefined values. All right, last but not least here, our last round of examples is going to be angles that are larger than a revolution. So what I did is I kind of did this a couple ways. First way was the old school way, the way that I first taught you how to graph angles in day 2, which is basically like take the circle or take half a circle pi, right, and break it up into 3 parts, 3 pi and 6 pi, right? Break it up into fractions, and then you can just count, right? So, we go all the way around. This is negative, right? So it's negative 3 pi over 3, negative 6 pi over 3, negative 9 pi over 3, negative 12 pi over 3, negative 13 pi over 3, negative 14 pi over 3. And you can see that's kind of like a lot of work. And especially like, what if I gave you something like 148 pi over 3? You're not going to want to count to, 148 to graph the angle. So one thing we can do is use period as an aid, use an extra revolution. And so what's happening here is if you look at this graphically, I went around the circle once, and then I went around the circle again. And then I went around the circle negative 2 pi over 3. So obviously, this angle and this angle are not the same, right? If you run around a track, you want credit for running around the track. Yet you begin and you end at the same places, right? You start here, you end here. You start here and you end there. So therefore, these are coterminal angles. And what's important about these is what I wanted to discuss earlier, is that they have the same coordinate point on the unit circle. Therefore, their 6 trigonometric functions are the same. So while if I ask you to graph this, you need to make sure you have those extra revolutions, when we're looking into evaluating the 6 trigonometric functions, we don't care about these extra revolutions, right? We don't care about negative 6 pi over 3 going around twice. We just want to know, where are you ending up? Which quadrant are you ending up on? What is the reference angle where you ended up on? So we can evaluate the coordinate point. Again, you can see right here, negative 14 pi over 3 and negative 2 pi over 3 are coterminal. They have the same initial and terminal side. So therefore, since they're coterminal, they're going to have the same reference angle and the same coordinate point on the unit circle. But again, since they're in quadrant 3, therefore we're going to be using negative 1/2 and negative square root of 3, right? So again, you could do this, the graphical approach. I prefer just to find a revolution, right? We know that 2 pi in terms of thirds is equal to 6 pi over 3, right? So therefore, the hard part about this problem was it's negative. So you don't want to add 6 pi plus 6 pi. You got to use negative 6 pi over 3 because you're using the negative direction. And then when you keep on finding them, you basically just find the remainder, and that's going to be your coterminal angle. So therefore, I have In this case, negative square root of 3 over 2, negative 1/2. I simplify, and again, you see in the third quadrant. So sine, cosecant, secant, and sine, cosine, cosecant, and secant should all be negative, which I forgot to write a negative there. See how that's a good check. Yet tangent and cotangent should be positive, which they are. Okay, so that's really the only difference. What we're going to do is just kind of rewrite these. You could graph them, you know, and I'll graph them. That's, you know, fine. But I am going to also just kind of rewrite the angles so that we can better understand them. So 13 pi over 3, we know all the way around is 12 pi over 3 plus an extra pi over 6, I'm sorry. The nice thing, though, is that gives us a point in the unit circle, right? So that's 12 pi over 6 plus pi over 6. Right? So we can cancel out that extra revolution if we wanted to. Theta prime equals pi over 6. Well, our coordinate points for that is going to be square root of 3 over 2, comma 1/2. So we have the sine. Again, I don't really want to write 13 pi over 6, so I'm just going to use theta. Sine of 13 pi over 6 is 1/2. Cosine of 13 pi over 6 is square root of 3 over 2. And the tangent of theta is going to be y over x. So that's going to be 1/2 over square root of 3 over 2, which when you simplify will give you square root of 3 over 3. For the cosecant of theta, that's going to be 2. Secant of theta is going to be 2 radical 3 over 3. And the cotangent of theta equals the square root of 3. And again, everything's positive because we know it's in the right quadrant. I'm not showing a lot of my work here because I've already showed the work, right? All right, let's go ahead and graph negative 420 degrees. Well, negative 360 is right there, right? So then I need to add another 60 degrees to get me to that. Or you could just write this as negative 360 degrees plus negative 60 degrees. Right? And therefore we recognize then since we went 60 degrees past the x-axis, our reference angle is going to be 60 degrees. So therefore the coordinate point at 60 degrees is 1/2 square root of 3 over 2, but that's in the first quadrant. We are in the fourth quadrant, so therefore my y coordinate is going to be negative. So now let's evaluate the 6 trig functions from here. So we'll have the sine of, I don't want to write negative 420, so I'm just going to use theta. So the sine is going to be negative square root of 3 over 2. Cosine of theta is 1/2. Tangent of theta is now going to be sine over cosine, so now it's the flip version of that, which is just going to be square root of 3. Yet it's in the fourth quadrant, so it's a y over a negative, so that's a negative square root of 3. The cosecant of theta is, again, we already know that reciprocal, so that's going to be negative 2 square root of 3 over 3. The secant of theta is going to be a positive 2, and the cotangent of theta is going to be the reciprocal of square root of 3, which is square root of 3 over 3. There you go. All right, let's do another one, 11 pi over 4. So 11 pi over 4, it's going to be in the positive direction. Well, here is 8 pi over 4, right? And then you could do 9 pi, 10 pi, 11 pi. 11 pi right there. So an extra 3 pi over 4. All right, or we could just write that as a revolution. 8 pi over 4 plus 3 pi over 4. From there, we recognize that the reference angle is going to be pi over 4. So the coordinate point over here is going to be square root of 2 over 2, comma, square root of 2 over 2. Therefore, for this point, it's going to be a negative square root of 2 over 2, comma, positive square root of 2 over 2. So now let's just evaluate the 6 trig functions. So again, we have sine of 11 pi over 4, but let's just use theta. That's going to be a positive square root of 2 over 2. The cosine of theta is going to be a negative square root of 2 over 2, and the tangent of theta is going to be y over x, which is now going to be a negative 1. For the cosecant of theta, that's going to be the reciprocal, which hopefully you remember is square root of 2. The secant of theta is that reciprocal, but in this case it's negative since it's in the second quadrant. And the cotangent of theta in this case is going to be, obviously, again, another negative 1. All right, in the last case here, again, we have 3 pi, so that's going to be all the way around circle is 2 pi. And then we're just going to go an extra pi, which gives us to our point negative 1, 0. Or you could also write this as 2 pi plus pi. right? You did the extra revolution, but then you're back there. All right, so we have our coordinate point, no reference angle. So the sine of, let's just write it as 3 pi. That's not too hard to write, right? The sine of 3 pi is 0. The cosine of 3 pi is going to be -1. And the tangent of 3 pi is going to be 0 over -1, which is 0. The cosecant of 3 pi is going to be 1 over 0, which is obviously undefined. The secant of 3 pi is going to be 1 over -1, which is -1. And the cotangent of 3 pi is going to be -1 over 0, which again is going to be undefined. Now, before I get to the final reflection, I just wanted to kind of highlight this slide that I did not talk about, that I showed some work on. And this was something before the process, because this is one of those, this is something I wanted you to take away from this. So before I actually gave students a process, I said, why don't we graph the angles, find the reference angle, determine the quadrant, and then determine the point on the unit circle. So we actually practiced this before we went into the problems. And the point that I wanted to make with the students was that, you know, here the reference angles are the same. Pi over 6 and 5 over 6 have the same reference angle, right? And since they have the same reference angle, the coordinate points are the same. And since their coordinate points are exactly the same, you can see that the only difference is, again, the signs based on which quadrant they're in. But in this case, you can see that the sine is both the same at 1/2. So what that really means now is that the sine of pi over 6 is equal to the sine of 5 pi over 6, right? All the other trigonometric functions are going to be different signs. But for these two angles, you can see that the sine is equal to each other. In this case, in the second and the third quadrant, you recognize, again, same coordinate points, same reference angle. The only difference here is the y coordinates, because one's, you know, in the second, one's in the third. But the cosine is the same for both of them. So therefore, the cosine of 2 pi over 3 is equal to the cosine of -2 pi over 3. Because again, the only difference is, there is no difference with the cosine. They're both in -1/2. And then we look at these two triangles. Again, they have the same reference angle, so therefore they have the same coordinate points. They're in different quadrants, so this is positive, positive. This is negative, negative. But again, the tangent is going to be the same for them. So therefore, the tangent of -3 pi over 4 is equal to the tangent of pi over 4. So that's that kind of relationship that I just wanted students to understand. If you understand the quadrants that they're in, you understand these positive and negatives of these points, you're going to understand that relationship for the trigonometric functions. And then last but not least, the most important one is 90 degrees and 450 degrees. Those are the exact same points. Those are coterminal. And this is something that we investigated on our own because we didn't talk about it before. But of course, guys, coterminal angles, since they have the same coordinate, since they start and end at the same spot, they're going to have the same coordinate point on the unit circle, and therefore the 6 trigonometric functions are going to be exactly the same. That's why it was so important in our last example just to find a coterminal angle that worked for us, because you know, you could use these large angles, but if you just use period A's to reduce them to a coterminal angle that we're more familiar with, it's a little bit easier to evaluate the unit circle, define the reference angle, and so on and so forth. But again, guys, hopefully from this lesson, you understand a little bit more about where these points come from on the unit circle. They're not just made up points. They come from special right triangles placed on a coordinate grid when the hypotenuse is 1. And again, since the hypotenuse is 1, our trigonometric functions now can just be the coordinates of those coordinate points. We don't need to include the hypotenuse any longer for our definitions, which makes everything a little bit easier and more efficient when evaluating the 6 trigonometric functions. So hopefully you guys enjoyed. If you have any questions from this lesson or some things that you would like a little more clarifications on, please feel free to comment down below, and I look forward to seeing you guys on the next video. Cheers. Welcome, ladies and gentlemen. My name is Brad McLogan, and in this video, we're going to work on graphing trigonometric functions. Now, this is actually the 5th day in our chapter for trigonometry, and I'm actually not going to graph the trigonometric functions, but I'm going to help you identify all the parts you need to know, so therefore, if you need to graph them, you can. So part of the parts that we're going to figure out is we're going to identify what the graphs look like, so we can see these kind of parent graphs for sine, cosine, and tangent, and then we're going to learn how to basically identify the parts. So for sine and cosine, that's going to be amplitude, period, phase shift, vertical transformation, domain, and range. And then for tangent, it's basically just going to be the exact same, but we're going to add add in the vertical asymptotes, as well as there is no amplitude for that. So we'll get to that once we get to the vocabulary part of the lesson. But before we do that, I wanted the students to investigate and kind of see where these graphs come from. How do we create these graphs? So therefore, they know that they can recreate them really at any time without having to like memorize the graphs, which sometimes people get them confused. So it's important to understand where these graphs come from. So what I did is I gave the students a whole bunch of angles. All these angles actually are from the unit circle. And I basically gave them out some cards and said, let's evaluate for the sine, the cosine, and the tangent of all of these angles. Now, I didn't ask every student to do each and every one, but I gave them, a couple of each one, and then we went ahead and plotted them. Now, obviously, when you plug in like the sine of pi over 6, that gives you 1/2. So therefore, you could plot that on an xy axis. However, the sine of pi over 3 is going to be square root of 3 over 2. So I just gave them the decimal equivalent, 0.86. So therefore, they could draw this on an xy axis. So, basically, when we're evaluating the trigonometric functions, remember, we can evaluate those for those angles based on points on the unit circle. So therefore, the sine of theta was y, the cosine of theta was x, and the tangent of theta is y over x. So that is for each one of those trig functions of an angle represents those coordinates on the unit circle. But then what we kind of did, and it's kind of tricky, is then what we did is we took those coordinate points and we plotted them on an xy axis. So here is an example of what sine looks like. Now, if you have y equals sine of theta, now again, that's kind of the same thing as y equals like sine of x, right? I mean, but I don't want to confuse you with the x and y being the x and y from the unit circle to being the x and y here, because the x is the same thing as the theta. It's the angle, right? So that's the input of these functions, because remember, trigonometric functions are functions. You have the input and you have the output. So in this example, sine of theta, this is going to be our theta axis. And you can see our theta axis, which is also known as the x-axis, is represented by angles, all right? Now, these angles, for each one of these angles, as I mentioned, you can find a point on the unit circle, and that's how we found the output value. So, for sine, the output value is the y-coordinate of each of the points on the unit circle relative to the angles. So, for instance, let me just do kind of one here. For instance, sine of pi over 6. Well, here's pi over 6. So if I, for instance, I gave students like sine of pi over 6. So that coordinate point for pi over 6, that coordinate point is going to be square root of 3 over 2, comma 1/2. Okay, so if I wanted to plot this point, pi over 6 is going to be my input variable. So basically what we're doing is we're graphing a input variable and a output variable. So theta is my input variable, which is pi over 6. And then my output is, what is the sine of pi over 6? Well, remember, when we have a point on the unit circle, the sine represents the y-coordinate. So my output value ended up being 1/2. And that's how I plotted that point. And if you plot all of these points, you can kind of see we have a general shape. Now, just to note, my scale is not really proper because, some of these points are going to be a lot closer to each other than others. This is not actually evenly distributed like this. But I just wanted to kind of give, this is the only scaling that I could create, so I just wanted to have something. But, excuse me, if we go ahead and connect these, you can kind of see we have this nice little curve. And this is one thing that we kind of talked about in the class is like the shape, right? So this represents going all the way around the circle, right? This represents finding all these angles around the circle. These are all those output values. So there's a couple things that should make sense. One, it has a maximum point of 1 and a minimum point of -1, which makes sense, right? Because if you're looking at all the x and y coordinates, right? Or actually sine is just y coordinates. So if you're looking at all the sine coordinates, the farthest the y coordinate is, right, away from the origin is 1, right? Which is like right up there, 0, 1. It doesn't get any larger or farther away than 1. And again, that makes sense because the unit circle has a radius of 1, right? So that's why we have this max and min is 1. But we recognize, though, we can also go around the unit circle. Again, like this is just one revolution. After we do one revolution, we're going to start hitting the same values again. So a couple important points is, one, this graph is going to continue in that direction and in that direction. So it starts repeating itself. Now, what we call this, how long it takes for the graph to repeat itself is 2 pi, which is basically one revolution. In addition, we could also start looking at some kind of symmetry. So it's a little bit easier to look at once you start zooming out from this graph. But obviously, if you take this graph and flip it over, you can see that it's not symmetrical about the y-axis. But actually, this graph, if you reflect this about the x and then the y-axis, it makes sense that there's going to be a point down there at negative pi halves, negative 1, because you can kind of see that. And we'll look at the graph, and you'll be able to kind of visualize that a little bit easier. But for right now, we recognize that this does have symmetry about the origin, so therefore sine is odd. We see that there's a maximum point of 1 and a minimum point of negative 1. So it's also bounded. This is an absolute maximum and this is an absolute minimum. We can also see that the increasing, decreasing intervals keep on changing. We're not going to spend too much time really on that, but that is something just kind of important to remember. And then also we see that the graph kind of continues, right? And there's no discontinuities, right? There's no reason for any angle for us to have an undefined value, right? We've already talked about undefined values so far in this class as far as dividing by 0 and taking the square root of a negative number. Well, when you're just looking at the y coordinates of points on the unit circle, you're never going to be dividing by 0 for sine, right? So therefore, we're going to be defined for all angles, meaning that the domain of this graph is going to be all real numbers. So then we did the same thing for cosine. Now, again, really the only difference is cosine just represented the x-coordinates, right? And we can see that the graph looks very similar to the sine. So, now this is the x-coordinate, or y equals cosine of theta. So again, we have our theta axis and our y-axis. And again, my graph is not supposed to be perfect, but hopefully you guys can kind of see the general idea of what it looks like. And when we put these, together next to each other, when we put these, angles onto it, it looks like they're just kind of a shift over, all right? But again, same thing, like we're going around the unit circle. This is just going around the unit circle once, again, representing the x-coordinates. But what's important about this, though, as well, is if we, continue this graph, as you can see, it's going to kind of take that shape, which looks like it actually has symmetry about the y-axis, which in that case means that the function is going to be even. So that's something, again, important. We'll talk more about that later. But you can kind of see that if you continue the pattern, it looks like it's going to be symmetrical about the y-axis. Same kind of thing. There's a maximum point of 1 and a minimum point of negative 1, which again, like if you look at the unit circle, those come on, move that. There we go. If you look at like the unit circle, the points on the unit circle, the farthest x-coordinate is going to be 1, right? It doesn't get any farther away than 1 on the unit circle. So that's why we have that maximum and that minimum point. And again, like it's equal to 1 at 0 and it's equal to negative 1 at pi, right? And a lot of times people did make some wrong points, and I'll kind of explain how it's really easy to determine. Sometimes, I had a student that was, the point was like right here, or they had a point, up here. And so one of the things that we could check our work with, and again, this is one of the things that, again, is making that relationship that I want students to understand with the sine and the cosine graphs based on where they come from. So where they come from, or again, what you look at is like, let's look in this first coordinate. In this first quadrant, right, for all the angles in the first quadrant, which is basically angle 0 to pi halves, all the x-coordinates are positive, right? And you can see the graph is represented by all positive values. However, once we go from pi halves to pi, right, all the angles, pi halves to pi, you can see the x-coordinates are all negative. And look at these y-coordinates here are all negative. Then we go from pi to 3 pi halves. Again, the x-coordinates are negative, and you can see how these output values here are negative. And then once we get from 3 pi halves to 2 pi, you can see the output values are going to be, again, positive. I know it sometimes gets confusing using x and y's kind of like interchangeably for both of them. So that's why I'm trying to use like input, output. Like input is theta, output is this y-coordinate of the graph, not to be confused with the y-coordinate on the unit circle, right? And you can see how that plays out as well with the sine. From 0 to pi, right, sine is always positive. And then from, pi to 2 pi, you can see how the y-coordinates of the unit circle are all negative, right? And that's why those produce those output values to be negative. The other thing, just a real quick, I forgot to mention, you can see that I didn't write down these coordinate points. Square root of 3 over 2 is 0.86. Square root of 2 over 2 is 0.70. So that you can see those are the tick marks represented right there. And I didn't do that for tangent as well, did I? My bad. So let's see. There was the square root of 3 over 3. And then there's a square root of 3. And I forgot to mention that. I forgot to put that in there. So the square root of 3 is 1.73. And the square root of 3 divided by 3, oh, come on. What? Square root of 3, and then divide that by 3. Yeah, 0.57. Okay, that was 0.57. So you can see that's where those tick marks kind of came in, just so you can kind of see. So here we went ahead and did the tangent graph. So they did the same thing. Now, students, a lot of times they had trouble. Typically, students had trouble, and this one was obviously with pi halves and 3 pi halves. So we have to kind of understand, again, what are we doing with pi halves and 3 pi halves? So tangent of x, or we could look at that at tangent of theta. Okay, so again, I think it's really important, again, if you understand the unit circle here, what is going on? Right? So at pi halves, this coordinate point here is 0, 1. That means the tangent y over x. It's undefined, right? And so it's like, well, what do I graph when it's undefined? And the best answer is nothing, right? It's undefined. You don't put anything there. However, in graphing, you know, if you were to graph this graphing calculator is not going to put anything. Desmos online doesn't put anything there. However, we do want to represent like what exactly is going on. Like it is a discontinuity. Is it a hole? Is it removable? Is it an asymptote? Is it non-removable? And in this case, we can see that it doesn't really look like it's anything going to be removable. So we're going to represent it as an asymptote. And therefore we can just show that it's a dotted line, just so we know that not only is it a discontinuity, like it's undefined, but we can see that this graph is going to be approaching the asymptote, right? And that's the important thing about understanding it's an asymptote, is that this function is going to be approaching the asymptote. And that's the same thing for 3 pi halves. Over here, that coordinate point is 0, 1, right? So you can see that the, again, -1 over 0 is undefined. Now, again, students made the same kind of mistakes. They made positive points when they should have been negative. But again, if we understand that tangent is positive in the first quadrant, negative in the second, positive in the third, and negative in the fourth, we can double check our answers. Besides that, the other one was just doing the ratios, which again, we're going to get, more familiar with evaluating for all these angles. But again, here, when the angle is in the first quadrant, all my output should be positive. From the second quadrant, pi halves, to pi, my output value should be negative. From pi to 3 pi halves, which is the third quadrant, my output values are positive. And then from 3 pi halves to 2 pi, you can see my output values are again negative. Now, I want to kind of, again, as I mentioned, guys, my scaling is not ideal here, right? So I'm trying to just do my best to kind of show you guys, but it looks like this kind of S curve that's going on. And again, the scaling is way off, guys. These are not evenly distributed scaling. So besides overlooking that part, there's something that's important that's going on, because tangent looks absolutely nothing like sine and cosine. Sine and cosine, right, kind of have this nice little ups and downs, little ebb and flows. There's no discontinuities. We can see that after we've traveled 2 pi, the graph starts repeating itself again, right? Because that's going around the unit circle. And it's nice, it's just like this nice little wave here. Whereas the tangent, we obviously have undefined values because, again, that makes sense. It's the ratio of y over x, and x can be 0, especially at pi halves and 3 pi halves here. It looks like it's always increasing. It's not changing from increasing and decreasing. And it looks like it does repeat itself. It's kind of odd to kind of see this repetition here. But if you kind of look at it, like that looks like the other part right there. Like if I were to expand this out, like if I was to keep on going around the unit circle, it looks like the next thing I would do would be continuing this graph like over here. So it does look like it repeats. Then we need to kind of understand, well, how long does it take to repeat? Is it 2 pi or is it shorter? And it looks like, really you're just getting this little S curve. So what is the length of the S curve? And you could say, well, from pi halves to pi, like how far is it from here to here? Well, hopefully you can see that pi halves plus pi, right, or 2 pi over 2 gives you 3 pi halves. Another way you can confirm that is it looks like the asymptotes are occurring every pi. Like here's pi halves, you add half of a circle, which is pi, then you add half a circle again, which is pi, half a circle, which is pi, and you can keep on adding pi. Now, that brings up to our next point is, well, then how can we identify all these asymptotes here, right? Because it looks like there's a lot of asymptotes going on. And I don't really want to write down all the asymptotes, but let's try to maybe make sense of them. So we know that the first asymptote occurs at pi halves. And then the next one occurs at 3 pi halves. And then if you add, again, pi, you'd have 5 pi halves, 7 pi halves, 9 pi halves. And then you realize, wow, I can keep on adding repeatedly, like keep on adding pi continuously. So how can I represent repeated addition? And that the answer is multiplication, right? Well, how many times, what am I going to multiply by? Like how many times could I, keep on adding pi? And we don't know, right? It's an unknown. You can do infinite many times. You can go around there infinite many times. So to represent an unknown that can go all the way up to infinity, we can multiply pi by the variable n. And n just basically represents the number of times you can add n or subtract n, right? Because n can be negative. And again, let's kind of make this case. Let's say n is 0. That means there's a vertical asymptote at pi halves plus 0, which is pi halves. Got it. What if n is 1? Well, if n is 1, that's going to be pi halves plus pi, which is 3 pi halves, right? And then what if n is 2? Well, that'd be, again, going to give us 5 pi halves, which kind of makes sense. That's the next asymptote. What about if n was negative 1? Well, that'd be pi halves plus negative pi, which ends up giving us negative pi halves, which looks like based on this symmetry is going to work. And the symmetry might not be obvious in this case as well. So what we're going to do is we're going to look at this graph in a little bit different direction. And that's what we call with our parent functions using the initial period. So, the whole purpose of me doing this, probably took like 30 minutes of my class to kind of go through this, is because I really wanted students to understand where the graph came up. But if students really want to graph it, I'm not going to expect them to plot all those points. Like, it's kind of crazy. However, I think if any time a student is confused or kind of forgetting about what the graph looks like, they can always remember this portion of the unit circle. And then from here, they can represent the initial period of a trigonometric function. Again, these are the trigonometric functions, just looking at the first revolution, right, from 0 to 2 pi, except for the tangent one. And just using these 4 points, these 4 angles, 0, pi halves, pi, and 3 pi halves, and 2 pi, I'm sorry, so I guess 5 angles. But using those angles, you can easily plot those points and then just make the connections, understand where the max and the mins are and where the x-intercepts are. And again, you can just see like, the y, this represents all the y coordinates for each angle, like 0, 0, pi halves, 1, pi, 0, 3 pi halves, negative 1, 2 pi, 0. This one represents the x coordinates of these points at 0, 1, at pi halves, 0. So you can kind of see how that relates. Now, tangent doesn't really seem like, that last graph was kind of confusing. So what we do for tangent is we still want to get like an actual full S-curve between 2 asymptotes. But rather than doing between pi halves and 3 pi halves, if we actually look at between negative pi halves and 0 and pi halves, we still get that nice full asymptote, right? And instead of doing a revolution of the unit circle, it's really just half revolution positive and then half the revolution negative here. It still gives you a full period, but I think it's a little bit nicer. You can just kind of see how that full version of it is. And from there, you can also see that we already confirmed that negative pi half was an asymptote. But also in this case, what we can see though, is that the graph is odd. It's symmetrical about the origin, like reflect about the x-axis, reflect about the y-axis, you're going to get the exact same graph. So, but just remember, these are just the initial period, right? These graphs continue indefinitely in both directions, positive and negative, because again, they come from the values of the unit circle, right? So you can keep on going around the unit circle in the positive or in the negative direction. All right, but now what we want to do is, now as we get into the graphing portion, what I want to do is just remind students is like, what do we already know? We already know transformations of functions. That's something that we've already covered in this class. So, if I give you a trigonometric function, it doesn't matter if it's sine, cosine, tangent, or if it's not a trigonometric function, if it's x squared, x cubed, square root of x, cube root of x, e to the x, ln of x, like 1 over x, it doesn't matter the function. If you're multiplying on the outside by 2, that is going to be stretching the graph vertically. If you're multiplying by a factor between 0 and 1, that's going to be vertically compressing the graph. If you are multiplying by negative on the outside of the function, that's going to reflect about the x-axis. If you're adding 1 outside the function, that's going to shift it up. And if you're subtracting 1, that's going to be shifting the graph down. Notice that all of those transformations are all outside and they all impact the graph vertically. So again, just to kind of reiterate, make sure we're really good with this. Let's go and just take a look at Desmos just to kind of verify all of this stuff. Okay, so on to Desmos. What I did is I plot a lot of this stuff in here. So in this case, I have sine of x. And you can see, like, we only talked about the initial period, right? Between 0 and 2 pi, which would be like 6.28. That was our initial period. But obviously, you can see that this graph, how it like expands out as you zoom out, right? So it keeps on going on forever, just continuing that same pattern. All right. So a couple things again. Let's go through this. Multiplying by 2, that is going to be vertically stretching the graph, right? See how it vertically stretches it. Here we have this horizontal compression. Okay, when we multiply by a negative, that's going to reflect about the y-axis. Okay, adding 1, that's shifting the graph up 1. See how everything moves up 1, everything moves down 1. So again, notice how everything that I just did is a vertical shift upward, or is a vertical transformation, right? Then the next slide, we talked about these cosine ones. So I went over and gave them the cosine graphs. And just to kind of save some time, we'll just look at cosine. So here's the cosine graph. Again, now we can put them in because my class got to see this. But you can see, here's the sine and the cosine graph. You can see that they're very similar to each other, right? It's basically the exact same graph, just kind of shifted over. And that's something we'll talk about really in next chapter as far as understanding a little bit more of that relationship. But but let's go and focus on cosine here. So now we're looking at the operations, inside the function. So we know multiplying by 2 outside, we're vertically stretching it. So if we multiply by 2 on the inside, that's going to have the same operation, but it's going to be horizontal. So how can we like stretch it vertically, but horizontally? Well, that's going to be a horizontal compression. And let's kind of see. Yeah, right? Now, again, something's interesting. The distance it took for the graph to repeat itself just got shrunk, right? Instead of it being from here to here, now it's from here to here. So this horizontal compression changed how fast the graph repeated itself, which is something we'll talk about. Then you can see here when we divide by 2 or multiply by 1/2, you can see that there's horizontally stretching the graph, right? Kind of like a vertical compression. Not the same, but it's that same kind of, same kind of idea. It's being horizontally stretched. You can see that also that changes again how long it takes the graph to repeat itself. All right. Obviously, we have the negative reflection, and I was kind of like, having fun with students, making some jokes. But you can notice that this graph is symmetrical about the y-axis. So if you flip this graph around the y-axis, you're not going to notice anything, right? Because it's an even function. However, though, just note that that is a reflection about the y-axis. And then obviously, if we're adding something inside of the function, remember that shifts it to the left, right? And we're going to verify this again. And if we are adding an angle, that's going to be shifting it to the right. So you can see how that graph is actually being shifted to the right. All right. And then the last one I wanted to show, the last slide that we talked about was the tangent. So let's go and look at the tangent function, which again, you remember, it doesn't show the asymptotes, right? But you could draw the asymptotes if you wanted to, like kind of draw the lines where they would be. But again, this repeats indefinitely. Okay. And you can see how that's why from 0 to 2 pi was like this portion, and then half of that. It's kind of weird. So you can see how this is like this nice little initial period between negative pi halves and pi halves right there. In this one, we want to look at the combinations, right? So my point that I'm trying to bring up is when I have negative tan of x minus 1, does that mean I shift the graph up 1 and then reflect it? Or should I reflect the graph and then shift it down 1? I'm sorry. Should that mean I shift it down 1, so it's down 1, and then reflect it, so therefore it's going to be up? Or should I reflect it first and then down 1? So again, when you're looking at a combination with a reflection and a vertical shift, follow the order of operations. If I wanted to evaluate the tangent of pi over 4, let's say. So at tangent of pi over 4, I'm going to evaluate tangent of pi over 4, which is 1. Then I'm going to multiply by negative 1, which is negative 1. Then I'm going to subtract 1. So again, you're following the order of operations. You're going to multiply by negative 1, which is the reflection first. Then you're going to subtract the 1, which ends up giving me a negative 2. So therefore, when you see at pi over 4, which would be somewhere over here, you can see that that's going to be equal negative 7.8, which if you remember on my point is negative 2. So they don't do it in radians, but you can see how that makes sense. So the graph is not up there. You don't shift it down and then reflect it back up. You reflect first and then move it down. The other one comes into, a lot of people remember, oh yeah, positive 1/2. So therefore it's, left pi halves. And then they say, well, this one's left pi halves. But again, be careful. You have to factor out the 1/2. This is, I'll show you actually in this. This is actually going to be pi to the left. And we'll look at this. But you can see it's not pi halves to the left. It's actually pi. So you can see negative pi halves to the left. All right. This one again, and again, I'll show you in the slides, you can see this. In this case, you have a reflection about the y-axis because that's a negative x, and you're actually shifting this pi to the fourth to the right. So this is actually a transformation to the right, not the left. So you can see how the graph got shifted to the right, and it's reflected because that's a negative x. And then this one that's actually going to be pi halves to the right. And again, guys, I'll show my work, but you can see how this graph actually got shifts pi halves to the right. Yeah, pi halves to the right, which actually, and then also there's a period change. So kind of look a little confusing, but the main thing is I want you to see like it's not the same graph just being shifted, pi over to the right. And I'll show you what we need to do again with that once we get back into the slides. So let's go and take a look at the slides because I think looking at the algebra for this is a little bit easier to be able to understand everything. Okay, so in this case, we're just going to investigate sine, although we could be using any one of them. So again, remember D, when a D is positive, that shifts the graph up. And D is negative, that shifts the graph down. Fairly basic one. Most students kind of remember that. Again, C though is one of them ones that students, a lot of times they still confuse. They don't understand why is it positive to the left and negative to the right. Well, again, notice as C gets positive, it's going to the right. Agreed? Stop. C is 2.5. It's moving 2.5 to the right. Again, if you were to place C with 2.5, the equation would be bx minus 2.5. So you can see how this equation, it looks like it's negative, but again, it's a positive C, so you're shifting it to the right. And as C gets more and more negative, you can see we're moving to the left. Where C is negative, we're moving to the left, and then stop. C is negative 1. Now, if I were to replace C with a negative 1, it'd be minus a negative 1, which we'd represent as positive 1, right? Minus a negative 1, positive 1. But you can see, again, it's shifting it to the left. All right, now let's go and take a look at the A. Keep on forgetting to switch those around. So again, A, remember, is that vertical stretch or compression. So when A is larger than 1, you can see how it's vertically stretching the graph. Now, it's very important for us to see this, that we're vertically stretching the graph, right? But again, notice that the x-intercepts, the zeros of the function are not changing, right? And if you remember, that was something really important that we talked about in polynomials. Like when we have scalars, that stretch or compression, that does not change the zeros, right? It just is a stretch of the graph. And then obviously when we get between 0 and 1, you can see how that's horizontally stretching the graph, but again, or vertically compressing the graph. But again, that vertical compression is not changing the zeros. And then obviously we get to 0, where A cannot be 0 because then we just have a line. But as we get to negative, you can see now it performs kind of the same way. Now there's something important that's happening here. When A is negative 2, look how low the graph goes, negative 2, and how high it goes, right? Which makes sense. We'll talk about that in another problem. But you can see when it's negative 2, the max to the min is negative 2 to 2. Yet when it's positive 2, again, it's the same thing from negative 2 to positive 2. So, either way, no matter what's happening, you can see how this stretch and compression is just really kind of changing with those graphs, but the x-intercepts are, again, remain the same. These are your scalars. But again, really notice that A really tells us how high and low the graph goes, and it doesn't matter if it's positive or if it's negative. Oh, I was trying to get to 0. But we don't want 0. We want 1, actually. All right, so then let's go and look at the 1. Okay, so when we're looking at 1, I need 1. Okay, when we're looking at B here, remember if B is going to be inside your function, right? So when B is larger than 1, what that's doing is that's compressing the graph, right? See that the distance it takes the graph to repeat itself, see how that's being compressed, right? And then when B is less than 1, you can see how that's a stretch. Now, either way, if I'm compressing or stretching, notice how the distance it takes the graph to repeat itself is changing, as well as the zeros, the x-intercepts is changing, okay? And then obviously you can see how that really just kind of reflects. Obviously when B is negative, you can see how the graph reflects about the y-axis, right? That wasn't as apparent with cosine, but you can see how we have that reflection that's going on. As a stretching, obviously when B is 0, you're getting a line, but you can see how that kind of works from there. And let's try to get to 1. Oh, almost. Okay, So that is basically it. Now let's kind of get into a little bit more of our formal definitions here before we actually get into some examples. Okay, so back to the notes. Let's talk about the parts of sine and cosine. So that distance, basically that max and min is basically kind of referred to as the amplitude. Really, the definition of amplitude is going to be the half distance from the max to the min. But if, as we mentioned, like when we see a 2 or a -2, that kind of tells us how high and low the graph goes, right? It goes, -2 is in front, it went down to -2, up to +2. When +2 was in front, it went down to -2 and +2. Now that's not always the same, and I'll explain a little bit more why that is the case. But it's just kind of important for us to understand from right now how that impacts the graph. It's a vertical stretch in both directions, really. So that's kind of the idea of the amplitude. It's the half distance from the max to the min. The period is actually the distance it takes the graph to repeat itself. So when we have these outside operations, that was not impacting the period, but only the inside ones. So you can see that's why it's 2 pi divided by the absolute value of b. The phase shift is basically the horizontal shift, how we're shifting left and right. The vertical transformation is basically the vertical shift, how you're shifting up and down. We know the domain is all real numbers. And then the range, I have this formula. I tell students, you guys can memorize the range if the form if you want to. But again, like look at the range here. For sine and cosine, it's -1 to 1, right? Well, if I shift the graph like up 1, then the range, now the lowest point, instead of the lowest point being -1, the lowest point is going to be 0, right? Instead of the highest point being 1, the highest point is going to be 2. So therefore, the range is basically whatever the amplitude, kind of like that idea, plus, so it's like A, -A, +A, and then either, adding for your shift up or you're going down for a shift down. So once we get into these examples, I think it'll make a little more sense. But again, like also remember period is, 2 pi, that's how long it takes the graph to repeat itself because that's a revolution around the circle. And obviously B is going to be horizontally compressing that or horizontally stretching that. So now let's go and take a look at the parts of tangent. So tangent is really, very similar as far as the transformations. However, the period is not going to be 2 pi divided by b. It's just pi divided by b because it only takes tangent pi to go ahead and start repeating itself. So the definition for the period for tangent is just going to be pi divided by absolute value b. The phase shift is c, and the vertical shift is going to be d. Now, we already talked about the vertical asymptotes. That's going to be pi halves plus pi n. The range, this one's kind of nice, that the range is from -infinity to infinity. That's why there's no amplitude here. Because again, if you look at the definition of amplitude, it's the half distance from the max to the min, right? Well, there is no max and min for tangent, right? It goes down and it goes up. So in this example, there is no amplitude. And as far as identifying the domain, this notation, which we haven't really used in my class, we basically just have done interval notation. This notation basically says all real numbers such that x cannot equal pi halves plus pi n. And again, that pi halves plus pi n is where the vertical asymptotes occur. All right. So those are kind of our 2 points here for the parts of sine and cosine and the tangent. And now we're just going to kind of get into some examples here. As I'm kind of working through these examples, if you want to go ahead and check, like look at the graph version, then you can always use that link. But otherwise, I'm just going to kind of knock out through these examples that we kind of covered. And then so you guys can kind of see the steps that we're going to do. But if you want to see the graph, because you need to actually graph them, for your class, or you want to know how to do that, you can kind of confirm the graph by using that link. All right, for the first example, we have y equals the sine of x plus pi plus 1. And again, the definitions that I'm using here is just going to be from our notes that we previously took, right? The sine and cosine here. Oh, a little fast. All right, so the amplitude, remember, is absolute value of a, which in this case is going to be 1. So you can see there's would be a 1 right there. So therefore, absolute value of 1 is just 1. That's the max min. The period, again, is how long it takes the graph to repeat itself. 2 pi divided by absolute value of b. Notice b, again, is the coefficient of x there. So that is, again, also going to be a 1. Let's try to do that a little better. All right. Let's put a dot there for that one, too. And so therefore 2 pi divided by 1 is just 2 pi. So basically this graph has not really changed at all, right? I mean, it's not being stretched, vertically compressed, or not being horizontally stretched or compressed. Yet though, we do have a phase shift. The graph is being shifted pi to the left, as well as there's vertical transformation up 1. So Using that information, though, we can identify there's no change in the domain, right? It doesn't matter. The domain's always a real number. So it doesn't matter what transformations happen. The domain's always going to be all real numbers. Yet the range, though, is going to be from 0 to 2. And the reason why is kind of what I explained. Like if the amplitude is 1, that means the graph goes down to -1 to +1. And if the graph is being shifted up 1, now the graph is going to be from 0 to 2. So again, if you want to verify the graphs or take a look at it, I have the link provided for you. And that will help you understand a little bit more what the graph is. But for kind of the sake of time, I'm going to work through all these, just identifying the parts of each graph. All right, so let's go ahead and just work on the parts of sine. So again, the amplitude here is just going to be the absolute value of 3/2, which is just going to be 3/2. Now 3/2 is a fraction, but it's larger than 1, so it's technically vertically stretching the graph. That means but the graph is still going to go up to 3/2 and then down to 3/2. The period is going to be 2 pi divided by the absolute value of -4, which is 2 pi divided by 4, which equals pi/2, right? So again, you can see that the graph started at, you can see the graph started at pi, and then it got compressed to pi/2, right? So you can see that period, how it got compressed. That's why that 4 is a compression. That also means that's a negative. That's a reflection about the y-axis. So I'm going to want to write that in there as well. So reflect the y-axis. There is no shifting left or right or up or down. However, the range changes by the amplitude, right? And again, we looked at this on Desmos. Like when that a was 2, it went down to 2, up to 2. So if a is 3/2, that means my range is going to be from -3/2 to 3/2. So the domain is just the same, but my range is going to be from -3/2 to 3/2. All right, let's look at the next one, which I guess I don't know why I didn't do sine. That's kind of weird. I'm going to add one of these. Sine one of those? Yeah, let's do, let's change this to a -1. Okay, let's look at the next one. The next one here has a amplitude. Wait, let me just double check. Sorry. Cosine, I did one of those. I wanted to do, did I do one for tangent? Please tell me I did this one for tangent. No, I didn't. Okay, I'm going to change this then. I'm going to do this one. There's a certain problem that I was looking for. Let's do this one, a -1. Okay, so in this case, again, we're just going to have a y equals, the amplitude is going to be the absolute value of -2. That was right. What am I doing? Which is just 2. The period in this case is going to be 2 pi divided by, now again, this one's kind of confusing because what's b, right? Is it a 1? Is it a 2? Or is it 1 divided by 2? Well, the answer is it's 1 divided by 2, right? Because x over 2 is equal to 1/2 x. So you can see dividing by 2 is the same thing as multiplying by 1/2. So now I'm just going to multiply by my reciprocal, and you can see my period is 4 pi. So instead of the period being at 2 pi, right, when you multiply by 1/2, it stretches the graph horizontally to 4 pi. There is no phase shift. There is no vertical transformation. Again, I am now reflecting the x-axis. Okay, so now I'm reflecting the x-axis, and then the domain is still the same. And the range, though, is now going to be from -2 to +2. All right, last one here. Again, I'm adding this shift. Actually, you know what? Let me change that to a black, just so I can remember this shift here. All right, so in this case, again, now we have a fraction, but it's less than 1/2, so it's actually going to be compressing the graph. That means the graph only goes down to 1/2, up to 1/2, right? So for my amplitude, that's just going to be the absolute value of 1/2, which is 1/2. My period in this case, my b is again 1, so that's just going to be 2 pi. 2 pi divided by 1 is just 2 pi. We do have a phase shift. We are shifting the graph pi/2 to the right. All right, and we are shifting down 1. Now, as far as my domain, again, or that's my vertical transformation. So my domain is still the same, right? However, my range, now this one kind of gets a little tricky. Like students are like, all right, you're at -1/2 to +1/2, right? That's the amplitude, but then you're going down one. So like, what would that be? So that's where that kind of formula that I provided can be helpful here. This negative, negative a plus d, positive a plus d. So basically what I can have here is I can take -1/2 minus 1, and then I can take +1/2 minus 1. And by simplifying that, you can see that that's going to be a -3/2, and then 1/2 minus 1 is going to be a -1/2. So that is going to be a range. So sometimes when you're dealing with fractions or numbers that are maybe not as easy to be able to apply the operate, to add and subtract, using that kind of understanding the formula sometimes is helpful. That's why I wanted to add in that problem. And again, did I forget to write in range? Domain and range, yeah. Oops. Okay. All right, now let's go and get into cosine. So in this cosine example, again, really the same thing, right? We're looking for the same parts. We know the graph is a little bit different. So if we actually had to graph these, we would just have to apply them to a different paragraph because their initial period is different. But as far as the characteristics, they're exactly the same as what we just did. So again, in this one, we see that the amplitude is -2. So the amplitude is just +2. We have our period is going to be 2 pi divided by 2, which is just pi. We have a vertical shift down 1. Because you're subtracting 1. The domain is -infinity to infinity. And obviously we have a reflection about the x-axis again. Did I do that x-axis? Yeah, I did. Okay, and that's y-axis. And then again, so if our amplitude in this case is from -2 to +2, right? The negative doesn't matter. Like the negative is just reflecting. It's still from -2 to +2. But now the graph is being shifted down 1. So therefore, that's why it's from -3 to -1. And again, we're using those brackets to make sure that you understand that that is a... we're using the brackets to make sure that we understand that the points are included in the range. All right, let's go ahead and do these 3 problems. So again, in this one, the amplitude is just going to be 1, absolute value of 1. The period is just going to be 2 pi. 2 pi divided by b, again, same definition. Here we're going to have a phase shift of pi over 4 to the left. And we're going to have a vertical transformation of up 2. So again, our domain is all real numbers, just like for sine. But our range, again, the graph is going from -1 to 1, but it's being shifted up 2. So now the range is going to be from -1 up 2. That's going to be 1, 3. For next one, we have a -1/2. So my amplitude here, amplitude is going to equal the positive version of that, which is 1/2. My period, I have a nice little tricky one here. This one's kind of interesting. I have a -3/2. So again, it's 2 pi. And again, is it like 3, 3? Is it 2? Is it 3/2? Well, it ends up being 3/2. So again, we need to multiply by the reciprocal. And when you multiply by the reciprocal, you can get 4 pi over 3. So that's how long it takes the graph to repeat itself, which for graphing would not be that fun, but you could go ahead and do it. So there's the period. What else do I need to do? Oh, phase shift. There is no phase shift. There is no vertical transformation. We do have a reflection about the x-axis though. We have a domain, which is -infinity to infinity. And we have a range, which is really just going to be from -1/2 to +1/2. The reflection does not impact that. All right, last but not least here is, again, just another example of the cosine here. So we have the amplitude is just going to be 1. The period is just going to be 2 pi. We have a phase shift of 2 pi to the right. And we have a vertical transformation of down 1. Okay, so again, the domain is -infinity to infinity. And the range is going to be, was from -1 to 1, but now it's going to be from -2 to 0. And I put a parenthesis, which is wrong. You should use a bracket. Okay. All right, so that was it for sine and cosine. Basically kind of the same thing over and over again. I mean, there are more difficult problems I'm going to say I'm actually reserving for after we did this. But I wanted to kind of get these basic ones down for the sine, cosine, as well as tangent. Now, again, remember when we're doing tangent here, we're not identifying the So we're doing tangent here. We're not identifying the amplitude. There is no amplitude. So if we have a number in front, that is like compression, right? It's a vertical either stretch or it's a vertical compression. In this case, we're multiplying by 1/3, so we can say that is a vertical compression of 1/3, right? The period, again, is pi divided by b. So in this case, we end up getting 2 pi. And again, you're multiplying by 1/2, so that's a horizontal stretch. The range is going to be all real numbers. And I'm not going to do, did I do domain? I did domain. You know what? Let's just scratch out domain. Because I told my students you're not going to have to worry about the domain. And again, really, the domain is all real numbers except for where the asymptotes occur, right? So we don't really need to include that, again. The range, though, is going to be negative infinity for all of them. And we'll just kind of get used to writing that. The hard part is the vertical asymptotes. And the reason why is the vertical asymptotes represent pi halves plus pi n. Now, again, if we have the tangent function, and this kind of comes important. Let's go back up to the tangent graph real quick. Do I have the tangent graph here? Yeah. All right, here's the tangent graph, right? The vertical asymptotes occur at pi halves plus pi n, right? Every pi away from each other. Now, if I stretch or compress that tangent function, the asymptotes don't change. If I shift the graph up or down, the asymptotes don't change. The only times the asymptote changes is when I'm shifting the graph left or right, or stretching or compressing the graph. So what that means is anything inside of the function, right, is going to impact the asymptotes. So what I'm going to need to do when I need to identify my new asymptotes, I'm simply going to take whatever's inside my function. In this case, my function is x over 2, and I'm going to set that to the equation of the asymptotes. I then just solve for x, and that gives me my new equation for the asymptotes. So in this case, you can see x equals pi plus 2 pi n. All right, so let's just kind of work through them here. We have a reflection, x-axis. We're going right, pi halves, right? The period, that's the phase shift. The period is just going to be pi, right? Because b in this case is 1. However, the vertical asymptote, to do the vertical asymptote, you're going to take x minus pi halves. Why did I put a parenthesis there? So all you're going to do is do x minus pi halves equals pi halves plus pi n. So that's my original. Here it is with transformations. Therefore, add pi halves to both sides. X equals pi plus pi n. Now, if you have pi plus pi n, that is really going to be simplified to just pi n, right? Because it's just an extra pi. Okay, so we can look at the graphical portion of this. This is something we're going to dive into a little bit more deeper. But I just want kind of students to see this as far as when they're doing a multiple choice, how that would work. For this next one here, we have a 2/3. So even though it's a fraction, you can see it's less than 1 though. So therefore, that is a vertical compression of 2/3. We're multiplying by negative inside the function. So therefore, that is a reflection, the y-axis. We have this 2, so we know that's going to be horizontally compressing the graph, but we can just represent that with the period. So the period, again, is going to be pi divided by 2, not negative 2, because, again, remember, it's the absolute value. So pi divided by 2 is just pi halves. And then there is no phase shift, and there is no vertical shift. So we're just going to leave it from there. And then the other thing is the vertical asymptotes. So, again, we're just going to take negative 2, so the vertical asymptote. So we're just going to take inside the function and set it equal to pi halves plus pi n. So now we're just going to divide both sides by negative 2. So therefore, x equals, so negative pi halves divided by negative 2 is a negative. Pi halves divided by negative 2 is going to be a negative pi over 4. And then this is going to be a plus a negative, or just a minus, pi halves n. All right, and that would be your simplified version here. And again, you could subtract. You can just always leave that as a positive. You don't really need to subtract it because n is positive or negative. So therefore, we could just write that answer as a negative pi over 4 plus pi halves n. And really, that could also even be simplified to a positive pi over 4, really, because if you add pi halves to pi over 4, you get positive pi over 4. So why don't we just actually write that in there? And again, like I'm writing this so you guys can see what a multiple choice answer would be. Those are equivalent, but typically we like to have the positive version. All right, last example here. We have I guess I just could have done a +1 there as well, right? Yeah, well. So in this case, we have a vertical stretch of 3. We have a period. Again, that's just going to be of pi. We have a phase shift, which is going to be left pi. And we have a vertical transformation, which is just up 2. Now again, this is very important. Like if you originally had your asymptote at pi halves, but you move it pi to the left, like where is that new asymptote? Well, the interesting thing about this problem is it actually is just going to occur at back of that negative pi halves where we already had an asymptote. So let's kind of see how the asymptote here changes. I did forget to write the range, but I think you guys get the idea. All right, so vertical asymptote in this case is going to be x plus pi is equal to pi halves plus pi n. So if I subtract pi, I'm going to get x equals negative pi halves plus pi n, right? Well, again, what happens when you add pi to negative pi halves? You get, again, back positive pi halves. So this one actually is a transformation that's exactly pi, which is how long it takes the graph to repeat itself. So the asymptote equation is actually not the same. So again, this is, kind of a hard concept to really understand, but the nice thing is next lesson, we do this a lot more in depth. So it's a little bit easier to pick it up on it. And also it's nice to kind of look at the graph so you can see how this works, which we'll kind of do more in the next lesson as well. But at least therefore you can see what the equations are. And again, I don't, for this first kind of quiz, I don't tell students they have to simplify it into the positive or the most simplified vertical asymptote equation. I just want to make sure that they can set whatever inside transformations equal to that equation for your vertical asymptotes, and then to go ahead and solve for x. All right, the last problems that we needed to do, guys, was just those combinations. Those ones that got so tricky for students is when you had the b and the c. And the main thing to do is remember when you have that b and c is to factor out the terms. You've got to make sure your x in this case is going to be 1. So therefore that represents your b, which in this case, in this problem was a -3, which therefore, since it's a -3, that means it's going to be a reflection about the y-axis, and it's going to be a horizontal compression of my period. Instead of my period being 2 pi, it's now 2 pi divided by 3. Our amplitude in this case is just absolute value of -1, which is 1. Since there's a negative on the outside, that's a reflection about the x-axis. We're shifting 2 pi to the right. Again, it's not 6 pi to the left. When you factor out the -3, you can see it's 2 pi to the right. My domain here is -infinity to infinity, and my range is still going to be -1 to +1. All right, so the last 3 problems we got here is just going to be these combined functions. All right, so in this case, we have an amplitude is equal to 3. Let's go ahead and first thing we need to do is factor them out. So in this case, I can factor out a 2. Factor out a 2, that's going to leave me with an x minus pi. Okay, so now I can say my amplitude is just going to be absolute value of 3, which is 3. My period, which is going to be absolute value of 3, which is 3. 2 pi divided by 2, which is pi. And then also I am going to have a phase shift, which is pi to the right. And there's no vertical shift, so I don't need to worry about that. I'm not going to be going up or down at all. But again, my domain here is going to be all real numbers. What did I say? Did I say just, yeah. Domain and range, and then my range though, let's see what the range is. So again, now my amplitude is 3, so it's going to go down to -3 up to +3, which is my amplitude. -3 to 3. Okay, so again, it's that really main important point is the factoring out the 2. In this case, we can see that the x is negative, so I'm actually going to want to rearrange everything. So -x plus pi halves. Then I'm going to want to factor out the negative. Okay. So we have the negative and we have the x minus pi halves. Okay, so amplitude, and there is no amplitude, right? Be careful. So you sometimes get in those moods oh, amplitude, but again, there's no amplitude here. But we do have the period is just going to be pi divided by b. Well, b, remember, absolute value b. So since it's -1, we don't really need to worry about that. So that's just going to be pi. That does tell us, though, we have a reflection about the y-axis. And we are shifting right pi halves. Okay, there's no shift up or down, no vertical transformation. This does impact, though, our vertical shift, or our asymptotes. So let's go and figure out our asymptotes here. So our asymptotes, I'm just going to take this equation here as it's originally stated. Pi halves minus x equals pi halves plus pi n. Right? Well, now, as I subtract pi halves, I get negative x equals pi n. And then if I just want to divide by -1, I get x equals negative pi n, which is really the same thing as x equals pi n, right? It doesn't matter if it's negative pi n or positive pi n. You're still going to have the same equation for the asymptote in that case. And that's basically it. And then at the end, guys, I'll show you guys one more actually trick we can understand here. But you can see that the graph does have a phase shift, which I didn't write, which is pi halves to the right. Oh, I did write that. So that's the phase shift, which is right pi halves. All right, and the last example here, we have an amplitude, which is absolute value of -4/3. So that's going to be positive 4/3. The range here is -infinity to infinity. I'm not going to do the domain because the domain is all real numbers except for pi n, right? The range, though, is -infinity to infinity. The amplitude here, it's a sine function. So the amplitude is 4/3. The period is, why do I doing that? Stop. We see, guys, before we even get to this, we see that I have a b. I got to factor out that b. So this one kind of gets a little difficult because how can you factor out a 3 from pi? 3 does not divide into pi, right? But again, really factoring out, guys, is the same thing as dividing out. So I can rewrite this as a -4/3 times sine of 3 times x plus pi thirds. And again, like double check my work. 3 times x is 3x. 3 times pi thirds is pi, right? So when you're factoring out, you really are dividing out. You're really dividing by 3. So the amplitude, again, is going to be an absolute value of -4/3, which is just 4/3. The period, in this case, is going to be 2 pi divided by 3, which is just 2 pi divided by 3. We are going to have a phase shift of pi thirds to the left. There's no vertical transformation. My domain is from -infinity to infinity. And my range is, again, going to be from -4/3 to +4/3. Now, how are you going to, let's say you're really struggling with this and you're like, I don't like factoring. I don't think I can do that on my own. Well, let me give you a little tip to end off this lesson as far as another way to identify the transformations. So the sine graph, the initial period starts at 0. So if we have any transformations, this initial period is going to move. So this starting point is going to move left or right. So if it moves to the one left, if I find the new starting point is going to be -1, that means I just had to move from 0 to -1, meaning the transformation was shifting left 1. So what we would do in the graphing form, if I actually was asking to graph this, what I teach my students to do is find the new starting point. So if you have a shift left or right, you're going to have a new starting point. So what you're going to do is set your transformations equal to 0. Then just solve for x, right? So originally, this is what we call the start. So originally you would start at 0, but now you're starting at -pi/3. So if you originally were at 0, but now you're starting at -pi/3, where did you go? Well, you shifted to the left, or for you, it's shifting to the left pi/3. That's why that is pi/3 to the left, right? It's not left pi, it's left pi/3 to the left. And that works for all of these. You can set each one of these equal to 0. And this one, you'd get x equals -pi/2, right? Again, that's shifting pi/2. Oops, I'm sorry, that's a positive pi/2. Right, negative divide by. So that'd be x equals +pi/2. That means you're shifting pi/2 to the right, which is obvious here, pi/2 to the right. The only problem with using this technique is it doesn't remind you that there is a reflection there, right? This doesn't tell you that the period change or that b is 3. So it is helpful to identify the phase shift, but it's not really helpful in identifying the period and the reflections. And again, in this case, the same thing. Set 2x minus 2 pi equal to 0. And this x is equal to pi. So if we're originally starting at 0, but now we're starting at pi, that means we're shifting pi units to the right. So again, it's just another way for you to understand the transformations without having to factor, because I know sometimes taking a test or quiz, that can be confusing. So, all right, ladies and gentlemen, that is it. Feel free to add up any kind of reflection you have regarding today's lesson as far as understanding not only just the graphs, sine, cosine, and tangent, but also the components of the graphs and how to identify them from the equation. So I hope this lesson helps, and I look forward to seeing you guys on the next lesson. Cheers. Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we are going to work on graphing trigonometric functions, the reciprocal trigonometric functions. So that's going to be the cosecant, the secant, as well as the cotangent function. So again, these are the notes that I went through my class, and what I'm going to do is just kind of work through this lesson one more time, so therefore I can have some answers for you and for them. So basically, we're just going to learn, where these graphs come from, how they kind of relate to sine, cosine, and tangent, and then how to find the parts. So again, just a warning, I'm not actually graphing them. I used to teach that, but it just took us so much time to actually plot the points and everything. And, eventually I realized we don't really need, I didn't really think it was very beneficial for my students to spend so much time on the graphing, especially when we have graphing technology. So now we really kind of focus on our understanding as well as being able to identify the particular parts, like domain, the range, the asymptotes, domain, and the period. All right, so therefore what I did is I kind of started this lesson looking at the sine function. So last class period, we obviously learned how to graph sine, cosine, and tangent. And so what I did is I gave the students, all these points, and they plotted the sine function. Again, my scale is not perfect. These are not supposed to be evenly apart from each other. That's just the scale that or just how the graph that I used. But either way, they went ahead and plotted these points. Now, so students at least had an understanding of where the red graph, which is the sine graph, came from. Well, then what I did is I asked them, well, why don't we go ahead and find the cosecant? And rather than doing the cosecant for each and every one of those points, let's just do the first quadrant. So, I basically asked them to do the cosecant of 0, cosecant of pi over 6, cosecant of pi over 4, cosecant of pi over 3, and the cosecant of pi. Now, again, oops, I didn't kind of show that, did I? I guess I should let's go and do that. I'll draw that right here. So obviously we can draw the sine graph really quickly just by using these 4 points. Like if you know 0, like sine of 0 is 0, and then at pi halves, you can see it's at 1. And again, sine represents the y coordinate for a point on the unit circle. At pi, we're at 0 and 3 pi halves. But let's go ahead and do the first quadrant here, because I said, all right, let's just do the first quadrant. So we know this point, that's 0, comma 1. Then we had at pi over 6, that coordinate point is square root of 3 over 2, comma 1/2. Then we had pi over 4, which is square root of 2 over 2, square root of 2 over 2. And then at pi over 3, that's going to be 1/2, comma square root of 3 over 2. Okay, so that's where I got these first 4 points, because that's what I wanted just to focus on, was these first points. So again, we're looking at that's the wrong graph. That's 1, 0. Oh, and then we did this one as well. Okay, so we found the sine, and I kind of reviewed students with the sine, and then I asked them to find the cosecant, which is, again, remember the sine of an angle, sine of theta, right, is equal to the y coordinate. So the cosecant of theta is equal to 1 over y. And I said, all right, well, then just go ahead and reciprocate, and do this. But I mentioned to the students that, not always is just putting something over 1 the easiest thing. Like 1 over 1/2, just gets simplified to 2 over 1, which equals 2. Now, again, that's not usually too bad. But again, what about when you have 1 over square root of 2 divided by 2? You don't want to multiply by the reciprocal on top and bottom, then rationalize the denominator. So what I reminded them is, remember the reciprocal, yes, you can always write something as reciprocal as putting it under 1, but go back to our roots. Sine of theta equals opposite over hypotenuse. And remember cosecant of theta, this is again for a right triangle, not for points on the unit circle. But so cosecant was going to be the hypotenuse over opposite. So again, yes, y and 1 over y is a reciprocal relationship. But again, when you have fractions, just flip it. So rather than doing 1 over square root of 2 over 2, just do 2 over square root of 2. And then you should hopefully recognize how to rationalize the denominator, and you get square root of 2. So for cosecant of 0, if I take the reciprocal of 1 over 0, that's going to be undefined. The reciprocal of 1/2, you can see my work there, or just flip 1 over 2, flip it to 2 over 1, which equals 2. Square root of 2, we recognize that to be the square root of 2. And then 2 radical 3, when you rationalize that, so therefore you have 2 over square root of 3. Rationalize the denominator, you get 2 radical 3 over 3. So then what I said is, all right, let's plot these points for you guys. So obviously, the easy one, 1/2, that's going to go to 2. All right? Pi over 4, which was square root of 2, that's roughly like 1.3-ish. And then this 2 radical 3 over 3 was like 1.1. So you can see how those points kind of relay right there. And then at pi halves, you know, the sine is 1. And the cosecant of pi halves is going to be 1 over 1, which is also 1. So they share this point. There's actually, that's true for sine as well as for cosecant. Well, I also asked them to do, did I not write that in there? Oh yeah, I did do cosine of pi. Then I also asked them to do cosine of pi in addition to this cosine 0, because how do we represent this when it's undefined, right? And when it's undefined, we know that there's going to be a vertical asymptote. So again, I didn't write this point, but you can see at pi, it's going to be a vertical asymptote. And that is also going to be true for 2 pi. But my main goal was for students to kind of look at this graph and see, like, what is the relationship with these blue points and the red points? And a lot of students said, you know, it's flipped, it's the, you know, inverse or, you know, reciprocal or whatever else. And like, yes, it's, you know, those are all some words that I think carry some weight to this description, you know, but I think one of the ones that really stuck with me was like that mirror image, right? It's kind of like here is, you know, you could say like a little hump going down, and then this is the one reflecting up. Now, it's very important to understand these are not the same, right? Because again, we have vertical asymptotes here. So this blue graph is approaching the vertical asymptote, where the sine graph actually, you know, intersects at 0. So there, you don't have the perfect curve. And when we actually look at the graph on the decimals, you'll be able to see. But the general kind of relationship is like that mirrored image. They share a coordinate point, a vertex, right? A maximum or a minimum, which depending on which graph you're talking about. But then they kind of go in the opposite direction, like a mirrored image of each other. And you can see that kind of works again over here. Then the other kind of, then we started looking at, all right, well, let's talk about the relationships here of this cosecant graph. Well, if you kind of follow the pattern, like this opens up, then it opens down, then you can say the next one is going to be, you know, up here, right? I mean, it's going to open up. So you can see it starts to repeat itself. So therefore, the distance that the graph is going to take to repeat itself is going to be 2 pi, right? It's just like sine. So sine and cosecant have the same period, right? 2 pi. And again, that's the same thing. If you're going to look over here, like this graph is now going to open down, right? So if this opens up, then it's going to open down. So therefore, that helps us understand the symmetry. It's not going to be symmetrical about the y-axis, but it's going to be symmetrical about the origin, just like the sine function. So sine is odd, so is cosecant is odd. And again, that's something we're going to talk a lot more about in the next chapter. Let's see what else was happening here. You can see that the graph changes from decreasing to increasing, and therefore we have this little minimum point, right? And then we have an asymptote, and then it's increasing to decreasing. So we have a little maximum. But these are not the lowest points or the highest points of the graph, right? They're just the lowest or the highest points on a particular interval. So you can see these are what we call relative, again, minimums and a relative maximum. They're a high point or a low point, but they're not the absolute highest and the lowest points. We can also take a look at the range. Now, the range is very interesting. So, you know, the sine graph, we have this range is contained between -1 and 1. And the blue graph looks like it's kind of like that mirrored image of that. And I think this is really important, especially when we get into these problems. It's really important to kind of see that you can see this mirrored image of, you know, so if the range is from -1 to 1, the blue graph is from -infinity to -1. But again, it includes -1. And then from 1 to infinity, which includes 1. So it's really important to understand that kind of that mirrored image kind of shape or what's going on, because that helps us identify the range. In terms of the domain, you can see that we have asymptotes. So the domain is no longer all real numbers like the sine graph. However, we do recognize that the asymptotes occur when sine of x is equal to 0, right? Those are like the zeros or the solutions. Kind of interesting. Again, that makes sense, right? Because when y is 0, then cosecant is going to be undefined, you know, looking at the unit circle there. But again, we can see, well, not only do the asymptotes, you can see that they occur at every 0 to pi to 2 pi, 3 pi, and then 4 pi, and 5 pi. And therefore, I can write a relationship for those asymptotes to be every pi n, right? On every pi, there's going to be an asymptote. So if I wanted to write an algebraic statement for that, I would say x equals pi n, which obviously we're going to do. And the domain is just going to be all real numbers except for those asymptotes. So I think that is just about it for the cosecant function. We talked a lot about it, and then we kind of skimmed over the secant. Because it's really, guys, kind of the same thing, right? You can see we basically just take the cosine graph, and then we just kind of do the mirrored image. Now, at least as far as this initial period, you can see the cosine kind of gets like cut off here and here. But again, like you hopefully recognize that it's going to continue over this way and it's going to continue over that way. But continuing over this way, we can recognize that the graph is going to be even, just like the cosine function, right? Cosine's even, secant is going to be even. The other thing that's kind of different with cosecant is where the asymptotes occur. So again, the period is 2 pi, but the asymptotes occur every pi, right? When they start at pi halves, and then pi halves plus pi gives you 3 pi halves. So the asymptote equation for this is like tangent. If you remember tangent, the vertical asymptotes occurred at pi halves plus pi n. Well, secant occurs the same thing, pi halves plus pi n, because to get to the next asymptote, I'm going to have to add pi again, and add pi, and add pi, or subtract pi, basically just meaning n is going to be negative. So it is even, and so between these two functions, you know, this one's even, symmetrical about the y-axis, and the asymptotes are going to change. However, that mirrored kind of relationship, the range and domain, or the period, is all going to be really exactly the same. So then we get into the last one, which was the cotangent function. So if you remember, this red graph was this initial kind of period between 0 and 2 pi. And actually, I don't know why I didn't graph the, let's see, 3 pi halves. This would have been 2 pi. So if you remember, I kind of did my best little S curves that I could possibly do here. But again, to understand tangent, like the easiest thing to recognize, or at least, you know, when I told the students, like when you're trying to understand, like, you know, which graph is which, when is it undefined, when is it defined, the best points that you can use or to think about is this quadrant, or is this unit circle, just with those 4 points. Like just with these 4 points, you can determine when when cosecant, secant, and cotangent is going to be undefined, including tangent. Because remember, they're only going to be undefined when you're trying to divide by 0. So, for instance, tangent at 0 degrees, right? We graphed this point. We did the same thing with the other graphs for tangent. And we say tangent is y over x. Well, 0 over 1 is just going to be 0. You can see that point. But now when I do cotangent, which is with the reciprocal, which is 1 over x, or 1 over 0, I'm sorry, you can see that graph is now undefined, which for whatever reason, I did not put an asymptote there. So let's put an asymptote there. So you can see at 0, now the graph is going to be undefined, right? And then let's go and look at pi halves. So at pi halves, tangent was undefined, right? Y over 0 is undefined. But yet now when I look at cotangent, 0 over 1 is defined, which is at 0. So you can see why for the cotangent function, that's why I have now an x-intercept there. And then again, going to pi, just trying to do this initial period here. So for at pi, again, negative 1 over 0 is undefined. That's why I have an asymptote. So we have an asymptote at 0. We have an asymptote at pi. We know the graph crosses at pi halves, but do we know what this graph is going to look like? Well, a couple other points that kind of stem out, or at least the one important point that stems from this, is the pi over 4. Because at pi over 4, tangent and cotangent are exactly the same. It doesn't matter if you do y over x or x over y. They're both 1. So you can see how they share the point pi over 4, 1, and how they share the point 3 pi over 4, negative 1, right? But that's where really the similarities, you know, end, because remember, they still have that mirrored image, that reflection kind of idea going on. So if I kind of take that into consideration, and obviously you could plug in these points, you could obviously do the reciprocals, plot them if you wanted to. But what I did is I just kind of took that relationship and I plotted them over here, and therefore I just draw my nice little curve. So you can see how this graph kind of shows it, kind of like declines. All right, so let's go and take a look at the differences here then with tangent besides just the curve. Well, tangent looks like it's always increasing, right? Except for where the asymptotes are, the graph is always going up. Whereas cotangent is kind of the exact opposite. It's always decreasing or going down from left to right, except for where the asymptotes occur. Obviously, the obvious one, wherever x is defined, tangent is undefined. Wherever tangent is defined or undefined, cotangent has an x-intercept. The domain or the time, how long it takes the graph to repeat itself looks like it's going to be pi, right? So from here to here, and then it looks like the next one is going to be, again, from pi to 2 pi, it's going to repeat itself. So the period is just like tangent. It's going to repeat itself. And one thing I mentioned is the, let's see, it also looks like it's odd, just like tangent. Tangent was an odd function, symmetrical about the origin. What else we were going to talk about? We were going to talk about the domain or the asymptotes. You can see that the asymptotes don't occur every pi halves plus pi n. These blue graphs actually occur every at 0, at pi, at 2 pi. So it's kind of like cosecant. They occur every pi n. So that will be important when we are writing the domain. And then again, just like the tangent, the range, you can see this graph is going to be from negative infinity to infinity. Doesn't matter what the transformations are, that is going to be your range. All right, so basically, we kind of looked through these, and then I just kind of had students, kind of talk about that. And then we just kind of spent, one more time looking at these graphs so you can see this relationship, not from what we did on the board, in my class or what I just presented to you, but actually looks at a graphing calculator and kind of see these differences actually in there. So let's just go and take a quick little look just to kind of confirm everything. All right, so looking at the sine function, this is what we did before. We graphed the sine, and, again, just to make sure you understand, domain is all real numbers, all right? And you can see the period, goes into 2 pi from there. So let's go and take a look at the cosecant function. Now, again, remember, that Desmos is not going to give you the asymptotes, right? We need to understand where those asymptotes occur, but you can kind of see it looks like it occurs somewhere right around here, which coincidentally kind of looks like it's at 3.14 or pi, right? And you can see like that would make sense here. And again, like you can even have a little fun if you wanted to, x equals pi right there. And you can see like, yeah, that looks like that'd be an equation for an asymptote. But again, the important thing is, remember, sine is not a part of the graph. We just use sine to represent that they both share the point, pi halves 1, and they share all these points. But when we're actually graphing cosecant, if you needed to graph cosecant, or when we're just identifying the characteristics of cosecant, the sine graph is not there, right? So, but I just wanted you to see that reciprocal relationship. Again, see how their periods, it repeats every 2 pi, just like sine, but it has asymptotes, which sine did not. And you can see this relationship is exactly the same for cosine. Okay, and again, cosine is actually not there, right? So it's just using that for that reciprocal relationship. Now, the tangent and cotangent is not really as easy to kind of view. You can see there's the tangent. You can see how the graph repeats itself. If you remember, that was our initial period from negative pi halves to pi halves. And cotangent, obviously, is, again, from 0 to pi, right? So you can see, again, that pi, it's defined for x, and you can see that's where, again, where we're going to have that asymptote occur, right? And again, but you can see at least that they share the point pi over 4, 1, 3 pi over 4, negative 1, and then they also have that inverse relationship, that mirrored relationship. And again, it's not a perfect mirrored relationship, right? Just like I explained here, when you actually look closely, you can see that it's not a perfect mirrored relationship, right? It's not whatever's down here is going to be exactly up there because, again, there's an asymptote here. This graph crosses at pi halves, and this is going to approach x equals pi halves. So it's not going to be the exact mirror image, but you can kind of get the idea of that relationship, okay? So that's what I wanted students basically to come away from right here. So let's go back and look into now generalizing all of these characteristics. So when generalizing the characteristics, we basically just look at the transformations. And so I just reviewed the students the same slide that I used for sine, cosine, tangent, which is really the same slide that I used for all the 12 basic trigonometric functions. It does not matter what the function is. It doesn't matter if I'm talking about cosecant, the absolute value of x squared, sine of x. It doesn't matter what the function is. These a, b, c, and d are all going to impact your graph the exact same way, right? And I didn't even write them down like I did in the last chapter because, again, I told students, like, it's the exact same notes. A stretches and compresses your graph vertically. If a is less than 0, it's a reflection about the x-axis. B horizontally stretches and compresses your graph. When b is negative, it's a reflection about the y-axis. C is going to be your horizontal shift. In this case, we call that the phase shift, right? And D is going to be your vertical shift or vertical translation, which is, again, is shifting your graph up or down. So I did provide a calculator if that's something that you want to kind of play around with, just to, it hasn't really sunk in, which for a lot of students, for my own students as well, it didn't really fully, they still needed to kind of see it. So I provided it for those of them that needed it, but for majority of them, this is the third time we've kind of covered this. So they already kind of had a good idea of what to expect. All right, so here's the cosecant graph. Now I put these on two different slides because I wanted to provide I wanted to give students the parent graph for each of them. But in reality, the cosecant and the secant have exactly the same piece of information. Their period is bothly 2 pi. The phase shift is c. The vertical shift is d, right? The range is kind of look confusing, but I'll talk about that. But again, you can see the range, they're both have a relative maximum of -1 and a relative minimum at 1. So their range equation is right there. I didn't tell students, I said you could write it down if you wanted to, but I'm going to use a different approach when we actually do the problems. And then the only really difference between them, besides their graphs, is their vertical asymptotes and domain. Because again, for the cosecant, you can see the vertical asymptotes appear at x equals pi n. So every pi n, or every pi, right, n could be any integer, there's going to be an asymptote. So the domain is basically all real numbers except for pi n. So this is the initial period. Again, I provided the sine graph as the dashed line. It's not a part of the graph. That's why I changed the colors. But I just so therefore you could kind of see again where those points and everything comes from. Then we did the secant, which again is very similar, same kind of idea. You can see the same information. The only difference is, obviously, besides the initial period being different of the graph, you can see the vertical asymptote occurs at pi halves. Plus pi n, and therefore the domain is going to be all real numbers except for pi halves plus pi n. But yet the range is exactly the same, right? It has that relative maximum of value of -1 and that relative minimum value of +1. All right, and then cotangent, we could kind of put this side by side. I used to actually teach tangent and cotangent kind of together because you can kind of see side by side how they're just that reciprocal relationship with each other. They both have a period of pi. Right? So this is pi divided by absolute value b. C and d remains the same. The range is different, right? This is like tangent, -infinity to infinity. And the vertical asymptotes and domain is just like the cosecant function, where it's going to occur every pi n. And this is going to be our initial period. All right, so now that we got that done, let's kind of go through what we're going to do. Again, guys, I'm not going to be graphing them, even though I know it says graphing, but hopefully based on all of this information, you can go ahead and provide a rough sketch of what the graph would look like. And typically that's what I tell my students is they should be able to provide a rough sketch of what this graph looks like, basically, or at least the initial period. We used to had students, they had to graph 2 periods, but, I think just the amount of time that I spent teaching students to graph and helping them with graphing, I think we could have spent that time doing a lot of other things. And then again, they knew how to graph, but then they didn't understand the range or they didn't understand the vertical asymptotes, which becomes very important in other lessons. So it was like, well, why are we, focusing on plotting some points when they don't understand some other key information? All right, so the first example is, let's just kind of go through this because there is some kind of tricky parts on this that I am going to discuss. And I guess I didn't finish this. So the first one is period. That's pretty easy, right? If you look at your notes that I did, 2 pi divided by b. Remember, x over 4 is the same thing as 1/4 x. So 2 pi divided by 1/4, multiply by reciprocal, 4 over 1 on top and bottom, and that's how we got 8 pi. We have vertical shift up 1. And the range, so the way that I like to teach range, I don't like to use that formula. I like to think about what is the range of the cosine graph, right? Because remember, these are just reciprocals of each other, right? They have that mirrored image. So the cosine graph with no transformations is from -1 to 1. When I multiply that by 2, when I have an amplitude of 2 of cosine, that's now going to go from -2 to 2. This is something we talked about last class period. So now my range of this cosine graph, again, this is what I'm talking about right here, is from -2 to 2. Now the graph is being shifted up 1. So now the range is from -1 to 3. So if I can figure out the range of cosine, I can figure out the range of cosecant. Because again, like here is the cosine. Like if I know what that range is for the blue graph, I can figure out the range of the red graph, which is basically going down to -infinity to the low point, and then, or to the low point of sine, and then going from the high point of cosine, sorry, not sine, cosine, and then going up to infinity. So that's how I got the range. I know that the low and high point of the cosine graph is -1 to 3. So my range is going to be from -infinity to -1, and then from 3 to infinity. The vertical asymptotes, again, is interesting. So we got to understand, how are vertical asymptotes going to be impacted? Well, if you have graph with vertical asymptotes, when you stretch or compress, that doesn't change the asymptotes. When you shift up or down, the asymptotes remain the same. The only thing that's going to impact the asymptotes is when you're stretching or compressing or shifting the graph left or right. So we got to look at this function and we say, all right, the graph originally had a period of 2 pi. It just got stretched, horizontally stretched, to 8 pi. Right? So my asymptotes are going to change. And again, I'm not going to pull this up, but if you want to look at it, a lot of times for students, when they would kind of give me that confused look, I would pull up the calculator and be like, hey, see for your own eyes what's happening here. See for your own eyes why the asymptotes are changing. So if that's kind of something where you're at, click on the link, look at the Desmos. I put these 2 equations in there, so therefore you could kind of visualize and see that. All right, so we have x over 4 equals pi halves plus pi n, and then to the 4th. Good. So to find the vertical asymptotes, all you're going to do is take whatever's inside the function, because remember, inside the function is your horizontal transformations, right? So in this case, we just have x is being divided by 4. So I'm going to write x divided by 4, and then you just solve for x. So the original asymptote equation, so you set whatever's inside your function equal to where the asymptotes occur. Now again, you only have 2 equations for your asymptotes, right? It's either pi halves plus pi n or pi n. So how do you know which one? Well, you can either memorize them, you could guess, or my preferred method is just to use remember those 4 points on the unit circle? If you know those 4 points on the unit circle, you can identify when the secant is going to be undefined, and then hopefully understand it's either going to be at pi n or it's going to be undefined at pi halves n. And obviously it's going to be undefined at pi halves plus pi n. So you set it equal to the asymptote equation. To undo divided by 4, I multiplied everything by 4, and I got x equals 2 pi plus 4 pi n. All right, so for the next example, it's really important, again, that A, B, C, D formula. This is not written in that A, B, C form, right? My unknown is x. I want that to be written in front. So I don't even know what my B is in this case. So what I'm going to do is I have a negative out in front. That's a reflection of the x-axis. But I'm going to rearrange my variable and pi, right? X is the variable. And then I need to factor out the negative. So therefore, I can see that actually I'm not shifting the graph pi to the left. I'm actually shifting the graph pi to the right. And I have a reflection about the y-axis. So that negative tells me a reflection about the y-axis, and the graph is being shifted right to pi. Now, it's important, again, on this one to understand that the graph is being reflected about the x-axis, reflecting about the y-axis, which is really reflecting about the origin. And, just a little, again, reminder, cosecant is odd. So it's symmetrical about the origin. So actually, those reflections aren't going to have any impact on the graph. It's still going to look exactly the same if you needed to graph it. The range, again, I looked at the sine. So again, notice that there's really nothing that's happening that's stretching or compressing the graph or shifting up or down. The only thing that's happening is sine graph is from -1 to 1. Then the graph is just being, flipped, right? Well, that doesn't change the range for that function. It's still going to be from -1 to 1. So in this case, I can write the range from -infinity to -1, union 1 to infinity. The last thing that kind of comes up in this case is going to be the vertical asymptotes. So again, I don't know why I didn't do this, but let's just go ahead and set what's inside my function equal to my asymptote equation, which is pi n. But this one does involve definitely some explanation, so I'm kind of glad that this happened. So if I could add x, right, you could subtract pi and then divide by -1. But let's just go and do this. X equals pi n plus x, and then subtract pi n. So my asymptote equation is x equals x equals pi minus pi n, which is the same thing as x equals pi n. And students really get confused in this. How is this equal to that? But again, I think about this like there's a couple of different ways I explain this. One, I know the asymptotes occur every pi. So if I shift the graph over pi units, right, which is my transformation, the asymptotes are going to remain the same, right? I mean, if I have an asymptote at every pi, right? So let's say I have an asymptote, or let's just say, so if I have pi and then I shift it over pi, well, whatever pi was at 0 is now at pi. Whatever pi was at pi is now at 2 pi. But again, like I'm actually not changing the intervals of where pi occurs. And then the other thing is I had a reflection. Reflection is not going to change those asymptotes either. Now, another way to kind of think about this is like identifying, even numbers. I could say all even numbers can be represented by 2n, and where n represents any number, right? So, n could be -4. -4 times 2 is -8, was even. We could say n could be 5. 2 times 5 is 10, even number. I could also say all even numbers can be represented as 2 plus 2n. So again, we recognize though, if I have an even number and I add 2 to it, that's still going to give me an even number, right? It doesn't matter what the number is. If it's even and then I add 2 to it, it's still going to be even. But that adding 2 is redundant, right? So that's what the case here is. If I have pi minus pi n, right? Well, again, n can be positive or negative. So therefore, we don't really need it to be a negative pi n. Like negative pi n is really the same thing as positive pi n, right? Because n can be positive or negative. Typically, we like the positive version is more simplified. We'll see those more on the multiple choice kind of section. And then if I have pi n, but then I'm adding pi, like again, why do we need to add pi plus pi n? We could just use pi n, and that's going to represent all the intervals. So that's kind of how that works. I told students, I accept this for these two, for this chapter, but once we get into the next chapter, it's going to be important and helpful to understand that simplified version. All right, so now let's get into the fun stuff. So we're not actually going to graph, we're just going to identify all of the parts. Okay. So the first one is, let's just go and find the period. The nice thing about here is my b is just 1, right? So period is just going to be 2 pi. I am not adding or subtracting inside, right? Again, a lot of students are like, where, is it -2? Well, again, that's why a lot of times we use parentheses to differentiate that. So I have a vertical transformation or vertical shift down 2. The range, again, I'm just going to look at the sine graph. So the sine is from -1 to 1. Multiplying by 2 takes it from -2 to 2. And then the graph gets shifted down 2. So now the range is going to be from -4 to 0. So my range here is going to be -infinity to -4 included, right? And then all the way from 0 to infinity. As far as the vertical asymptotes go, there's nothing changing around the inside, right? So now I just need to remember what the asymptotes are for a cosecant. And again, like here's if you like forget, right? Like crap, what was that equation? Well, again, here's 2 points. It's really actually going to be these 2 points. Which one of these is undefined for the cosecant? That's 1 over y. Oh, that's 0. And again, it's also going to be undefined here. So that's going to be 0, pi, 2 pi, 3. Oh, that's going to be pi n. So my vertical asymptote is equal to pi n. No transformations, fairly basic, good to go. The next one here, automatically when I see a negative, I always like to write the reflection because I will forget it and most students would forgot it when they wrote their answers on the board. So let's just do this as a reflection, the x-axis. Our period is going to be 2 pi divided by 4, which equals pi halves. My range is, again, remember for cosine, right? It doesn't matter if you have the reflection. So the -2 doesn't really impact anything. But now it's going to be from -2 to 2. And that 4 is a stretch or compression, or it's a horizontal compression. So that's not impacting the range. So my range in this case is going to be from -infinity to -2, union 2 to infinity. However, the vertical asymptote, that is going to be 4x equal to, again, for secant, that's going to be pi halves. Secant, again, is undefined at pi halves, and then plus pi. So that's going to be pi halves plus pi n. Okay, so now I just need to divide by 4. And again, remember, divided by 4, guys, is the same thing as multiplying by 1/4. So you could also just multiply everything by 1/4 there. And we get our vertical asymptote is x equals pi over 8 plus pi over 4n. And again, you can see there's nothing redundant here. And this would be like kind of our simplified answer there. And yeah, simplified answer, and we got a reflection, we got everything. Sweet. All right, move on to the next one. Next one, we see that there is no stretch or compression. And there's our b again, in this case, is going to be 1. So our period is going to be 2 pi. We have a vertical shift or transformation of up 1. And we have a phase shift of right pi halves. Okay, so we have, that's going to be going right to pi halves. As far as the range, so again, for sine is from -1 to 1, but if I shift it up 1, now it's going to be from 0 to 2. So again, the cosecant is just that mirrored image of that range. So the range here is going to be from -infinity to 0, union 0 to infinity. And then let's see here. Vertical asymptote. So for the vertical asymptote, again, we got to set this is going to be x minus pi halves equal to pi n. So to solve for x, we're just going to add pi halves to both sides. Now again, you can't add pi halves to pi n, so my vertical asymptote is just going to be x equals pi halves plus pi n. And that looks like it's going to be, can't really simplify it or of any of that case, so therefore that's going to be good from there. All right, last one. Now in this case, we don't have this, we have a b, but it's not factored out. So that's the first thing we're going to want to do is factor out. And again, remember, factoring out a 2 is like dividing both terms by 2. And dividing both terms by 2 is like the same thing as multiplying by 1/2. So sometimes explaining it that way helps students understand that when you factor out a 2, you're going to get x minus pi over 4. Because a lot of students, they just don't like factoring, right? But factoring is the same thing as dividing. And dividing is the same thing as multiplying by the reciprocal. And again, you can always check your work. 2 times x is 2x. 2 times pi fourths is pi halves. So therefore, in this case, we can see that the graph is being, there's no reflection, right? But we can see that the graph is being shifted. So we have let's do period first. So period in this case is going to be 2 pi divided by 2, which is equal to pi. So my graph is being horizontally compressed. I have a phase shift of pi over 4 to the right. And that's it. So the range, again, the graph is not being stretched or compressed or shifted up or down. So the range is just going to be that mirrored image of cosine. So cosine is from -1 to 1. Again, nothing vertically happened. So therefore, the range is just going to be from -infinity to -1, union 1 to infinity. And then my vertical asymptote, this one's going to be a little bit more work. So again, we're going to set whatever's inside our function. You could use this simplified version if you wanted to, or you could use, just the original equation, 2x minus pi halves equals secant is going to be pi halves plus pi n. So when I add pi halves to both sides, pi halves plus pi halves is going to be pi. So that's going to be pi plus pi n. Hopefully you recognize that we don't really need the pi here, right? Like pi plus pi n can just be written as pi n. So you could divide by 2 on both sides, but let's just get rid of the pi. We don't need it. So hopefully for students that are maybe just looking at the answers, like, where'd the pi go, right? But again, it's redundant. It's like 2 plus 2n. We don't need the 2. So then you divide by 2, and you can say x equals pi halves n. And so I'll just say vertical asymptote is x equals pi halves n. All right, now let's go and look into cotangent, which is basically, again, guys, the exact same process here. The only really difference is obviously the range. Oh, I didn't do the domain, did I? Did I say to do the domain? No, I didn't say to do the domain. But again, just a little FYI, the domain is going to be all real numbers except for where those asymptotes occur. So it's really the same kind of idea. You just write domain all real numbers except where those asymptotes occur. All right, for the cotangent, though, I asked for the domain and the range. And again, but the nice thing about the range here is the range is going to be all real numbers, right? Always. Doesn't matter what's happening. It's all going to be all real numbers. And the domain is going to be all the values except for where the asymptote occurs. All right, and just so again, notice that the period is going to be pi instead of 2 pi divided by b. But in this first example, we recognize that the equation is not in our standard form for transformations. So I rewrite the x divided by 2 as 1/2 x, and then I'm factoring out of 1/2. Again, factoring out of 1/2 is like dividing out of 1/2, and dividing by 1/2 is like multiplying by the reciprocal. So if you multiply by 2 on both of these, you get factored out 1/2, and then you're going to get x plus 2 pi. And again, check your work. 1/2 times x is 1/2 x. 1/2 times 2 pi is pi. There you go. So we have a negative on the outside. That's a reflection about the x-axis. Our period is going to be pi divided by b. Again, multiplied by the reciprocal on the top and bottom, you get 2 pi. We can see here we have a phase shift pi halves to the left. Our range is -infinity to infinity. And then for our vertical asymptote, we're going to take whatever's inside of our function. In this case, I just used this version, but you could use this version or you could use that version. It doesn't matter. And you set it equal to your vertical asymptote equation, which is pi n. So I subtracted pi, which you don't really need, right? So in this case, I didn't simplify it. I left it in there. But again, like if you have pi n and then you're subtracting pi, you don't need the negative pi, right? It's like even numbers are 2n and then -2. Well, yeah, that's still going to produce an even number as well. So in this case, I left it in there, where in the last example, I dropped it off. So, because what happens is when you multiply by 2, to get rid of the 1/2, you get -2 pi plus 2 pi n. So you can see that's redundant, so therefore we drop it off there. So it doesn't matter when you drop it off, you're still going to get the vertical asymptote needs to be x equals 2 pi n. And then let's just do the domain. So the domain is going to be all real numbers such that x cannot equal 2 pi n. All right. So now let's just do these last 4 questions, guys, and then we are done. So I see a negative, so therefore I know that's going to be reflect the y-axis. The period, again, is going to be pi divided by absolute value of -4, right? Remember, it's absolute value of b, so that's just going to be pi over 4. The range here is going to be -infinity to infinity. I don't really know why I wrote to do the range because it's always that, right? Never changes. But the vertical asymptote is going to equal -4x is equal to pi n. Okay, so you divide by -4. And you could say x equals negative pi over 4n, which is true, which is correct. Typically, a more simplified answer would just be the positive version of that. Again, I'm not going to mark my students down wrong for this, but we look in a more simplified answer, or at least on a multiple choice, you would expect to see that in the positive version. And that is it, right? Yeah, it is. Okay. So one thing that students, also kind of forget about is like, what does this 3 do? Well, again, the 3, vertically stretches the graph, right? There's no amplitude for cotangent or for secant or for cosecant because there's no absolute max and min, which is one thing I forgot. these graphs are unbounded, right? Since the graphs are unbounded, there is no amplitude. Because remember, the definition of amplitude was the half distance from the max to the min. Sorry, I had to add that in because I totally forgot about it. All right, so in this case, we just have period is going to be pi divided by 3. That was easy. Pi divided by 3. No other transformations. You could say a vertical stretch if I asked for it. The range is going to be -infinity to infinity. I guess I should have shifted one down one, but yeah, why don't I do that? Why don't I just do a +1? Just change that. So therefore, I could do a vertical transformation of up 1. And then I could say my vertical asymptote is going to be x equals, oops, I have a 3x. You know what? That's what I should do. Maybe I should do, I'm going to change that. Let's see, what do I want to change that to? Do I have one of those in here? I didn't do one of those, did I? Yeah, let's do that. Did I do enough here? Okay. So I'm going to do this as a 3/2. Okay. So let me actually change this. So I'm going to change this problem. Sorry about that. All right. So the period is going to be pi divided by 3/2. Again, multiplied by reciprocal is 2 pi over 3. There we go. So now I have 3x over 2 equals pi n. So therefore, x equals 2 pi over 3n. Okay, and there you go. So I just want to kind of make it a little different because none of these that I kind of changed here. Here, I'm going to have a vertical compression. My period, there's nothing in front. So therefore, that's just going to be pi. I am going to have a phase shift as pi over 4 to the left. My range, again, is -infinity to infinity. My vertical asymptote, though, in this case, is going to be x plus pi over 4 plus pi n. So if I subtract the pi over 4, oops, not plus pi n, equals pi n. Okay, so therefore, x equals negative pi over 4 plus pi n. And again, if you wanted to kind of simplify this, if you add pi to it 1, like let's pretend n is 1, like negative pi over 4 plus pi would be positive pi over 4. So I could, actually, I'm sorry, 3 pi over 4. So another answer could be positive 3 pi over 4 plus pi n. And again, I just wanted to show you because typically we like the smallest positive as our simplified answer. And so if you were to see this on a multiple choice problem, you'd probably see as this is the answer choice rather than that. So you just want to make that connection that those are exactly the same. The last example here is I have a 2 in front of the x, so therefore I need to factor it out, which is again dividing out of 2. Again, 2 does not evenly divide into pi. So rather than think of how do I divide 2 into pi, you can just say, well, dividing by 2 is the same thing as multiplying by 1/2. I can multiply pi times 1/2. Pi times 1/2 is just going to be pi halves. But let's rewrite it here. So we have y equals cotangent, factor out the 2. That's going to be left with an x minus pi halves. And if I'm concerned or not sure if I did that right, I just multiply it back. 2 times x is 2x. 2 times negative pi halves is negative pi. So now I have my period is going to be pi divided by 2. I have a phase shift, which is going to be pi halves to the right. And I have a vertical shift, which is our vertical translation, which is down 3. My range is -infinity to infinity. And then my vertical asymptote is going to be 2x minus pi equals pi n. And I think actually, never mind, I already did a problem like this. So therefore I have 2x is equal to, oh, I don't need that extra one. Is it going to equal pi plus pi n? Again, you don't really need the pi, so we just have 2x is equal to pi n. And then divide by 2, x equals pi halves n. And there you go, ladies and gentlemen. That is how you identify the characteristics for your cotangent. your cotangent, your cotangent, your secant, and your cosecant. I hope you enjoyed, and I hope you helped out your graphing. If you have anything that you'd like to add as far as what you understood or what you had trouble understanding, please feel free to leave a comment down below, and either I or somebody can hopefully help you out. Look forward to seeing you on the next video. Cheers. Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we are going to work on inverse trigonometric functions. So this is the last unit in our trigonometry chapter. And again, what I'm going to do is work through my slides and give you basically the same lecture and notes that I gave my students. So therefore, you will have an answer key that you can kind of reflect on and hopefully learn a little bit more about inverse trigonometric functions. Hopefully that is why you are here. So basically what we're going to cover in this chapter is how to evaluate the inverse of any trigonometric functions. Even though I did change that, I don't cover the reciprocal functions. We'll do that later. I talk about how to apply and understand the restriction to the inverse trigonometric functions, how to evaluate the composition of trigonometric functions and their inverse, and how to use right angles to evaluate the inverse without using a calculator. So we are still on a non-calculator version. So, but to understand, these inverse functions, let's just kind of go back to what we did inverse functions with when we were just doing inverse functions with, quadratics. And if you remember when we were dealing with the quadratic function and finding its inverse, there's a couple ways, algebraically that we did this. First thing, we represented the f of x with, we used to use the variable y, right? And that allowed us just to do the algebraic process a little bit easier. Then we'd swap the x and the y, and then you just solve for y. Now, this was the first time that we introduced the plus or minus the square root of x, which was very, very important. So therefore, when you're graphing this, you have the positive version of the square root of x and the negative square root of or the negative version, square root of x, which is basically just a reflection about the x-axis. And then you just replaced it using our inverse notation, which was f, with the -1 up top. So that was the inverse, but the problem with chapter one was on functions. And if you look at that graph, it does not pass the vertical line test. So we basically just considered then the function x squared does not have an inverse as it's written, but basically it just has an inverse that is just not a function, right? So we just said, it's not invertible. And the way that we could describe that or understand that was anytime that a function was not one-to-one, basically it does not pass the horizontal line test, then its inverse is also, the inverse is not going to be a function. So therefore we just say it's ininvertible or it is not invertible. It does not have an inverse. Another way we look at graphing, rather than solving and doing that plus or minus, you could also reflect about the y equals x line. And that was usually like the preferred, quicker method of being able to graph a function in its inverse. And that's exactly what I do for the rest of these examples. So since our x squared was not invertible, right, its inverse was not a function, basically what we did is we applied restrictions. So this is what we did in chapter one. Whenever we had a function that was not invertible, we applied restrictions. And the restrictions don't really change much when we're dealing with the inverse function. Like here I have g of x equals x squared for x values greater than 0. So the only difference here is like when I find the g inverse of x, like algebraically the process is the same. The only difference is I don't need to include the positive and the negative version, because you can see when you take the inverse of that positive version of the red graph, I only have the positive version of the square root of x. So you don't really need to put the plus there. I was just putting it there just to kind of emphasize that it's the positive square root of x. But you can see that red graph passes the horizontal line test and the blue graph passes the vertical line test. So therefore, by adding the restriction, we allowed ourselves to be able to find the inverse of g of x. And the other most common restriction that we had was, we could also do x is less than 0. So now we take this parabola and we just restricted it for all x values less than 0. Again, algebraically, the work is going to be the same, but now you're going to get y inverse is now the negative version of the square root. So now you can see that the restriction here on our restriction impacts our final answer to be the negative square root of x. And you can see when I reflect that, how that is that reflection. That is the negative version of that square root of x right there. It's not both versions, right? And again, you can see that is one-to-one, and this is indeed a function. However, we didn't really play around with this, but in reality, we could really pick any restrictions that we wanted to, like at all. And so by applying our restrictions, like for instance, if I chose the restriction 1, 2, the important thing is when I do the restriction 1, 2, that limits my function to make sure it's 1 to 1, right? And therefore I can find the inverse, which is again going to be positive square root of x, but it's going to be restricted from 1 to 4. But it's important. You just want to say, well, any restriction then is going to make a function, because if you restrict it from -1 to 1, look what happens. You have a red graph that's not 1 to 1. So when you find the inverse, again, it's not going to be a function. So therefore, just adding a restriction does not make it invertible, meaning we have to be smart with our restrictions. So there's really two things I wanted to come away from this. Is one, if a function is not 1 to 1, then it is not invertible. Basically, the inverse is not going to be a function. So we have to make sure that when we are finding the inverse of a function, it has to be invertible, meaning 1 to 1. In the same respect, we're going to do that by adding restrictions, but we just can't add any restrictions. We want to be smart about those restrictions to make sure that they are going to include this or to make sure that it's going to be 1 to 1. So that's what we kind of talked about. And then we looked at Desmos, and by looking at Desmos, basically what we did is we looked at the graphs for each of these. And actually, you know what? Did I go through this? Yeah, let's go through this. Okay, so on the graphs, one of the things we looked at is, we looked at the sine graph and we say, ooh, that's not 1 to 1, right? That fails the horizontal line test miserably, right? Create any horizontal line, it's going to cross it multiple times. So the inverse, you can't even draw the function inverse would definitely not be a function. You can see that it'd just be a squiggly line, right? Going vertically. So that would obviously not be a function. So what we need to do is we need to restrict the graph. And so what I had students do is let's just play around with some restrictions. Let's pretend it was only x values that were greater than 0, right? Okay, well that works. But again, remember this graph continues on and on. So that's not going to work. Because obviously you want to restrict the negative values, that's cool. But if you just keep on going positive, it's still going to fail. So then we said, well, if we look to the right, the farthest we can kind of go to the right here is going to be pi halves. Because once I go past pi halves, the graph, the y values start to repeat themselves. So let's say the farthest we want to go is pi halves. And then as we start going to the left, I can go to 0, but I can actually go all the way over to negative pi halves. But if once I go to the left of negative pi halves, the y values are going to start to repeat themselves. So what we did is we say, well, the best restriction then is going to be between negative pi halves and pi halves. And you can see if I restrict the sine graph between negative pi halves and pi halves, then that is going to make the function 1 to 1. It's still the same function. I'm just restricting it between negative pi halves and pi halves. And you can see that is now 1 to 1. And that's going to cover the most amount of y values with it remaining 1 to 1, because you can't go any farther right or farther left without the y values repeating themselves. So again, that's the function that we're going to reflect. So then we took the y equals x line and I said, all right, that's what the graph looks like. And what do you know? You can see how this is actually programmed into Desmos, into this. And same thing with your graphing calculator. It has that restriction actually programmed in, because you could have chosen anyone. We could have done, this interval in 3 pi halves to 5 pi halves, right? Or negative 5 pi halves to negative 3 pi halves. But why use those intervals when we have negative pi halves to pi halves, right here at 0, right? So you can see here, that is how that restriction is. Now, the other thing I just wanted to point out with the students is, as far as understanding this, is we have this restriction. Remember these points, that's negative pi half to negative 1. And if you remember a function in its inverse, it's just the swapped version of those points. You can see here, that's 1, 1 comma 1 half, and this one's going to be negative 1 comma 1 half. So remember, you just swap the x and the y's. That was something that was very important. And if I can even get rid of the x, you can see how, again, that kind of works. You see how they're reciprocals of each other. All right, let's do the cosine. So the cosine, we kind of looked at the same thing, right? This goes on and on and on forever, fails the horizontal line test miserably. We could break it up into all values greater than 0, but again, that's not really helping us. So let's just say how far to the right we want to go. And let's just kind of start at 0. Well, if we go to 0, if we start at 0, and we go to the right, we say the graph really doesn't start repeating, the y values don't repeat themselves until we get to pi. And we can't really go farther left, right, like we did with sine, because then the y values repeat itself. So it looks like our interval is from 0 to pi, which indeed, that is our interval, from negative 0 to pi. And you can see that that graph passes the horizontal line test. So again, using our same kind of idea, if I wanted to reflect this about the y equals x line, Then I just do my cosine inverse, and you can see how that is a nice little reflection. Again, the coordinate points are swapped, right? Here's 0, 1. What do you think this one's going to be? Maybe 1, 0? This point is pi, negative 1. This one's going to be negative 1 pi, right? So you can see again how that swapped version, that y equals x, remember, swaps the x and the y axis. And I also just wanted you to see how we restrict the domain. Again, this is something like you can't graph. If you were to reflect this whole graph, it would not be a function, right? So this software has it programmed that cosine, we are going to restrict cosine from 0 to pi, therefore we can find the inverse. Because if we didn't have that restriction, we would not be able to find the inverse. It wouldn't be a function, right? It'd be invertible. So that's why the restriction is very important. And so right now we have sine is from negative pi halves to pi halves, and cosine is restricted from 0 to pi when we need to find those inverses. The last one is looking at the tangent. Now the nice thing about tangent is actually the easiest, because tangent, we don't really need to find the interval. Like we can see that, like I could pick any one of these, right? Any one of these little S curves is 1 to 1. So then what's usually like going to be the best one? Well, I would say the one that's right by the origin, right? So all we really need to do for this one is just remember, well, how far to the left and how far to the right is that? And if you remember from the parent graph for tangent, those are going to be your vertical asymptotes, negative pi halves to pi halves. Oops, not that one. There we go. There's tangent. So you can see where that green graph is. And then if I get rid of it, now I just reflect about the y equals x line, and I get this lovely graph. Not that graph. Where's my tangent inverse? Oh, I need that graph. And then this graph. There we go. Should be a different color, but either way. So you can see again how that is reflected. So tangent, it has the same restriction as sine, negative pi halves to pi halves. And that's something that we're going to want to keep into our notes. So let's go back into the notes and look at that. So in my class, we just basically kind of talked about those restrictions, where they kind of came from, because again, we could have chosen any restrictions. And I just wanted students to understand why those restrictions made the most amount of sense, because they are adopted as the go-to restrictions that we use for our trigonometric functions. So I just kind of went through, some notes here. Here's the initial period. Again, kind of looking at those points, you can see that the x values are restricted from negative pi halves to pi halves. And then obviously my graph is not a very, it's not a very good square kind of xy axis, but I just kind of did my best to represent that reflection. And again, you can see, remember, the domain and range are also swapped, right? That's just kind of like that interesting kind of portion of understanding the inverse functions. And then the cosine, same kind of idea here. When you reflect that, you can see that was that same graph we got from Desmos. Again, the coordinate points are swapped, therefore the domain and ranges are swapped. But again, remember, cosine has a domain of all real numbers. So you can't have, again, that's why we have to restrict it for us to be able to find that inverse. And then obviously we look at the tangent again, and just understanding those restrictions. So really the main thing is now understanding this notation for the inverse, because previously we used the notation for f inverse of x, which is really kind of like the same idea, f inverse of x. But again, so that's not raising f to a negative first power. You're not raising cosine to the negative first power. That is just our inverse notation. Also in calculus, it's more, we more often use the arc cosine, which really kind of represents the exact, it's the same thing. It's just a different version of that. So we use that more often in calculus. But in this class, I'm primarily going to just use the this -1 notation. And then I just kind of summarized again those restrictions. You can see how sine and tangent are the same. And then really the main thing is understanding what really we're asking for, right? When I say cosine inverse of square root of 2 over 2, what I'm asking for is the cosine of what angle is square root of 2 over 2, right? Cosine inverse of square root of 2 over 2, that equals an angle. So that's really the big nugget out of these notes, is when you're trying to use cosine inverse, you're looking for the angle. That is what we are looking for. What is the angle? So we use inverse trigonometry to find the angle. Remember, sine, cosine, tangent, all the trig functions, those are ratios of side lengths, of comparing side lengths. So, but those are comparing side lengths based on an angle, right? It's the sine of something, cosine of an angle, tangent of 30 degrees or pi over 6 or whatever. But you're always doing the trig functions of an angle. And so now we're using our inverse trig functions to actually find the angle. So again, that's that main thing is when you're using inverse functions, you're looking for the angle. In this class, our default is going to be find the angle in radians. We're not going to work on finding the degree or finding the angle in degrees. Another thing that I work on or just kind of expose the students to is, you know, if you're using cosine inverse of square root of 2 over 2 equals theta, well, then you can actually rewrite the statement as cosine of theta equals square root of 2 over 2, right? If you can write cosine inverse of square root of 2 over 2 equals theta, then just rewrite it as cosine of theta equals square root of 2 over 2, right? Because that's what you're asking. Cosine of what equals square root of 2 over 2. And this is the same thing we did in division of polynomials. Like 12 divided by 4 is equal to 3. It's the same thing as 3 times 4 equals 12. And just remember that cosine is that inverse operation, right? We undo it with kind of cosine when you get to that solving portion. So we're going to do solving more in next chapter, but I just wanted to kind of expose students again to understand, to really drive home that cosine inverse, like what it means and why we use it. Because now we're going to evaluate some problems. So the first problem is sine inverse of 1/2. So again, I'm looking for what is the angle? The sine of what equals 1/2? Well, the problem is there's two angles, right? You can say, and I'll even write this down here, you know, the sine of pi over 6 equals 1/2, and the sine of 5 pi over 6 equals 1/2. Now, there's actually infinite many answers, right? You could keep on going larger coterminal angles, but these two angles, at least on the unit circle, work. But the main thing is, remember, sine has to be restricted between negative pi halves and pi halves. So you can't just pick any angle. It has to be the only angle here between negative pi halves and pi halves. So instead of a lot of times writing down that function, what I will do is I'll just kind of draw this little, you know, restriction here, negative pi halves to pi halves. And you can see the angle 5 pi over 6 goes outside of the restriction. So 5 pi over 6 is not within the restriction, so therefore we can't use it as far as our inverse. The only angle that makes sine of pi over 6 equals 1/2 is going to be pi over 6, and that remains within the restriction, so that is our answer. Cosine is negative 1/2. Again, cosine is going to be negative 1/2 at 2 pi over 3 and 4 pi over 3. So we could say, you know, cosine of 2 pi over 3 equals negative 1/2. Cosine of 4 pi over 3 equals negative 1/2, right? So those are the two angles, or at least those are at least two angles that give us negative 1/2. But again, our restrictions for tangent, actually, you know what, I'm going to write these restrictions. Negative pi halves, comma pi halves. Cosine, inverse cosine, remember we restricted that from 0 to pi. So the only angle that I have up here that's between 0 and pi, a lot of times it's just easier to draw that kind of like red ring, is you can see 2 pi over 3. 4 pi over 3 is outside the restriction. So therefore, we were only going to have 2 pi over 3. And again, the other thing I mentioned to the students is, remember, these are inverse functions, right? There's only one answer. So even though I'm graphing using the unit circle, I'm giving you two options, there's only one answer that meets the restrictions of cosine. There's infinite many answers. And actually, this is a really important point that I probably should go up to there. You know, I'll drive this kind of home like, let's do a green. Like when you're looking at cosine, there's infinite many answers, right? There's infinite many answers when x equals 1/2. But there's only one answer within that restricted domain that meets it. That's why that works, okay? That wasn't something actually I taught with my students. So that's actually something I'm going to bring up next. That's something I'm going to bring up for next chapter, but I figured it'd be a good time to bring it up for you guys. So for our last function, tangent here, what we have is tangent inverse of negative 1. Now again, a lot of students confuse this tangent negative 1 with the, you know, x and the y-axis. But remember, the points that lie on the x and the y-axis. But remember, tangent is the y-coordinate over the x-coordinate. So the only time, again, first of all, tangent is going to be negative is in the second and the fourth quadrant. And remember, tangent is only going to be 1 at the angles of, you can see square root of 2 over 2 over negative square root of 2 over 2, right? Those are the exact same. Even though they look crazy, they're fractions and radicals, but they're exactly the same. So when you take the y over the x, that's negative 1. Y over the x, that's negative 1. So remember, these have, those have the, I don't know what I was going to say. I'll just move on from there. So the problem with this, though, is remember tangent has the restriction. Maybe that's what I was thinking of. I don't know. So the restriction here is negative pi halves again to pi halves, just like sine. All right, but here's a problem. Our two angles, 3 pi over 4 and 7 pi over 4, do not fall within the restriction, right? It goes outside of that restriction and then comes back in. Or at least 3 pi over 4 doesn't even land on it. So we know if it's going to satisfy, it has to be in this first and fourth quadrant. Now 7 pi over 4 looks good because it at least has the terminal side within the fourth quadrant. The only problem is the angle 7 pi over 4 is larger than pi halves, right? Pi halves is only from here to here. So 7 pi over 4 does not meet that restriction. However, if you do the negative version of that, right? So if you look at these, you say, oh, why don't I go from here to here? Well, you can do that, right? You can still get to that terminal side using the negative angle. That's a coterminal angle. So now I just got to figure out, well, how far is this to here? Well, again, 3 pi over 4 and 7 pi over 4 have the same reference angle. That reference angle is pi over 4. So they're both pi over 4 away from the x-axis. Because again, remember pi over 4 over here is positive square root of 2 over 2, comma square root of 2 over 2. So therefore, the answer is just going to be negative pi over 4. And that gives you this coordinate point, which satisfies, gives us negative 1, and that also satisfies our restriction. All right, so now let's get into some more examples. So again, with my students, I'm hoping that you're at the same point that I'm expecting my students to be at, where you kind of understand a lot of the points on the unit circle. So therefore, I'm not going to go in depth as far as explaining how and where these points came to. If you're a little weak on the unit circle, I would recommend having that in front of you. So therefore, as I am saying, where these points and angles are coming from, you can quickly kind of check my work. So sine of negative pi square root of 2 over 2. So what I'm going to do is I'm just going to kind of do a rough little sketch here. Sine is negative square root of 2 over 2. That's going to either be down here or down there. And again, you can't use these two angles, right? Those two angles are not going to work. It has to be this angle. So now I just need to figure out, well, what is basically that angle? How, what angle gives me a y coordinate of negative square root of 3 over 2? What is that reference angle going to be? And the reference angle in this case is going to be pi over 3. So the answer here is a negative pi over 3. Because the sine of pi over 3 would give you a positive square root of 3 over 2. So if it's negative, it's going to be in the fourth quadrant, which gives me a y coordinate negative. Cosine inverse of negative 1. Well, remember that's when the x coordinate is negative 1. Well, that's going to be this point over here. Remember, cosine has to be between 0 and pi. So obviously, I want to make sure I'm going in the positive direction. It does include 0 and pi, that restriction. So therefore, my answer here is just going to be pi. And again, we're looking for the angles, right? For C, I'm looking for when is tangent equal to square root of 3. So when tangent's equal to 1, like that's easy. It's square root of 2 over 2. So now I just got to figure out, well, when is it going to be square root of 3 over 2? So we only have two other options. We have, we have 1/2 over square root of 3 over 2. Or we're going to have square root of 3 over 2 divided by 1/2, right? Those are your other coordinate points from the unit circle. Y over x, or you could have this be y over x. Well, hopefully you've done a lot of work so far with these, and you recognize that this is going to be your coordinate point. So now we just need to be able to determine, what coordinate point is that when x is 1/2 and y is square root of 3 over 2. Well, that's going to be pi over 3. Now again, since this is positive here, that's pi over 3. That's going to give you your coordinate point that we were looking for, this 1/2, comma, square root of 3 over 2. So this point, let me just write this out there anyways. That's a positive 1/2, negative square root of 3 over 2. Let me draw these points in so you can see. So therefore, you can see that's the y coordinate over the x coordinate, which gives me square root of 3. It's in the first quadrant. So that one's rather nice. Sine inverse of 1. So again, that's when what angle makes the y coordinate 1? Well, that's going to be up here. Remember, it has to be between negative pi halves and pi halves. So that's 0, 1. So you can see that angle is pi halves. And then we have when is cosine going to be negative square root of 2 over 2? Well, again, understanding this cosine has to fall within these restrictions from 0 to pi. Well, cosine's only negative here in this second as well as the third quadrant. So, what are these two angles? Well, it's not going to be this angle. I mean, I could figure it out if I wanted to, but I just know it has to be this one. So what is that angle? What is the angle when the cosine is going to be a negative square root of 2 over 2? And when you look at the unit circle, you can see that that angle is going to be 3 pi over 4. So one thing actually I didn't mention in my notes, that's kind of a little tip that actually I gave away to my students up here, is notice that none of the angles that we chose, or look at least the restrictions, nothing is in the third quadrant, right? So when you're determining, what angle makes sense, if you have an angle that's in the third quadrant, you know that is not going to be the answer. So the third quadrant does not meet either of our restrictions for sine, cosine, or tangent. So therefore, if you immediately are trying to choose between an angle between the third quadrant and something else, you don't need to think about the angle in the third quadrant. That is definitely, that doesn't match any restrictions. All right, last one is when tangent is equal to 0. Now again, remember, tangent is y over x. So for this one, we need to look at, what are the coordinate points between negative pi halves and pi halves, where the y coordinate over the x coordinate is going to be 0. Okay, so you can see 1 over 0, that's undefined. Negative 1 over 0, undefined. The only point that works is 0 over 1. You can see that's undefined. So therefore, that angle, which is basically not moving anywhere, is just going to be 0. So that's kind of the basic idea. Again, this really depends on your being comfortable with the unit circle. And, I told my students, right now, you can rely on the unit circle, but eventually we need to get to the point where, you are able to not have to sketch this graph every time or look at the unit circle to try to determine what the coordinate points are. Because we start picking things up. You can see now we're going to do some composition. So if you remember, composition is plugging one function into another. And here, basically all we're doing is we're composing trig functions with their inverse, or inverse trig functions with another trig function. The basic idea here is just to really do the inside first and then work your way outside. So in this case, you can see I kind of did two problems here. I did the first problem, which is on the inside, sine of pi over 6. So I graph pi over 6, I say sine is equal to 1/2. So now this is equal to 1/2. So therefore I just rewrite the problem, cosine inverse of 1/2. So again, that's looking for what is the angle? What is the angle that produces 1/2 that meets the restriction of cosine? The only angle that is positive 1/2 that meets the restriction is going to be pi over 3. And remember, when you're, when you're looking at these, it's either a first or second quadrant for cosine, right? If it's in the first quadrant, it's positive. If it was negative, it would be in the second quadrant, right? But those are kind of two options. You can kind of see how that kind of works. For sine, it's kind of the same thing. If it's positive, it has to be in the first quadrant. If it's going to be negative, it's going to be that same acute angle, but just in the fourth quadrant. So anyways, let's do this again. Sine of 5 pi over 4, well, that's going to be the y-coordinate, which is y-coordinate, negative square root of 2. Sine inverse of negative square root of 2, you can't use that angle, so you're going to use the angle that's in the fourth quadrant, the negative version of it, which is negative pi over 4. And you can see negative pi over 4 gives you that y-coordinate of negative square root of 2 over 2. Last but not least here, we have negative 1/2, our cosine inverse of negative 1/2. So now we're actually doing the inverse first. So the cosine inverse of negative 1/2 is going to be 2 pi over 3, because we know if it's cosine's negative, or cosine, if you're doing the cosine inverse of a negative answer, or of a negative ratio, that angle is going to be in the second quadrant. And then we just do the tangent of 2 pi over 3, which is square root of 3 over 2 over negative 1/2, which we already kind of talked about. But again, you're doing an angle that's in the second quadrant, so we know it's going to be a negative square root of 3. All right, so now let's go and work on some more composition problems. Looking fun. All right, so in this one we have cosine of pi over 3. So again, I'm just going to kind of work through this, step by step, or just one by one. I'm not going to, or maybe I'll show the graph maybe of the first angle. Actually, I'll do the graph of the second one. Whatever the inverse is, I'll do that. So we have cosine of pi over 3. So cosine of pi over 3, that's going to equal pi over 3, cosine of pi over 3, that's going to equal 1/2. And the sine inverse of 1/2, again, to meet that restriction, is going to be right here, which is positive 1/2, comma, square root of 3 over 2. And so that angle, hopefully you got, is going to be pi over 6. For next one, sine of negative 2 pi over 3. So negative 2 pi over 3, this one we probably need to do 2 here. So negative 2 pi over 3 is right here. So that y-coordinate of negative 2 pi over 3 is going to be a negative, let's see, that coordinate point is negative 1/2 comma negative square root of 3 over 2. So now that's going to give us a cosine inverse of negative square root of 3 over 2. Now to evaluate the negative square root of 3 over 2, again, that's going to be a negative version. So therefore, that's going to be in the second quadrant. And negative square root of 3 over 2 is going to be when cosine, right? That's negative over there. So therefore, that coordinate point in the second quadrant is going to give you a 5 pi over 6, because that coordinate point is negative square root of 3 over 2, comma 1/2. So that angle is going to be a 5 pi over 6. All right, well, I guess I'll just work my way down. I'm not sure, A, B, C, D, whatever. So sine inverse of 1, we kind of did that. Remember, that was pi halves. So that's that point right there, which is 0, comma 1. So therefore, this is equal to the tangent of pi halves. Oh, I'm sorry, yeah, sine inverse, right, is just going to equal pi halves. Now the tangent of pi halves, we already have the coordinate point here. That's y over x. Well, that's undefined. All right, let's go ahead and work on this one. So tangent of 3 pi over 4. So if we were to go to 3 pi over 4, that's in the second quadrant. Right, remember that's going to be a negative square root of 2 over 2, comma square root of 2 over 2. So that's going to equal negative 1. So we have sine inverse of negative 1. Well, when is the y coordinate going to be negative 1? What angle? Again, has to meet this restriction. And that's going to be the coordinate point 0, comma negative 1. So that's going to be angle negative pi halves. Let's look at cosine of negative pi over 3. So negative cosine of negative pi over 3 is going to be down here. Negative pi over 3 is going to equal 1/2, right? Because that coordinate point is positive 1/2, comma square root of 3 over 2. So now that's going to be the cosine inverse of 1/2. And when is cosine equal to a positive 1/2? Now again, it can't be this angle because again, remember cosine has to be in the first and the second quadrant. So since cosine has to be positive, we know it's going to be in the first quadrant. And you can see that angle is going to be this angle right here, 1/2, comma square root of 3 over 2. And that's going to equal pi over 3. All right, last one here. Tangent inverse of negative square root of 3 over 3. And a lot of people look at this and be like, no, not going to do this one. But again, like, think about this, guys. And again, this is where like the practice comes in. You already have square root of 3 over 2 over negative 1/2. Like when you have square root of 3 over 2 divided by 1/2, we know that's going to give us square root of 3. Our only other option here is going to be 1/2 divided by square root of 3 over 2. Like that's the only other way based on the unit circle for the points that we have on the unit circle that's going to give us that. And again, when we simplify this, that's exactly what happens. When you multiply by 2 on the top and the bottom, for those students that didn't do their work, you get 1 over square root of 3. And when you rationalize the denominator, you get square root of 3 over 3. So you can see how that works. Now again, that's the, let's just make this negative. There you go. Okay. But again, this tells us, now again, we don't know where the x and the y is. We actually don't know where the negative is, but we know that's the y and that's the x coordinates, right? So what coordinate point then is going to be giving us this, cosine inverse or tangent of y over x? When that is the y coordinate, that's the x coordinate. So if we look at this, well, we know tangent is going to be negative. Tangent inverse has to be negative down here, right? It has to be that negative version. And we say, well, it's actually not going to be y. It's going to be the, y works. So this would be x coordinate, square root of 3 over 2, comma, negative 1/2. So for what angles now, what angle gives us this negative version, right? Because you can't do the regular version. You have to stay within that fourth quadrant. So that angle is going to be a negative pi over 6. So now you're just going to do the cosine of a negative pi over 6. Well, if you look at that cosine negative pi over 6, you can see that the cosine is just going to be the x coordinate, which is going to be a square root of 3 over 2. Okay, so there you go, ladies and gentlemen. And again, you can see, one last thing I want you to remember is, again, when we're looking for the sine inverse, right, we're finding these angles. When our last operation is actually taking the tangent or the cosine, we're actually getting a value, right, that ratio. So again, that's that difference between evaluating trigonometric functions and evaluating the inverse trigonometric functions. All right, on to the next one, which is evaluating with triangles. So everything that we did up here, I didn't really kind of explain why we're using the unit circle, but we were using the unit circle because these were all angles or values that we are familiar with from the unit circle, like pi over 3, 3 pi over 4, negative pi over 3, negative 2 pi over 3. Like those are angles that we recognize from the unit circle. 1 and square root of 3 over 3, or negative 1/2. Like those are points, or at least ratios, that we recognize from the unit circle. So when you see that, use the unit circle. But again, don't forget, the unit circle is just a easy way for us to take triangles and like organize that information, right? Because that's all the unit circle is. It's just made up of special right triangles on a coordinate grid. So the unit circle is still us evaluating the sine, cosine, tangent of special right triangles. It's just we simplified everything and put them on a circle, basically. So the reason why I bring that up is because a lot of students, they get used to using the unit circle, and then I provide them something like this, and they're like, crap, what do I do? Well, again, you're going back to our basics. Like, remember, cosine, yes, it's the x-coordinate, but it's the x-coordinate of a point on the unit circle. If that point is not on the unit circle, it's not the x-coordinate. It's x over r, where r represents the distance away from the origin. Or if we have a triangle, r would represent the hypotenuse and x would represent the adjacent side. So again, remember, cosine is also adjacent over hypotenuse. So they're just different definitions based on the information. So in this case, we have cosine inverse of 4 over 7. So the cosine of something equals 4 over 7. I don't know what that angle is, so I'm going to call it theta. Now, this is very important to understand. So if I say the cosine inverse of 4 over 7, I don't know the answer. I don't know the cosine of what angle gives me 4 over 7. But again, there's a couple important points. One, I know that is not an x-coordinate that's on the unit circle. And two, I don't know what the answer is, so I'm just going to use a variable theta. So therefore, I'll say, all right, this is going to equal theta, right? So I basically just said, I don't know what that answer is, but I'm just going to call it theta. So now I need to figure out what is the tangent of theta. So here's the nice part. If I have cosine inverse of 4 over 7, this goes back to our first lesson. This is enough information to draw a triangle. Cosine of theta equals 4 over 7. That is your adjacent over your hypotenuse, right? It's not on the unit circle, so it's not the x-coordinate. It's not on a coordinate grid, so it's not x over r. It's the adjacent over hypotenuse, so draw a triangle. So I put the 90 degree here, put the theta here, and I say that's my adjacent, that's my hypotenuse. Do the Pythagorean Theorem. This is a triangle in space, so we don't need to do plus or minus. And you can see the opposite side is square root of 33. So now doing the tangent is square root of 33 over 4, and there you go, you are done. The next one, again, looks completely confusing, right? But again, remember, like, sine inverse of this ratio, which of course, I don't even know what the value of x is, so of course I don't even know if it's on the unit circle. This ratio is equal to some angle. What is that angle? I don't know. So let's give it a variable, alpha. So therefore, if this is going to be called alpha, then let's just put alpha there. So what is the cosine of alpha? That is really our question. So again, going back to that statement that I talked about at the beginning, if this is equal to alpha, then the sine of alpha equals 2 over, this. Again, this is not a coordinate point on the unit circle. At least we don't know it is. So we're not going to say that's the y coordinate. We don't know it as far as on a coordinate grid, so we're not going to do y over r. But again, if you think about this as a triangle, you could say, oh, that's opposite over hypotenuse. So if I put opposite over hypotenuse as base alpha there of a unit circle, I can now solve for my alpha. So by using the Pythagorean theorem here, so I have quantity x, square root x squared, or square root quantity of x squared plus 4. Well, when I go and square that, I just get x squared plus 4. When I solve for x, or a, I just get x. So, oh, that wasn't a. Yeah, I guess my a is equal to x. So now I'm just trying to figure out what the cosine is, which is x over square root of x squared plus 4. And then if you rationalize the denominator, basically multiply by the square root of x squared plus 4 on the top and bottom, you get x times x squared plus 4 over x squared plus 4. So the only way to get around this, guys, is just to practice. So let's go and do this. But hopefully you guys recognize, like, it becomes fairly basic. Like, I'm not going to rewrite these equations anymore, but hopefully you recognize, like, this is opposite over adjacent. So for some angle. Now let's call this angle theta. So if this is theta, this is opposite over adjacent. So really, I'm just going to do, what is the sine of theta? So let's do the Pythagorean, let's call this c. So 2 squared plus 4 squared, so that's going to be, so I'll do c squared equals 2 squared plus 3 squared. We've already done this plenty of times, so that's going to be the square root of 13. So the sine is going to be opposite 3 over the square root of 13. And therefore, we'd say the sine of theta equals 3 square root of 13 over 13 when you rationalize the denominator, which at least in my class, I made sure the students always simplify their solutions with that. Let's go and work on this one. This one adds a reciprocal function, but that's cool. Like again, what is a reciprocal? Oh yeah, that's hypotenuse over opposite, right? You could write the equation again if you wanted to. Let's call this angle, I call this one theta. Let's call this one alpha. So again, let's draw another triangle. I like to just draw all my triangles the same. So therefore, this is 13 over opposite. Now, hopefully you recognize this is a Pythagorean triple. So you could do the Pythagorean theorem, but hopefully you recognize that answer is 12 because 13 squared plus 12 squared, 13 squared equals 12 squared plus 5 squared, okay? So now we just need to figure out the secant, which is going to be a hypotenuse. So therefore, we're having secant of alpha. Well, again, alpha here, so that secant is hypotenuse over adjacent. So that's going to be 13 over 12. All right, so now we have the ones with the variables. But again, guys, the same really idea is going on here. Cosine is going to be adjacent over hypotenuse. And let's call this angle beta. So let's draw a nice little triangle. Okay, so we have adjacent over hypotenuse. Let's call this adjacent side here A. So I can say a squared plus 1 squared equals x squared. When I solve for a, I'm going to get x squared, square root of x squared minus 1. So I'm kind of skipping some steps here because we've already kind of done this a lot. And again, we don't need to do plus or minus again because this is just a triangle in space. So therefore, that's a equals x squared minus 1. So now we're doing the sine. Wait a minute. Oh, I wrote that wrong. I was wondering. I'm like, there you go. Thankfully, nothing got messed up. That's the adjacent over hypotenuse. Okay, so therefore, a is x squared minus 1. So now when I want to do the sine, it's going to be, so let's call this beta. So therefore, the sine of beta is going to equal the square root of x squared minus 1 all over x. Right, so I'm equaling to beta there. But again, you don't really need to. You can just write the answer here up there as x squared minus 1. You know, if you are going to be introducing a new variable, make sure you have that defined from there. So for instance, we would actually really need to do this like 1 over x equals beta. Okay, for the last one here, I have x over 2. So again, same kind of thing. Let's call that for a triangle. Let's just go back to theta. So cotangent, remember, is adjacent over opposite. So we have x over 2. Again, using Pythagorean theorem, let's call this c. C squared equals x squared plus 2 squared. So therefore, c is going to equal x squared plus 4. And again, we're trying to find the sine here. So the sine of theta. Stop. All right, let's just set that equal to. So the sine of this theta is going to be 2 over that. So that'd be 2 over square root of x squared plus 4. And then you rationalize the denominator. And there you go. That is our answer all nice and scrunched in there. So just remember to rationalize that denominator, at least for the simplified form. So that was it basically with triangles. So we have, you know, when we're using the unit circle and we have triangles, there's one less problem oh, the reciprocal. Oh, I did do that problem. Oh, okay. All right, so I'm sorry, I made a mistake. So we're going to do, so sine inverse of pi over 4. So I'm actually going to erase this. Let's use that one. Oh, crap. So why don't I do, yeah, okay, let's do sine. That's fine. So we have sine inverse of sine pi over 9. Okay, that worked. Oh, I already did the answer. Oh, cool. All right. So last one, I took off the reciprocal. I'm not going to deal with that for this chapter because we're gonna work on that actually next chapter. We'll talk about that. So for in this example, what I want to do is, again, understand the 5 pi over 7. So, or what about if we do 5 pi over 7? Well, that's not an angle that we're used to. We don't know the point for 5 pi over 7 on the unit circle. And we can't draw a triangle, right? Because when we drew a triangle here, for these values, we drew triangle because we were given the inverse, right? So we could create, those were the sides of the triangle. Here, we're given the angle. So we don't know the sides of the triangle. But we also don't know the point on the unit circle. So the way I explained this problem to my students was, I said, why don't we do something that's very, very similar? Why don't we do tan inverse of tangent of 5 pi over 6? So when we're doing tangent of 5 pi over 6, all right, we know that's in the second quadrant. We know whatever this point is. And again, you don't really need to know the point. In reality, whatever this point is, we do, hopefully you know the point is negative square root of 3 over 2 comma 1/2. But notice I didn't write it down because we know that's not the answer, right? When I'm trying to find the tangent inverse of that angle, which is 5 pi over 6, I can't use that angle, right? Because the angle has to remain within this quadrant. So it can't be this angle. And so it has to be this negative version. Well, again, how do we figure out that angle? Well, if this angle is 5 pi over 6, that means it has a reference angle of pi over 6. This angle down here is going to produce the exact same tangent, y over x, that's going to be negative, right? Because it's either in the second quadrant or the fourth quadrant. So these reference angles are exactly the same. I use this angle to find this reference angle, which is pi over 6. So therefore, I know this angle has to be the negative version, right? Because you can't go outside and come back in. So therefore, you're going to use, so this answer would be negative pi over 6. So I use that understanding to explain this one. If I have 5 pi over 7, that's again going to be in the second quadrant, right? Because all the way halfway around is 7 pi over 7. Halfway around would be 3.5 pi over 7, right? So it's going to be in the second quadrant. So therefore, tangent's negative. The only other angle that's going to give me a negative tangent is going to be an angle in the fourth quadrant. But I can't go, remember, I still have to remain between negative pi halves and pi halves. So I can't go past pi halves. I have to use the negative version. So I have to go from here to here. Well, remember, these are the same reference angle. So if this angle is 5 pi over 7, how far is it from here to here? And that answer is 2 pi over 7, right? 5 pi over 7 plus 2 pi over 7 gives you 7 pi over 7, which is pi. So this reference angle is going to be 2 pi over 7. We need to go in the negative direction, which is a negative 2 pi over 7. All right, so I'll have to fix up these slides, and I apologize for looking at that. So let's go and take a look then at our angle. So actually, I already did this one. I didn't mean to do this, but let's just go and work through it again. I'll work through it from step by step. So, well, again, you have your angle, sine of pi over 9. I don't know where pi over 9 is, like where exactly it is, but I know it's in the first quadrant. It's going to be somewhere right there. I have no idea what that coordinate point is on the unit circle, but again, I don't need to. So if here's my angle, let's just pretend, whatever, like you can see up here, I just said exclamation mark, or not question mark, like what is it? But it doesn't matter. All I know is if I need to find, this y coordinate, let's just call this y coordinate A. So what is the sine inverse of A, right? That's going to equal the sine inverse of A. Well, again, we need positive A. Sine is only going to match the restriction here in the first quadrant, which is then just going to give us pi over 9. Okay, so again, the y coordinate, remember, represents that A. Sine inverse of A is just going to be pi over 9. So the nice thing is when you have angles that's in the first quadrant, the sine and the sine inverse actually undo each other, right? They typical inverse operations, they undo each other within the same restriction. So you don't have to worry about the restrictions. However, once you get outside that first quadrant, it matters. So again, we don't want to just say, oh, the answer is negative pi over 5. No, it doesn't work like that. Because let's look at this one. When I do a negative pi over 5, that's down here.
So, let's call this answer A here. Well, what's important about A? Is A positive or is it negative? Well, A is positive, right? So then you say, well, this angle, though, doesn't match my restriction. So my angle then has to be up here, right? Because I still need to get a positive A, but I have to match the restriction. So instead of doing negative pi over 5, I need to do the positive pi over 5. Okay, let's do another one with sine. So this one is going to be at negative 8 pi over 9. So let's go ahead and graph where that would be. Again, we know that 9 pi over 9 would be halfway around a circle, right? So negative 8 pi over 9 is just going to be just short. Right? And that's going to give us a reference angle here of pi over 9. Now again, remember reference angles are always positive, right? So that's going to be our reference angle, pi over 9. So that's negative 8 pi over 9. Okay, so the important thing though is when we look at this coordinate point, we have no idea what the coordinate point is on the unit circle. All I know is that y coordinate is going to be a negative answer, right? So the only way that I can figure out that negative answer that's going to match my restriction is to go over here. This angle also produces a negative A. So then what is that angle? Well, that angle is going to be the reference angle, but in the negative direction. So that'd be a negative pi over 9. And last but not least here, we have 6 pi over 5. So again, that's going to be another one in the third quadrant here. So let's go ahead and graph that. So again, 5 pi over 5 is halfway around a circle. So 6 pi over 5 is going to be right there. Again, we recognize the reference angle is going to be a pi over 5. And okay, so whatever this point is on the unit circle, whatever it is, we know cosine in this case is going to be negative, right? Because you're in the third quadrant. So so let's just call this a negative A. Whatever, we don't even know what A is, or we don't know what the y coordinate is, but it doesn't matter. We know we have to match the restriction. We have to find our other angle, which is going to be right here. So we know that has the same reference angle, pi over 5, right? This one's pi over 5 larger than 5 pi over 5, but we need to get to one that's going to be pi over 5 shorter, right? Because again, this is going to give us that same angle, but this angle at least is going to fall within the restrictions of cosine of cosine. And therefore, this angle is going to be a 4 pi over 5. Right? Because these two angles are going to have the same reference angle. The difference is this angle matches the restriction where this angle is outside of the restriction. So there you go, ladies and gentlemen. That is it for inverse trigonometric functions. I hope this helped because we dealt with angles, evaluating the inverse for angles that we didn't know their points on the unit circle, but without using a calculator. We were able to use the composition using right triangles, again, without using a calculator. We were able to use the unit circle to evaluate our composition, as well as to just evaluate the inverse of trigonometric functions, again without a unit circle. Without a calculator. So you can see using that unit circle is so powerful and so helpful. So I hope this helped you out as far as learning inverse trigonometric functions. Obviously, this is something we're going to be building on. So I did purposely leave some of the some definitions and things out. So therefore, I want the students to get this foundation set before we move on. But this is the end of the chapter, and I hope so far that has helped, and we'll look forward to seeing you on to the next one. Cheers.